This machine learning course starts at the beginning and goes all the way to an advanced level, teaching you both the theory and applications of machine learning concepts. Ayush, who teaches this course, is a data scientist and machine learning engineer.
Hi everyone and welcome to this course of machine learning. This course will teach you machine learning from very basics to an advanced level in machine learning. In this course, we'll be having both theoretical plus practical understanding of machine learning algorithms and building real-world AI projects. After this course, you will be able to build your own machine learning applications and real-world applications in many domains. Okay? But wait, first, who am I? My name is Ayush and I'm a data scientist at Artifact. I'm in Standard 9 from India. I have worked on various applications of artificial intelligence like machine learning, deep learning. I've worked on various domains of deep learning, which is known as computer vision, generative adversarial networks, and natural language processing. I've also contributed to the large AI projects in a team by Ondana. Okay, so this is my basic skills, and also I run a small YouTube channel, which is not as small, a big YouTube channel, which is around, we have 500 members, where I make a content on machine learning, deep learning, and various AI things, and I put end-to-end courses there. Currently, deep learning course is being launched, so you can start watching after this completing that deep learning course. Okay, so that is from my side, and you can connect me on LinkedIn if you want to know more about me. And I've also cleared some Microsoft exams, so you can get to know more about me. Okay, I'm also a founder of Andrew, an AI edtech platform, and also product-based platform. Okay, so that's it from my side, and I hope that you will get a lot more from this course. Now let's discuss the syllabus of this course. We will start with the very basics of machine learning, covering the fundamentals of machine learning in the section number 1. And then we will go further into understanding some algorithms like linear regression, logistic regression, support vector machine, principal common analysis, learning theory, and some ensemble learning methods like bagging, boosting, stacking, cascading, and then we'll talk about unsupervised learning. And you may think, hey Ayush, you only wanted to teach this much. No, absolutely no. This is a 10+ hours of course. So absolutely there is a lot more content. So this course is divided into sections, and each sections have different subsections. So I have made a full syllabus docs, what topics I'm going to cover in each and every topic or a section, divided into subsection, and you can assess the syllabus by visiting the course website. The course website I pre-made with are made with my friends of Andrew, so you can definitely go there and assess all the syllabus, all the problem sets of this course, and each and every section you will be having one problem set, and all of these is in the description down box below. Okay, all of where the timestamps as well as the course notes, okay, so are all available on the course website. So you can go there, see what assignments are there, complete that, and join our Discord server to discuss your assignments, and you can also submit it through forum. Okay, so this is the basic syllabus that we are going to follow, and I really hope that I worked a lot in preparing the materials for this course, teaching you all in the Blackboard and helping you understand each and every topics of machine learning in a very easy way. And this course have extensive syllabus, a very good syllabus which I haven't seen on full YouTube. Okay, so please be sure to see the syllabus, what we are going to cover. Just have told you in just short. The reason is I want to just start with this video. So I've given a shot. You can see the syllabus by visiting our course website for absolutely free. Everything for absolutely free. You can go to the course website, which is the link in the description box below. So let's start with the section number 1, fundamentals of machine learning. Okay, so now we'll start with machine learning. In this section you will get an introduction to machine learning, and we'll talk about introduction to machine learning, types of machine learning and their types, and we'll see some cool applications, and then we will see some problem of overfitting and underfitting, and then we'll wrap up this section. Okay, so let's start. Okay, so now we'll answer a question, what is machine learning? And you may ask, hey Ayush, it's very, can you tell what actually machine learning is? Yeah, you will get to know more and more about what actually the big picture of machine learning means in depth when we will go through this course. But in simple terms, machine learning is like this: computer programs that uses algorithms to analyze the data and make intelligent predictions based on the data without being explicitly programmed. And you might think, hey Ayush, what is kind of this? I'm getting a little bit confused. No worries. So let's get into this, and let me explain you what I'm saying over here on this blackboard. So you are given a data. Okay, and then you give to the algorithm. The algorithm analyzes the data, and whatever he has analyzed or learned from the data, it makes predictions based onto that. Okay, so specifically what we are doing, we want to make a function x that maps out input variable x to the output variable y. And you may think, here you sure confusing me, what is x, what is y? No worries. X is the input feature. Means let's take in a problem statement of predicting the house prices. Okay, so you wanted to do this. So here, on the basis of the size of the house, you wanted to predict the price of the house. Okay, so you give input variable x and you get output variable y. Okay, so on the basis of the size of the house, you want the price of the house. Okay, so you wanted to make a function. F that takes input x and maps that to y. And that's the definition of machine learning. That's the beauty of machine learning. So what we were doing, we want to map our input variable x. Maybe it can be maybe the size of the house, maybe the number of fans in the house, maybe the number of bedrooms in the house. So I'm denoting with a subscript 1, subscript 2, subscript 3, and we want to make a function that maps these input variables to the output variable, which we denote with y, which is the price of the house. And that we are doing, and we will learn how to make these functions. Okay, so that's the beauty of machine learning, which you can see over here. So let's see some of the more formal definitions which you will see more over the internet. Now, the machine learning is the field of study that gives computer the ability to learn without being explicitly programmed, said by Arthur Samuel. But one definition that I've said to you is totally means if someone asks you, hey, whatever your name, what is machine learning? You just ask, hey, I know a better way to define a machine learning. You just make a function that maps your input variables to the output variable. Okay, and that's the beauty, or that's called the machine learning. And I hope that you got it, what I'm trying to say you here. And x's are the input features that you wanted to, on the basis of that, these are the input features, and on the basis of that you want to predict the price. Okay, another definition of machine learning is the computer program is said to learn from the experience E with respect to some class of a task T and some performance measured by P. If its performance on T as measured by P improves with the experience E. And this seems a little bit intimidating, but let me clear this definition. It's very my favorite definition, although this is my favorite definition that I've shown to you, but let me tell you what the definition tells you. The definition is, so before that, let me take one example, which is let's take an example of checkers. Okay, playing checkers. I hope that you let's take another, because many other people do not play checkers over here. Okay, so let's take a email spam detection system. Email spam detection system, which you will make in this course. You will make this course. You will make this into the course. Okay, so this is a problem statement, and let's fit that definition onto this problem. Here, T is the detecting the emails, means detecting whether the email is a spam or not. So let's denote 0 as detecting a spam, or 1 as ham. Okay, so let's say ham. And E is the experience of his prediction, is the experience. Here E is the experience of detection, and P is the performance, how much performance increases upon to the experience. So in this way, higher the experience is, best the system is. But I think this is more formally fit to something called a reinforcement learning, which will not see the advanced learning, but again, the definition which you have to take is you wanted to make a function f that maps your input variables to the output variable, and that's machine learning, and or you can say that's the beauty of machine learning. Okay, so some of the applications of machine learning, there is I've just listed on a few, but there are a lot more. Self-driving cars, real estate, stock price prediction. In medical, we have a COVID-19 detection, maybe using chest radiographs, and then disease prediction, cancer detection, etc. And then it's just a boom, and I highly encourage people to get into this field and try to contribute to the world in a unique way. Okay, so you can see over here some of the applications of machine learning. So how it works. So what you do, let me get back to my board and how it actually works, all this, how it works. It's kind of very easy. How it works, first you study a problem. So again, let's take a problem. Let's take a problem of, again, a spam detection. A spam detection system. Okay, I think this C. Okay, so you have to make a spam detection system. So first you study the problem, you have a look at the data, how actually the data is. Okay, so first you do this. The second thing, this is a basic workflow. The second thing, you train the algorithm, and algorithm is just a function. It's just a function. Okay, f of x, which you will how it is defined, which you'll see later on. But you just have a function which is algorithm. This is the algorithm, and you train with this algorithm, and then you go further into evaluation. You evaluate it into you give new emails and check whether it's correct or not, and then if it is good, then you launch the system. Otherwise you analyze some error, you do error analysis, and then you go further into tuning improving your algorithm, or evaluating your and then you evaluate, then again do like this. So that's why machine learning is called ML, is very iterative process, which you will see in ML Oops why it is termed that. But if beginner, don't worry about it. Okay, but if you want to get it after this course, you can get to my GANs course, or maybe the deep learning course, or maybe another course which is DSA, which I'll talk about why it is very important, and then you can head over to the ML Oops videos. Okay, so this is the basic. You can head over to that and learn something new from there. Okay, so what are the types of machine learning systems? Since there are, I think, three types of the main machine learning systems are three types: supervised, unsupervised, reinforcement learning. And although there is few more, which is batch learning, transfer learning, active learning, passive learning, and etc., which you can learn obviously. When you go further, means into more into machine learning, then you will see that how you're learning these all, and you learn grasp each and every concept in a few minutes. Okay, so what is supervised learning? Supervised learning, let's go get back to my board again, and let's take an example of another example, which is my favorite. Not my favorite, but yeah, it's house price prediction. So I'm just writing it out: house price prediction system. Okay, so this is a house price prediction. So you have a feature. Let's denote that on the basis of the size of the house. I'm just taking example because in the real world, the size of the house, the number of fans in the house, number of bedrooms in the house, on the basis of. But just for now, for predicting this from the size of the house, you want to predict the price of the house. you want to predict the price of the house, which we denote as a y, and whatever we take as a feature, we denote this as a x. Okay, so there is there is only one feature, which is x1, and only we are getting a one output, which is y. Okay, so we provide x1 means the size of the house, and we are getting the price of the house as an output. Okay, so you can see over here that we have size and we have a labeled, means we have given the price, and the model can learn from this how the trend is on a, it can recognize patterns. Okay, so you can see over here that our data is labeled as a y, means we know what our output, so it learned from their label and input. That's called a supervised learning. How you can identify the problem is supervised, because you see the target variable, which is called the this is called the target variable, and this is called the features or variables. Okay, and the one we want to predict is called the target variable. So this is the features or variable. So you see that there is a relationship between your input value x and the output value y. Input value x and output value y. Why I'm saying it has some relationship, because you can see over that we are given the size of the house and we want to predict the price of house. So you can see over the entities that they have some kind of relationship, and we know what our output should look like. In this case, we know what our output should look like in regression. It's kind of a continuous output. Our output will be in continuous value, so we know what our output should look like, and that's called supervised learning. Okay, so I think I think it's going good, means you're understanding what I'm saying. So in simple terms, you can see the definition over here. We feed the data, and the data are labeled, means that the output variable, which we denote as a y, are labeled, and which has some relationship between our input value x and the output value y. Okay, so in unsupervised learning, which I'm not going to go dig dive just now, and further I will be digging dive into this. So the data are not labeled, and we can say that we don't know what our output should look like, and there is not kind of any relationship between what will be our input variable and what will be our output variable, and we have to recognize our patterns based on the data. For doing so, we have different algorithms which we'll study later. Okay, so I'm just not digging deep, but in simple terms, what I'm saying that. Let me tell you what I'm saying. Okay, so let's say these are the t-shirt sizing. You have a different t-shirts. I'm denoting this as t-shirt, so we have a different t-shirt, and and this is our data. And you have to simply classify or cluster it out. So what your model will do, it simply make this as a L. It simply makes this as a XL, and it simply makes as a M. Okay, so it's just make clusters. It makes cluster XL and L. And for now, I don't recommend to brainstorming these things, because we will first we have to understand fully supervised learning, then it will much clearer unsupervised learning. So I don't want to dive into unsupervised learning for now, but you can see over the definitions are cut to cut. Okay, so let's keep deep diving into supervised learning. So what are supervised learning? So in supervised learning, we know our output variable and input variable, etc. that I will just explain you over house price prediction. So in supervised learning, we have two types of problems. The problems of supervised learning can be classified into two types. So let me write it. A supervised learning problem can be classified into regression problem, and it can be classified into classification problem. Okay, so let's keep talking about what is regression, what is classification. So I'm going to take one example, which is a house price prediction, and we can see over here that our output will be in continuous value, because supervised learning, and we know what our output is. So you can see over that output will be in continuous value. Okay, so your output is in continuous value. And in classification, let's say given a picture X, means you want to classify an image of a picture as a cat, or a non-cat, or a non-cat. Okay, so you're given a picture X, you wanted to identify that as a cat or non-cat. Okay, so you can see over that is a binary. It is only two. It is called a discrete value. It is called the discrete value. Means we can now classify that in regression, if our output of that problem is in continuous value, that's called that is a regression problem. If our output of the particular problem is in discrete value, we can classify that as a classification problem. And you can see over here the definition is the same. Okay, so why we need to divide our data? So let me talk about, because I'm talking too much about data, but what is data? This question arises, a very good question that I want to ask by myself. Is data, how does data looks like? In data, let's take an example of an application system that is a price of the house, house price predictor. Okay, so the data will look like this. So I'm just making a data frame. So you have a size of the house, then you have a number of fans, then you have a number of bedrooms, then is the target variable, which is the price. So these are your X, these are your X, and this is your Y. Okay, and what you do, let's take 9 square feet to 22. I'm just taking as a 1,000, etc. Just $1,000. I'm just taking as an example. Don't think that is a 9 square feet size of the house. Don't think like that. Okay, so this is kind of thing. So this is kind of thing, and we have a size, and we have a number of fans, we have a number of bedrooms. Okay, so what you do here, you can see over here that we have a data. We have your data, and what you do, you divide your data into training and testing set. Training and testing set. So let's say you have 100% of data. You take 80% of your data for training your model and 20% of your data for testing. The reason why you take this to evaluate your model, because from where you will get all those for testing. So you just keep 20% for evaluating to check how best your model is. Okay, so this is the division of a data, which you'll see more later on. Okay, so there are two problems that I want to highlight is overfitting and underfitting. Okay, so what is overfitting? So let's take an example again. I just believe in examples. Okay, so here is your X and Y plane. I hope that everyone remembers in their school days. Oops, what happens? I hope that I drawn correctly. Okay, so you have this these features. Let me draw it very quick way. This is your data points, and what you do, you simply draw a straight line. You simply draw a straight line to make predictions. Okay, so let's this is your input, which is X. So let's say 2200 square feet. So it will go over here and check what is the price. So it will give here. Okay, so like that it will make prediction, which you'll see later on. So you can see over here that in underfitting, what happens? If your model has not performed well onto the training data as well as the testing data, means in underfitting your model does not perform well onto the training and the testing data, means your model performs bad on the training and the testing data. It means because you don't have a large number of data, you can simply add more data. Okay. But what happens in underfitting? Can anyone tell me what happens in underfitting? So let me highlight this little bit. Let me. So in underfitting, if your model has learned too much, this is because when you have too much of features. So let's say your it will try to touch each and every point. It will try to touch each and every point, and this is. And you can see if your model learned too much and it is generalizing very well onto the training data, but it fails to generalize well on testing data, then you can say that your model is overfitting. Okay, so you can see over here that that diagram is over here, and you can see over here that underfitting, which does not fit a straight line in a very good way, and good fit is good model. You can just fit a straight line, and in a bad fit, overfit it. Okay, so the solutions of this, which we'll see later on, but before that we'll touch some algorithms, and again some notations which I've already taught you. X means the input features, x1, x2 all the way down to the xn. Y means the output features. M means the number for training examples, and here let's say 600 is training example, which you will get to know more further, which when we will go more further into this course. Okay, so now we are done with this introduction of machine learning, and I really hope that you enjoyed this tutorial. And in the next section we'll be talking about one of the algorithm, which is linear regression, and I hope that you will really enjoy that. So let's meet at the next section. Okay, so now we will briefly talk about supervised and unsupervised learning with its application and some case studies and data sets, so to fully understand what happens in supervised and unsupervised learning. Okay, so let's start. So what happens in supervised learning? In supervised learning, as the name suggests, someone is supervising over here. I will take an example of a data set to help you understand better. Okay, so in supervised learning, what I have told you in the previous section is about in machine learning that you in supervised learning we make a function f of x that maps your input variable to the output variable. Okay, so here in supervised learning we have the input data as well as the output data. Okay, means here as an example that we have this data set. Just assume that we have this data set, and here we have this outlook feature, temperature feature means x1, x2, then we have a humidity as x3, windy as x4. Okay, and here the red one, play tennis. So here is our problem statement is given on these features, outlook, temperature and humidity and windy, we have to predict whether that boy will play tennis or not. Okay, so this is your target variable, or the variable that we want to predict. Okay, this is the target variable or the variable that we wanted to predict, so it is given in this case. So here we have our x variable as well as y variable, as well as the y. Okay, as well as the y variable. Okay, so we want to make a function f of x using this data that maps our input value, all these features x1 all the way down to x4 to a y variable. Okay, so we'll give input whether it is sunny or whether it is hot or high or false, and given on this feature the function will give you output whether it will play no or yes. Okay, so here this is a supervised learning problem because we have our labels which you can see over here. Okay, so and you can also see that we have some kind of relationship between our input value and our output value y. As you can see that and there is some kind of relationship, like let's take an example of house price prediction. So given an input feature size, you want to predict the price of the house, so it is on a same niche. So there is some kind of relationship between our input feature x and output feature y. Okay, another property of supervised learning is that these features which are input features are independent features. What do I mean by independent features? They do not have to depend on any feature. They don't have to depend on any feature, but this target variable y is a dependent feature because the target variable y is depending on these features, to be mapped, and is depending on these features. So that's why x1 all the way around to the xi, I equals to 1 all the way around to the k, means x1, x2, x3, x4 is an independent feature, which you usually call as an independent variable or feature, and y is your dependent variable or feature. Okay, so that's called the features, the supervised learning. So let me write a basic definition or a good definition of supervised learning. What is supervised learning? A good definition. Okay, so the good definition of supervised learning is, here in supervised learning we have our input features x, we have our input features x, we have our input feature x, large X, and just assume that x, large X, contains all features in a vector all the way under the xi. Okay, so we have our input feature x, and also we have our output feature y. We have our output feature y, and there is some kind of relationship between the input value x and the output value y, and x is called independent feature. X features are called independent feature, and y is the dependent feature because it is dependent onto the input features. Okay, so we have shown you an example that there is a y that is used to train using x. Okay, that is using x and y. Okay, so we'll be able to predict our model. So we will see in the next section how we make a predictive model, okay, as a part of linear regression. So let's see some of the but before that I wanted to just show you that there are two parts of supervised learning. First one is regression, second one is classification. So what do I mean by regression? You know what your output will look like, because here we know that what our output, because we have already seen our data. So you can see that the output is in discrete value. What do I mean by discrete value? Your output is infinite, means either it will be yes or no. So here, if it is in discrete value, if you know that your output is in discrete value, then you consider that as a classification problem. How you identify that is a classification problem? When your output is in discrete value, and when your output is in continuous value, means it's not finite. Maybe the age of the person, maybe the stock prices, that is continuous. Okay, so that's why if your output is in continuous, then it's a regression. If your output is discrete, then it's a classification. Okay, so let's see some of the applications of supervised learning to help you understand more better, to get the feel of supervised learning. So in supervised learning, we have our favorite. In supervised learning, we have maybe the stock price prediction. You are given closing price high, closing high, then etc. Maybe some volume, and you want to predict what is the stock price, and you want to predict this. You can consider C close as a target variable. You want to predict what will the closing price basis on high and volume. Okay, so high and volume are your independent feature, and C will be your dependent feature, which will be the y. Next is maybe the house price prediction. Maybe you want to basis on the size, like that. You want to predict what will be the output y. And maybe let's take example of a classification problem. You want to identify whether the person has a diabetes or not, basis on maybe the age, gender, BMI, etc. Okay, so we have this output variable y. Okay, so these are some of the applications of supervised learning. Okay, so now let's see unsupervised learning. As I'm not going to go deep dive into this unsupervised learning, there is a next section there is a particular section after supervised learning. We will cover the in-depth about unsupervised learning, but the core idea behind unsupervised learning, that in this case, in supervised learning, we are given xi as well as yi for every I equals to 1 all the way down to the m, and m here is the number of training examples, means okay, so that's m here is means we are given I. Okay, so here in supervised learning, we have this. In unsupervised learning, we have only xi's. We don't have yi's. We have only xi. We have x1, x2, x3 all the way down to the xm. Okay, we don't have the label yi. There is no supervisor that will guide you. Okay, and what you have to do, let's take an example. You have you have this. Here is your data set. So here you have a channel, reason, fresh, milk, grocery, frozen, detergent, and delicatessen. So let's take an example that unsupervised learning is used in market segmentation, segmenting your customers. So you have these features, and you don't have the whether the person with you. What you do, you just cluster the person which has similar nature. You just cluster the person. Let's take an example that this person used to eat milk, this person used to that, so you cluster this out, okay. Then you can hand code it, okay, this person used to eat milk, and then you can send promotion to these people, or big deal, another thing, to these people. So you can identify your business needs, etc. from these clusters. Either I'm not going to give deep dive into the application, etc., but I will go deep dive into the application, everything. But as of now, I hope that you understood supervised learning in depth. Okay, so that's it for this just a small video on supervised learning and unsupervised learning. In the next section, we'll be starting with actually the math, and then we'll deep dive into the machine learning. You will see the beauty of machine learning. Okay, so let's meet at the next section. Till then, do the problem sets. So now we have seen an introduction to machine learning, and I hope that you have really enjoyed that section. Now it's time for getting hands dirty into the maths. Now we will see some learning algorithms, which is linear regression, and then we will do one project which is Boston house price prediction. So I'm very excited to have your first learning algorithm in your toolkit. So head over to the next section. Okay, so now we will see one algorithm which is linear regression, which is a learning algorithm. As in our previous section, we have seen a machine learning and introduction to machine learning. Now we will see how to make that function f of x that maps your input variable x to the output variable we. Okay, so before that, I want to recall something, which is in supervised learning. We were having two types of problems. First one is a regression problem. The second one is classification problem, as you might think. Okay, so linear regression, as you know, as you can see from the term regression, it's a regression algorithm. So it's a regression algorithm that we'll study today, okay, in this section. Okay, so let's recall what is regression. It's a type of supervised learning algorithm, and here we know our output will be in continuous value. Our output will be in continuous value means, let's take an example that you want to predict the price of the house. Let's say you want to predict the price of the house. Okay, so you can see over here the output of this particular problem will be in continuous value. We don't have any kind of discrete value, so we can identify that this problem is based on to the regression problem. Okay, so let's see how this algorithm works in much more detail, so that you could get more intuition about, and you can ace an interview on linear regression. And also I'll be putting some interview questions over here of what someone can ask you and what someone not. Okay, so let's assume that we have a scattered data. So let me make one x and y plane. I hope that this is good, pretty good. And let me make that one. Okay, so I'm just going to make the scattered data that looks like this. Okay, so this is your data, and let's take as a problem statement as like this. Let's take a problem statement which is predicting the price of the house based on the size of the house. So let me write that: predicting the price of the house, predicting the price of the house, and this is the Indian rupees, so the price of the house based on the size of the house. Okay, so you will give x, which will be the size of the house, and you will get the y, which will be the price of the house. Okay, okay. So we have the scattered data, and in x-axis we have our size, which is our input variable, and in y-axis we have our price. Okay, so what we do, we fit a straight line, in linear regression, we fit a straight line like this, we fit a straight line which is called the hypothesis, which is called a hypothesis in regression term. This is called a hypothesis, which will see how we can compute the straight line. So we make this straight line, and you can see over here that after making the straight line, we can make predictions. So let's say that this is the size, and based on this we are making the prediction like this onto the y-axis. Okay, so and again, let's say let's say the size of the house is 2200 square feet, then the price will be like this, 22,000, etc. So like this we are making predictions. Okay, and you can see over here this line is a little bit far away from the actual data point, so that's the issue that we'll see later on. But you just construct a straight line that touches that closely touches each point, or that is closely passes through the scattered data points. Okay, so let's see how we can compute the straight line, because linear regression, as you know, linear means it constructs a linear line that separates the data. Okay, so let's see how it works. So for making the straight line, as I've already told you, this is called the hypothesis. So how we construct hypothesis? So this is called the hypothesis function. We compute hypothesis function like this. We have weight of every features. So let's say theta 0 times x0 plus theta 1, theta 0 times x0 plus theta 1 times x1 plus theta 2 times x2, all the way down to the theta n times xn. Okay, so you're summing it all up. So what you can see over here, that we have this theta and we have these features. This is the size, let's say the size of the house. Let's say this is maybe the number of fans in the house. I'm just taking this problem statement predicting the price of the house, so that's fine. Number of fans in the house, and etc. Okay, so these are the features, x1, x2, and x0 is the bias term, or the y-intercept, maybe if you know about intercept of y, means if x0 equals to 0, then your line will be crossing from the origin. If x0 equals to 1, then it will be from 1. If x0 equals to 2, then it will be from 2. Okay, so it determines the y-intercept from where he wants to make a straight line. Okay, so we have this theta 0 times x0, theta 1 times x1, theta 2 times x2, all the way down to theta x times xn. And let's take a particular problem statement and let's understand that. But before that, you may think, hey Ayush, what is theta here? What is theta here? We only have to learn, machine only have to learn this theta. Machine only have to get the best theta. Now we are able to make prediction. Now let's say we take theta 0. We take theta 0 to be 2, okay, and theta 1 to be, let's say, 3, theta 2 to be 4. Okay, so just now I'm taking only two features and one bias term, which is this is the bias term, and these are the two features. And x0 is always equals to 1. X0 is always equals to 1, so that's why we never write x0. Okay, so that's why we never write. We just write theta 0 plus theta 1 times x1. We do not write, but I just have showed you for a clear reason of those things. Okay, so you can see over here that let's take an example that we have two features, like the size of the house and the number of fans. On the basis of that, we have to predict the price. So for each feature, we learn the weight. These are called the feature weights. So we learn this, and if we get the best feature weight, we will getting the best prediction. If we get the bad feature weight, we'll be getting bad prediction. Okay, so let's say let's construct the problem. So let's say your theta 0 to be 2 times x0, which is x, where x0 equals to 1, so it's obviously 2, plus theta 1, which is, let's say theta 1 is 3, and times the size of the house plus the theta to be 4 times the number of fans in the house. Okay, so now using this, you can make the prediction. You can just plug in the size and you can plug in the number of fans, and you will be getting your desired output y. Okay, so just now you may think, hey, machine learning is not, we are only using it as a computational power, and you can see over here that how it learns theta, which we'll see, because machine learning is totally based upon learning parameters. Okay, so you will see how the thetas learn. So let me tell you, thetas, we have to only learn theta, we have to only learn, which we'll see the techniques where we have to only learn theta. We have to only learn theta, and if the theta is bad, then your hypothesis when the function is bad. So this is your function. This constructs your function like this: theta 1 times x1 plus theta 2 times x2 all the way down to the theta n times xn, and n here denotes the number of features, and features are the columns, okay, in the data. Okay, so this is a function, and you can use this function to map your input variable to your output variable y. Okay, so that's kind of we have our kind of a function that maps our input variable to our output variable. Okay. Okay, so now I think that we have got how we construct that straight line, and using this function we can construct that straight line, and we have to only learn these is called these are called the feature weights. These are called the feature weights, and these are called the feature weights, and this is the bias term, or the y-intercept from where the line should originate, as I've showed you earlier. Okay, so now I hope that you got intuition about hypothesis function. Okay, so now let's keep talking about the vectorized form of this. Means the vectorized form is maybe vectorization means how here we are separately computing for each values. We are computing theta 0, then times x0, theta 1 times x1, means separately for each value. So in vectorization we do at once. So what we do, we put our all the thetas. So we put our, so I'm just writing vectorized form. So we put our all theta, to be in joint vector theta, and let me do this: theta 0, theta 1, theta 2, all the way down to theta n, and theta, this is the feature vector. This is the feature vector which is the weights. You will further see that yeah, we have to only learn weights. Then you will believe me that yeah, we only have to learn weights whether it's a neural network, whether it's a machine learning. Okay, so you have this weights theta into joint vector theta, and you take a joint vector x and you store all your x's over there: x0, x1, x2, x3, all the way down to the xn. Okay, so you take this and then you take out the dot product. Okay, so then you take out the dot product and theta times dot product. Okay, so now your hypothesis f of x will be like this. Okay, so you just give this function, and thetas, what it will do, it will theta 0 times x1, theta 1 times x1, it will sum it all up, theta 1, theta 2, like this, broadcast it. Okay, and it is computing at once. Okay, so you can write and then sum it all up. Okay, so you can write in summation format: I equals to 1 all the way down to the n, or I equals 0 all the way down to the n, theta I times x, let's say I. Okay, so you are doing it's a vectorized form of that, and you can see over here in Python is very easy, just one line of code, like this. You just do like this: np dot theta and x, done. Okay, so it's very easy in Python, so don't worry how we can code this all. It's quite easy. Okay, so now we had seen the hypothesis and we have seen the vectorized form of this linear regression. Okay, so you may think, hey Ayush, how I can get this theta? But before that, how we can evaluate your theta is best? Means your thetas are good. The theta are good. So for evaluating your model, we have something called cost function. Okay, so why we evaluate a model? To check if our theta is good or not. Okay, so we check, because using that theta we are making prediction, we are multiplying with the features, and we will get feature. These the size we will get from the user, we will number of fans get the user, and we multiply with the weights and then sum it all up, and then we give the result. Okay, so this is the cost function, and here why we use cost function to evaluate your model. Okay, so you will get to know what we do. So let's say we have a scatter plot. So let me plot one scatter plot like this. Again, the same, I'll be doing the same, but this time little bit more crunchy. Yeah, I think so. Okay, so this is my plot, and what we do, we simply draw a straight line. This is your hypothesis. This is your hypothesis, which is f of x. And what this cost function will do, this is your actual data point. These are your actual data point, and these are your actual data point. What it will simply do, it will simply take out the distance between predicted, this is the predicted that I'm highlighting, and this is the actual. Okay, so this is the predicted, this is the predicted, and this is the actual. This is the predicted, this is the actual. Okay, so it takes out the difference between, or it takes out distance between like this, predicted minus the actual value, predicted minus the actual value, like this. Yeah, like this, and then sum it all up. Means higher this cost function will be, bad your model is. Higher the cost function will be, bad your model will be, and less the cost function will be, good your model will be. The reason why, if your points are on this line, and your cost function will be 0, because the predicted will be 0. Sorry, let's say predicted will be all the same, and actual will be also the same. So it will be resulting in 0. So just what we do, these are called the residuals in terms of cost function. So we just take out the distance between predicted and the actual value for all data points. Okay, so this is the cost function. Okay, so let's formulate this in a formula. Let's formulate this in the formula like this. Let me show you how I can formulate that. Yeah, so you just take out of j of theta. I'm just denoting j of theta will be like the short form of cost function, because we are checking how our theta is good or bad or not. Okay, because it only determines whether your model is good or bad. 1 over m, and m here is the number of our data points, plus I equals to 1 all the way down to the m, and you just model predicted value. Let's denote the model predicted value by y hat. And how we have we got y hat? Yeah, we have got y hat like this. Y hat equals to f of x equals to theta times x, mean dot product of theta and x, which is equivalently equals to the hypothesis. Okay, so let's note as a y hat minus y. Okay, and in other words, we can write this out like this. In other words, we can write this out like this: theta transpose xi minus yi, and this is just a hypothesis h of x. Okay, and transpose like this, your x will be like this, so you make this theta will to be like this. Okay, so it will be easier like this. Okay, so that's what this transpose is doing. But if you can do or not, just we are doing this. Let me write that: theta times x. Okay, the dot product between theta and x minus yi. Okay, minus yi for each and every data point. We are taking out the difference between predicted and the actual value, and then we're squaring. We are squaring here because it helps us to further call something called the gradient descent. Okay, for easily derivation of this cost function. You will see why I'm taking derivation term over here. Okay, so in other words, this is called the loss function, which is known as mean square error, MSE. Okay, which is called the mean square error. If you square root this, if you make this, let me show you what I'm telling. If you square root over 1 over m plus I equals to 1 all the way down to the m, theta xi minus yi squared. If you square root this like this, Okay, this is called the root mean square error. Root mean squared error. Okay, and higher this and better model this. Okay, that's just we are taking the square root. Okay, but we'll stick with this MSC. But in real world, MLE and Kaggle competition, they have given what they're going to use. Mainly I have seen RMSE to be used very much. Okay, so after we got our cost function and it tells, okay, your model is that good or that bad. Now if your model is bad, how you can optimize, or how you can get optimal theta, means best theta, how you can get the optimal theta? This is the great question to ask. Okay, so how you're going to get this optimal theta? For getting that, we have something called gradient descent, algorithm. Gradient descent algorithm, which is known as the optimization algorithm, which will help us to get the best theta. Okay, optimization algorithm. Okay, so let's dive into this algorithm and let's understand how we get this kind of thing. So let's say the visualization of the cost function will be like this. Okay, just for the sake of an example, I'm visualizing like this. Okay, so this is your cost function. I'm just writing as a z of theta. This is your cost function, and now your cost here is your theta, where the cost function is very high. Okay, so here is your theta. Okay, so what gradient descent does, it tweaks the theta. Means let's say your theta is 0, then simply let's say it makes theta a little bit to 0.2. Okay, it tweaks the theta, it changes theta a little bit, and if the cost function decreases, then updates the theta to be not like this, to be like this. If the theta go down, means the cost function little bit decreases, then it changes again 0.3. If the cost function decreases, then it's do not make this, then it's update this theta. Okay, then again it simply tweaks, checks if the j of theta going down. If yes, update the theta. Okay, until and unless your cost function is approximately equals to 0. Okay, so that is simply the gradient descent, and it's very simple that I just shown to you. So let's formulate this mathematically, because it's very simple when we formulate this as a mathematics. So how we simply what we do for tweaking these things, for tweaking the theta, we take out the partial derivative. Of your cost function j of theta. Now you will think, hey Ayush, you have why you have taken the calculus name? I'm not a calculus student, I'm not kind of that. Don't worry at all. It's I just want to give you one definition of a partial derivative. What it does, it simply tweaks your theta, and checks if the cost function decreasing. Okay, and it's just like the slope. But you don't need calculus. You don't even need calculus. Yeah, if you want to go on a research level, then you obviously need. But for now, for machine learning, you don't need calculus. For deep learning, even you don't need calculus. You can just what this equation is doing. It is just tweaking your theta a little bit. So it gives us like this 2 over m. So it gives us 2 over m plus I equals to 1 all the way down to the m, and this is a y hat minus y squared. Okay, so after deriving this partial, we get like this. Okay, so now after this we take out the partial derivative for every theta, means theta 0, theta 1, theta 2, theta 3, all the way down to theta n. We do for all theta, we take out a partial derivative of all theta, and then we update our theta. So here is a full gradient descent algorithm. So what we do, we simply write theta z. This is the update kind of assignment, theta z minus the learning rate alpha, and the kind of a partial derivative of your cost function. Okay, so what we are doing, this will be our new theta that I've just shown to you. We update the theta. So this is your old theta, means the bad theta. This is your learning rate, and what rate your this is the hyperparameter, which I will talk about in just a second in detail. But what we are doing over here, we are this alpha determines the rate, means if the alpha is too large, it will go like this. It will never converge. It will be like diverging like this. If your theta is very small, then I think that it will be never converge at local minimum. It will be like this. It will never converge at local minimum. So the optimal theta that I've used till now, it's a 0.1 for larger data set, 0.01 for okay, for a little bit smaller medium data set, 0.001 a little bit more smaller, and 0.00001. Okay, so these are the optimal for me I have seen so far is these alpha. But you can tune it. You can tune it using grid search CV or randomized search CV, which we will see later on. Okay, so I just say to you why this theta just determines the rate of your tweaking the parameter. Okay, just going down, and this is simply the partial derivative of your cost function, and we are updating this will be our new theta, and this is whole algorithm of gradient descent. Okay, this just equation tells us the whole algorithm for gradient descent. Okay, so now again I'm going to talk about vectorized form, how we can vectorize this. Okay, because I totally believe in vectorization. So let's what we can do here. We are in previously we are taking out the partial derivative of theta 0, and then we are taking out the partial derivative of theta 1 separately. What we can do, we can simply put that into like this partial derivative into a giant vector theta, into a j of theta with respect to 0, kind of this, and like this, all the way down to the end. Okay, so you just put into the giant vector and you just take out the partial derivative, whatever you want to take out, and then you just write the vectorized form theta z minus the learning rate alpha, and that gives us like this 2 over m times the x transpose x theta minus y, and this is your new derived equation, which is a vectorized form. Okay, and yeah, you can definitely use any kind of this is totally okay, but for vectorization you can follow or not, it's your upon, but for computational power just I've told to you. Okay, so we have seen so far, and now we are done with this. We have developed our linear regression model. We first have developed the model from making predictions, and then we have moved further to check if how our theta is good. Then we have seen how to get optimal theta. Okay, but you may ask, here Yushi, I have to do these kind of things. Yeah, you have to do these kind of things for getting your and if I say truth, the truth is in scikit-learn you can implement this in 3 lines of code. You can implement this whole algorithm into 3 lines of code in some library, but in programming assignment you have to implement from scratch this algorithm so that you can ace any kind of interview. Okay, so you may ask, there is something called the normal equation. There is something called normal equation that I want to highlight a little bit. Normal equation gives you a better theta in just one way. Means normal equation gives you a theta, optimal theta in just one equation like this. So equation is x transpose x, inverse of that x transpose y, and by using this, and x here is the data points, it means the features, so you can simply use this formula for getting the for getting your optimal theta. Okay, this is just the same as doing this, but not in every algorithm it will work. It will only for linear regression. The normal equation is only for linear regression, and I hope, but having a good intuition of all those, because in interview they usually ask this, they usually talk about normal equation. Okay, they don't talk about normal equation. They usually talk about this gradient descent, etc. Although there are too many optimization algorithm, some as like gradient descent. In gradient descent we have this, and then we have a stochastic gradient descent, we have a stochastic which is called HGD, we have an RM optimization algorithm, we have a RMS prop, and then gradient with momentum, which you will see advanced level in. I will talk about HGD, but RMS prop, and some more optimization algorithm or convex optimization, advanced which you will ever see in deep learning. Okay, or you can head over to the new era with the deep learning courses currently learning, and you can learn from there. Okay, so now we are done with this, and let's little bit spend some time on to some assumptions of linear regression. Okay, because in an interview they usually ask why you wanted to choose this algorithm instead of this algorithm, or what is the assumptions of this algorithm, etc. So the some of the assumptions of a linear regression, it should have a linear relationship. The data should be linear. And no or little multicollinearity. The correlation between variables should be nothing. Okay, no or little multicollinearity. Okay, you can see on internet for more. Okay, so now we have seen some assumptions, but I want to give you the things. What is independent and dependent feature? Independent means the size of the house, the number of fans, and number of let's say the bedrooms. So these are the independent feature because they are not independent to any feature for the kind of any value, but the target variable y is dependent on all these features. So that's why the target variable is called dependent, and these are called independent. Okay, so this is just a casual information to know because everyone talks about this. Okay, so now I think that we have talked very much in small amount of time, and I hope that you really enjoy this tutorial. And I'm putting all my effort. Then you can go onto my YouTube channel, New Era, and you can subscribe that YouTube channel if you want. Okay, so now we have talked that, and in the next section I'm going to go over in theory part I'm going to go over polynomial regression, but let's spend some more amount of, if I have time, let's spend 2 more minutes on to polynomial regression. Okay, so there is something called a polynomial regression. As we have seen the assumption that data should be linear, but let's say our data is not linear, then what we do? Okay, so let's say your data will be like, let's say your data is like this. Your data is like this. So if you fit like this, then it is obviously overfitting. So what you do, you just simply transform your data. To be like this into the quadratic form. To be you just simply transform this 1 degree to the 2 degrees, so it will conform like this. Okay, so your 2 will be transformed as, let's say, 4 and 6, 3 maybe transform as a 9, and whatever. So just I'm taking an example. Okay, so you transform your data to be fitting over the linear. Now your algorithm will be fitting like this. Okay, so now I hope that you have gone everything about polynomial, etc. Now we will talk about it. We'll do some Boston-Haas-Clarke prediction, and then we'll move on to the regularized linear models. Okay, so let's head over to the Boston-Haas-Clarke prediction, and then we'll move on to the regularized linear models. Okay, so now we have seen linear regression and we have done one project. Now it's time for getting your hands dirty in the programming assignment. You will be able to find the programming assignment in the description box below in the assignment page. Okay, so now we'll start with logistic regression. After doing assignment, come again and follow up with this course. So now we'll talk about logistic regression, and I hope that you will really enjoy this. Okay, so now we have seen linear regression, which is one of the regression algorithm. Now we will see one classification algorithm, which is logistic regression. Don't worry, don't think that this logistic regression is a regression algorithm. No, it's a classification algorithm. So because the name is logistic regression, because the underlying working of this algorithm is same as is something similar to linear regression. Okay, so you will get to know about this, how it differs from linear regression. Okay, so before that, let's be clear about, we are on the same page about classification. What is classification? Okay, so this is a great question to ask to yourself. What is classification? So let's take an example. That given an image X, you want to classify this image as a cat. If it is cat, then we will name it as 0. If it is non-cat, then we will name it as a 1. Okay, so this is a decreed value. Our output is a decreed value. And the classification is a supervised learning approach. So this algorithm is a supervised learning algorithm. So here we know what our output should look like. So here our output is a decreed value. So we can classify this as a classification task. Okay, so that's the classification, and something called the binary classification, and we have a multi-class classification, also called multi-class classification. Means maybe the person has a cancer, person has a pneumonia, etc. This means integrate value. Your output is a finite value. Okay, so we have this classification and this tool. So now it's time to study about logistic regression in detail. And so what we do in logistic regression, we classify the data. So let's start with hypothesis. In linear regression, we have our hypothesis, which is h of x. Let's denote as h of x equals to the, in logistic regression we also do the same, theta 0 times x0 plus theta 1 times x1 plus theta 2 times x2, all the way down to the theta n times xn. Okay, so in linear regression we are doing the same for drawing a straight line, and here we are also doing the same for a function, and this will be for linear regression, and the same for logistic regression. And this is the step, this is the first step for hypothesis, and the second step of hypothesis means the model predicted value equals to the sigmoid of h of x. So let's denote this as a short form of z. Okay, so this h of x is g, and g here is simply h of x, and h of x is here theta 0 all the way down to theta n. So we're going to name it as a theta transpose x. Okay, so you just do the sigmoid of your h of x, which is your prediction function. So you just do the sigmoid of this z, and you get your output. So let's say what this sigmoid does. You get your output from logistic regression, and this output makes the whatever the output came, let's say 22 to between 0 to 1. The sigmoid, if you apply sigmoid to this, you apply sigmoid to this, then it makes your output between the range of 0 and 1, and you set the threshold if the model predicted y hat is greater than 0.5, then this picture is a cat. Okay, otherwise if it is smaller than 0.5, then it is a non-cat. Okay, and this is what we are doing in linear regression. We are just this was our hypothesis, but in addition we add a sigmoid to our h of x. And the reason why we add sigmoid, it's totally because that we want our output between 0 and 1, in the range of 0 and 1, so that we can make prediction like this. So you apply sigmoid, and the formula for sigmoid is 1 over 1 plus e to the power minus z, and z here is h of x. Okay, so this will be your whole hypothesis. This is your prediction function. Okay, now you just put the z and theta. You have to learn theta. You have to learn these thetas, which is called the parameter weights. Again, the same as a linear regression. Okay, so what we are doing, we are just doing the same as first step. We are doing the same as a linear regression, and then we are applying a sigma at that h of x, and then we are getting the output, which is in the range of 0 and 1, and we set a threshold. 0.5 is a threshold, and if the particular the model predicted y hat from this output between the range is greater than 0.5, then it is a cat. Otherwise, if it's smaller than of 0.5, then it is a non-cat. If you want to be more strict, then you can make 0.7. The probability is greater than 70%. Okay, so let's say your model output like this, 0.80. Okay, so it is equals to the 80%. Your model is saying that a particular this image is 80% accurate, that this is a cat. Okay, so you just make it as a 1, round off to 1, means it is a cat. Otherwise, if it is 0.40, then it's 40%, that is so you make it as a non-cat. Okay, so this is the basic thing that you should understand. This is a prediction function that we have made, and again we have to only learn these thetas. Means we have to get these thetas to get our good output. Okay, so this was a logistic regression, and the hypothesis for logistic regression. Okay. Okay, so now in linear regression we have seen something called a cost function, and cost function simply what it does, it simply gives you the accuracy of your model. Means if the cost function is very, very high, then your model is very bad. If your cost function is low, then your model is good. Okay, so it helps us to evaluate your model. Okay, means the loss function. It should be all the cost function for a good model. Your J of theta means the cost function should be approximately equals to 0. Okay. Okay. So in logistic regression we have defined a little bit different this cost function like this. Let's do for one training example like this. J of theta equals to -1 times yi, the log of h of xi plus 1 minus yi, 1 minus yi, log of 1 minus h of xi. Okay, so this is your cost function for one training example, and you can see over here that we have a cost function -1 times the yi times the log of h of xi, and 1 minus yi times the log of 1 minus h of xi. So what we are actually doing, so let's break down this equation and let's understand step by step. Okay, so what we are doing here, we are doing yi is the ground truth, and h of xi is your model predicted value, which is the model predicted value, and it's just taking the log of that your model and multiplying with the yi. Okay, so let's say your y is equals to 0, and your model predicted y hat is also equals to 0. Then your cost function will be approximately equals to 0, because they both are same, so your cost function will be 0. Okay, will be low. If let's say your ground truth is 1 and your model predicted is equals to the 0, then this is a mismatch. Your model done very bad, so your cost function will be very, very high. Okay, so this is what the basic intuition behind this cost function, and this is your basic formula. And again, you can see over here that we do this kind of for okay, so let me write the equation for m training example. We have done for one training example, so let's do for m training example. So let me write the equation for that. So you have a j of theta, and 1 over m, I equals to 1 all the way down to the m, yi, log of h of xi plus 1 minus yi, the log of 1 minus h of xi. Okay, so this is the log loss. This is sometimes called as log loss in terms of machine learning. So you just this is your cost function that is used to use as a loss function that we have seen so far. And I've given an example when both the output is correct, your ground truth and your model predicted is equals, then your cost function will be 0. Otherwise, if it is different, then your cost function will be very, very high. Okay, so this is the cost function for your logistic regression model. So let's recapitulate the two things, the hypothesis and your for cost function. So the hypothesis is that h of x equals to the sigmoid of z, and z here is theta transpose times x. Okay, the dot product between transpose times x, and you just take the equation, which is similarly equals to 1 over 1 plus e to the power minus c. And z here is just a theta transpose x. Theta transpose x. Okay, so the theta contains the parameter weights. Theta contains the parameter weights, and x contains the x1, x0, x1 all the way to multiply. Okay, and by convention we are using x0 equals to 1. You can re-watch that linear regression section once more if you are getting a little bit confused, because I've gone a little bit slow there. Okay, so and the gradient descent for getting the good, for reducing this j of theta, or for getting the good optimal parameter, we use gradient descent algorithm. And gradient descent, what it does the same. Here is your theta, where the cost function is very, very high. This is your cost function diagram. So your cost function will be very, very high when your theta is here. When you change theta, your cost function a little bit decreases over here. Again you change, Means you're taking out the gradient of your cost function and checking if it is going down. If it is, then you just update your parameter. Let's say theta 0 was here to be theta 1 to be here 2. Then you update theta 1 to be little bit 2.1. Then your cost function decreases. Then you do the same for getting into the global optimum over here. Okay. Like this. Okay, so here's an equation for the same. So how's the equation? You just I'm doing it here. Theta z for it just means the taking of the partial derivative. J of theta equals to the 1 over m. This is your equation after deriving from cost function. This is your equation forms I equals to 1 all the way down to the m. Xi minus yi. Okay. And you just add up some kind of xj times xj. Okay, so this is your cost function. That's it. This is the taking of the partial derivative. Although it might change a little bit because everyone has a different kind of but it's similar to many of them. Okay, and then you just take out the partial derivative of your cost function j of theta, and then you update the theta by taking out the gradient. Then you update the theta like this. Theta z minus the learning rate alpha, and this is your previous theta, and this is a new theta, means updated theta, and you are taking out the partial derivative of cost function, and it's just the same. You just tweaks your parameter and checks if your cost function is decreasing or not. Okay, so we are done with the logistic regression, and I really hope that you enjoyed. So let's recap, and then we will a little bit go further into vectorization of this code. Okay, so what we have seen? We have seen hypothesis. And hypothesis is given by this segment of z, and it's a simple 1 over 1 plus e to the power minus z, and z here is theta transpose to x. Okay, and then what you do, you have a cost function for getting the accurate different model, this j of theta, which is equals to the minus 1 times yi, and the log of this is the actual phi. And for M training example, you have that, and the gradient descent, you just update you just update the theta, and theta z minus the learning rate alpha, and you just take out a partial derivative of your cost function j of theta. Okay, and the alpha here is simple. The determines the rate of learning that we have seen in linear regression. Okay, so we have seen so far, and now it's time for getting into more detail about vectorization. What's the vectorization means? So vectorization means is you are taking some amount of time, but if you want to do at once, if you want to do all the calculation at once, so here is a vectorized code for cost function. Okay, so I'm writing for cost function, which is a vectorized code. So here it is. Minus 1 over m times y transpose times the taking of the dot product between y transpose dot h plus 1 minus y t, and transpose dot log of 1 minus h. Okay, and h here is your model predicted, and y here is your ground truth. Okay, and this we had just vectorized the code little bit to get your job done. Okay, and a good way. Okay, so the gradient descent also a little bit vectorized. So here is the gradient descent theta. There's theta minus the learning, this is a partial derivative of learning rate alpha m times x transpose dot h minus y. Okay, so this is what you get after deriving your partial derivative. Okay, so this is the basic thing that you should keep in mind about when performing logistic regression. And I really hope that you have enjoyed till now. And now, if you can see, but let's summarize it a little bit so that you can get a better feel what we have seen so far. Okay, so logistic regression is a classification algorithm that will classify our example. That will give the probability after you just apply the sigmoid to the z, then you get the probability, means in between 0 and 1, you just get between 0 and 1, and then what you do, you simply take a threshold, means if it is 0, if your output is greater than 0.5, then you make it as a 1, otherwise you make it as a 0. Okay, as a convention we take 1 as a positive indication, means that the image as a cat is a positive indication, and 0 at the images are not cat, then it's a negative indication. Okay, you can take anything, but for convention you do this kind of thing. Okay, pretty much easy what I'm trying to say over here. Okay, so we have the hypothesis and we have a cost function for checking the accuracy of our model, and we have a gradient descent for getting your best optimal theta. And again, we are only learning theta over here using the gradient descent algorithm. Okay, so now I think we are done with logistic regression, and in the next section we will go over to project, which is breeze cancer detection system, and then we'll go a little bit further into understanding the support vector machine. Okay, and I really hope that you will enjoy that section also. So let's meet at the next section. Okay, so here I am on my Jupyter notebook, and you can download a Jupyter notebook by searching online how to download the Jupyter notebook, and you can follow the tutorials to download a Jupyter notebook. Okay, so what we will do, we will first start with importing the libraries, then we will load the data, we will understand what data we are working on, and then we will follow the feature engineering, then we will see how to select features, we will do exploratory data analysis like data visualization and data analysis, and we'll perform feature engineering, and then we'll see how to select the features from the correlation of the features. And you don't need to have any kind of experience with pandas, or although you can have a look if you want to in detail, but you don't have to be expert in all of these. If you are just this is just a beginner project, you can also modify it and put it on your resume and make some changes. And what you can do, you can save this model and simply deploy it over a website. Okay, so I will talk about deployment later on. But before that, let's walk through. Let me make you walk through this project. So first of all, we are importing the libraries. First, we are importing the NumPy as NP, and we are importing NP as alias, pandas as PD. PD is also alias, to short form a name. Plotly is another great visualization library, but I rarely use it. I don't want to use it for now, but in future you can use it. Plotly, just wanted to show you. Seaborn, which I'm going to use it here, and Matplotlib is also a visualization library that I'm going to use over here. And this Matplotlib inline tells you to use Matplotlib in the backend. Okay, it's kind of tells Matplotlib to plot the images in the backend. Use the Jupyter notebook as a backend. Okay, so first of all, this is the learning thing. So we will load the data from the scikit-learn library. Scikit-learn library is a famous library for machine learning. So we will load the data sets from load Boston, which is the Boston house price prediction. We'll make Boston house price prediction. So we want a data set of that. Okay, then we instantiate our load Boston, and then we take out X, which is the data. I will tell you what is X and Y over here, and Y, which is a load Boston.target. In our previous tutorials, in the introduction to machine learning, we have a talk about X and Y variables. X variables is the independent features, which we use to predict the model, and this is the Y, which is the target variable, because it's unsupervised, so we know what our output is. We know what our output label Y is. Okay, so we will be given this, and X, Y is the target variable, which will be in this case is the sales price, and this is the features. Okay, and then I call pd.data frame, and it constructs a data frame, and we give X, which is the features, and we give the name of the columns dot feature names. There is a dot attribute dot feature names to get the names of the columns automatically. Okay, and then we make one column. Here we are making one column, which is a sale price. We are making a sale price, and then we are making it Y over here. Okay, Y means the load Boston dot target. Either you can make this also like this.
either you can make this also, it's just the same. Okay, y is just a target variable, and if you just run this, now you can see this is the data frame. Here you have a crime rate per capita. That let's see the column distribution. So just first see, let me show you what we have done. These are the x variable till ls stat. These are the x variable, and this is the y variable that you use to predict. And you may think, yeah, I use 24.0, means 24.0 is the dollars is just the price of the house. No, the price of the house is given $24.0 thousand. Okay, so you can just we will see the whole thing just in a second. Okay, so this is the data frame that we constructed. Okay, so now let's take a look at the what data we are working on. So there are 506 rows, and there are 30 numeric and categorical columns, and with the median value attribute 14, which is our target variable. Here I'm given is a sale price name, but you can give as a median value. It's usually the target variable. Okay, so here is the column name, is the crime is the per capita rate, then proportion of a residential land, proportion of a non-retail business, NOx, age, what's the proportion, average number of rooms per dwelling, etc. You can rate over here. And the last, which is the favorite, the target variable, which is the median value of the, which is the sales price in this case, is at $1,000. So $24,000. Now your dream has gone out, I think so. Okay, so you can read it over here. Just you can use .DCEDESCR because it is available in the scikit-learn, so you have this kind of thing to see the information about the data set. But in real world, we will work on real world data set, so you will see how you download, how we process, etc. Okay, so let's understand a little bit more about the data. We look at the shape of the data, which is 506 rows and 14 columns, means rows and then columns. Then your .info tells us the information of your data, which is non-null values, means what are the data types, and is there any null values into that. Null means missing values into that column. Okay, and all the data types are float, what is the memory usage, etc. Okay, and let's .describe will tell you the mean of that particular column, the standard deviation, the minimum, 25% of that, 70% max count, etc. Okay, so we had seen what data we are working on. These are the features, which is the x variable, and this is the target variable, which is y, which is a supervised learning problem, as we can see over here. Okay, so let's just take a look at the null. You can use data.isNull.sum, and you can see over here that we have the 0, 0, 0 all the way, and then we can plot a pair plot, sns.pair plot, which will plot all the things which with respect to every feature. So you can see over here that we are just plotting the pair plot. You can see, but we do not get a lot of information from this pair plot because it's very kind of small, and we cannot see what data is it pointing on, etc. Okay, so we have to definitely take care of that to check more visualization that I made. Okay, just wait for a few seconds, then it will show up. Okay, so it plots, and we are unable to see this kind of thing, and we are unable to see, so it's very hard to see this. So what we do, let's take out the inferences from the sales price, which is the target variable. Let's do some analysis. So we plot a distribution plot, and you can see over here this is a little bit skewed. We are seeing over here this positive skew, but here we can add some transformation. So what's the skewness and what's some kurtosis? So here we have 1.108098 and 1.495197, which this will help us to find outliers, and outliers are those who are far away. Let's say that you are working on age. Okay, so age is 20 years old, 50 years old, but let's say 150 years. This is the outliers. Okay, these are the outliers. Okay, those who are exceptions of the data frame. Okay, so we have to take care of this, but before that, let's see some relationship with each and every column. Only I have taken 2 columns, so you can try different columns. So where there is little bit crime, there is the sale prices very high. When there is lot more crime, there is sale prices very low. Okay, and what's the age? You can also see, and you can see over here 100 years old has been sold in a smaller rate, and 20 years old has a little bit higher rate, and you can see the data visualization over here. Okay, and you can see over here that I've imported SciPy, which is again the like NumPy. I'm just taking out the norm and the skewness. So you just plot a distribution plot for seeing this kind of thing. Means for normal distribution, if you know about normal distribution, you have just plotted the normal distribution, and this is your actual this black line, and you have this blue line, so you have to transform it a little bit. So your mu, which is mean is 22.53 and sigma is 9.19. okay, so these are some, if you know about Python, you should know about these kind of stuff for formatting, etc. Okay, and this is the QQ plot, which will help us to see the quantiles, which is order values. You can search more on the internet or go on Wikipedia to learn more about this, but our main focus will be this sales price, means distribution plot. Okay, so let's run this. Let's add a log. Let's transform our sale price to a little bit more accurate. So now you can see over here that this is skewness is over. Now we have just applied a transformation over here, log 1p, and it's now good. Okay, to avoid outliers. Okay, and this quantile is also removed. Okay, so data correlation. What are correlation? First of all, correlation is the relation between features. Okay, so if it is 1, then it is positive correlated, then it's -1, very negatively correlated. You can search more on internet about it because it's not a statistics class. So you see over if the diagonal is 1, all the features are perfectly correlated. Okay, so how do we select the features which are highly correlated? Okay, the features how we select, if we have taken the absolute value of the sale price and we are taking the highly correlated feature from this statement, and there is 12 feature that we get that is highly correlated. You can choose this, but I'm not going to choose. You can either delete the rest of the columns except these 12. Okay, and let's just start with model building. So you just import train test split, and train test split simply divide your data into training and testing. Means let's say you have 80% of the data, so sorry 100%, so it will take 80% for training and 20% for testing, and you just drop because you don't want X to be sales price and Y to be the sales price. Okay, and then you test size, then the random state will tell you the means every time you run the data should not be changed. Okay, so if you run this, now let's take a look at the shape. 404 and 13 columns for training, and 402 for testing, and 401 for labels, and 102 labels. Okay, so let's start with let me make one more, little bit more so that it should be clearly visible. Okay, so you just import from scikit-learn, which is a linear regression, and you just instantiate it, and then you fit the model xtrain and ytrain, which we have used for training, and ytrain and xtrain are these are the input, and this is the y target variable. And then if you run this, now it's instantiated. Now we can make prediction. Okay, so you can see over the actual label, because we know what y test 0, because this is actual label, and this is the prediction, which is 3.36 is a predicted value from the model, and 3.21 8875 etc. is the actual value, which is little bit different from this, but it's performed very good in terms of linear regression, as we have seen so far. Okay, now if you want to check the accuracy, for checking the accuracy we have seen a cost function. You can run this and MSE, mean square error, and let's say if you want to see MSE, there is 0.035, which is good. And if you want to take the RMSE, the square root, you just np.square root, and you are getting the RMSE, so you can just print it out RMSE. Okay, and you have seen it's pretty much good. Okay, you will learn more about how we can improve this by using XGBoost, bagging, boosting, etc. later on. Okay, now we have done our full prediction project. The code will be in my GitHub, which is in the description box below. There is a lot more projects which is available in computer vision, natural language processing, which you can take a look if you want to my projects. Okay, so now I think I have not coded just now because it will take a lot of time, so I just written up and just annotated each and every line of statement. Okay, so if you have any kind of problem, you can search on internet because you have to master Google to if you have encountered any kind of problem. And in the next tutorial, we'll be talking about regularized linear models, which we'll talk about lasso and ridge, which we'll also use in this to check as a lasso and regression and a ridge regression. Okay, so let's get into the next section. Okay, so now we have talked about linear regression and we have made one project. Now it's time for getting into the regularized linear models. Okay, so if you remember that we have pointed out some problem which is overfitting, which we have pointed out earlier. Okay, so how does overfitting happen? Let's say if your model has learned too much, so let me draw one x and y plane and let me draw some data points. Okay, so these are the data points, and let's say you have a complex model which is a complex function which maps your input variable to output variable. So you just make the complex function like this, which is touching each and every line. So let's say a new example comes in and it's making a bad prediction. So you can see over here it learned too much onto the training data which are in trained, and it is very going bad. It is not generalizing well onto the new examples. Okay, so that's called overfitting. If your model working best 100% accuracy onto training and working worse on the validation accuracy, then your model is likely to fit overfitting. Okay, so how it is caused? Let's say you have a lot of features and you let's say 1,000 features, and so it will learn obviously the complex functions and then it will perform very bad. Okay, so for that we have some solution, and the solution are either you reduce some features. This is, you can do this. Another thing what you can do, you can this is the same as like this, regularization. In simple terms, regularization is just eliminating the features that are not useful. Okay, so it is just equals to this, so we give another name which is called the regularization. So let's see some of the regularization techniques. So the first one is lasso regression. So let's see a lasso regression. So what is lasso regression? Lasso regression is a regularized linear models. What we do, we just add a simple term, a simple regularization term at the end of the cost function. Let's say this term, lambda 1/2 I equals to 1 all the way down to the n theta squared I. Okay, so this is for a ridge regression. Okay, so this is for ridge regression. I will talk about lasso just after this. Okay, so just you add this at the end of the cost function. So your now new cost function will become like this: 1/m plus I equals to 1 all the way down to the m theta transpose xi. This is the model predicted minus yi squared plus your regularization term, this one, I equals to 1 all the way down to the n theta squared I. Okay, so you can do like this. Now let's understand what it's doing. It is just let's say you have some features, which is the, let's say the size of the house, let's say the price, let's say the number of fans, number of bedrooms, and a number of a grass. Okay, number of grass. So you can see whether this seems to be a less important feature. So it will simply make the theta, means the parameter feature, means the feature weight of this column to be 0. Okay, so it simply penalizes or closer and closer to 0. In ridge regression, it makes the feature weights closer and closer to 0. Okay, so what is doing, it is whatever the less important features are, is just penalizing the theta of that, and the theta is used to make prediction, and let's say theta times the number of a grass equals to prediction. So let's say it's a very small, okay, so it is just penalizes your theta. Okay, so that's ridge regression is doing, just penalizing or eliminating the, or by how it eliminating, just making theta to be equals to 0. Okay, but in ridge regression it is making closer and closer to 0. But in case of lasso regression, in case of lasso regression, I'm talking about lasso regression, it's whatever the less important feature are, it simply make the theta 0. So whatever, let's say theta times the number of a grass, so theta equals 0 times the, let's say 7, which is equals to 0. So these features is eliminated. So that's a lasso is very strict. Okay, so these two, and you use L2 norm. In that case, in ridge regression you are using L1 norm, but in lasso you are using L2 norm. Okay, just adding the regularization term, which is like this. At the end of the cost function, I equals to 1 all the way down to the end, the absolute value I and 1. Yeah, this one. Okay, so but one more thing that you can see over here, that we do not penalize our theta 0, which is the bias term, which is only the bias term. So we don't want to penalize this, so we start with I equals to 1. So we start with I equals to 1 rather than starting with I equals 0. So we do separately all the things. Okay, so what we do, we just start with the I equals to 1 all the way down to the j, which is the theta. We separately do 0. Okay, and I think it's very clear. Let me make you clear what I'm saying. I'm saying that you do let's say for theta 0, j of theta 0, you do separately this. You do separately this without the regularization term, without. Okay, but for other thetas 1 all the way down to the j, you do add the regularization term at the end of the equation, and then you separately update this also, this theta 0, and you separately update this theta 1, and you just take this as a gradient of this theta for theta 1 all the way down to j, and this gradient, the gradient of this cost function theta 0 for updating of theta 0 or getting the best theta 0. Okay, so you do not want to penalize, because only the bias term, you don't want to penalize this. Okay, so I think that is very clear to you, and again for recap, regularization is just penalizing or eliminating the less important features by making the parameter weights equals to 0. Okay, now I hope that's pretty much clear. Now I hope that is very clear, and in the next tutorial we'll be working on to last regression, logistic regression, which is the, now we'll start with classification, which will cover logistic regression as the same as a linear regression, but it's a classification, not regression. Okay, so let's I will be happy to see you in the next section. Okay, so now we'll talk about regularization, one of the favorite topic that I like to talk on. I will take around 10 to 15 minutes to complete something called as a regularization topic, and I think this is one of the most important topic in machine learning, or maybe you go to deep learning. Okay, so we'll learn about L1 norm, L1 and L2 regularization, which is often called a ridge and lasso regularization, and I hope that you will understand that. And what is a regularization? So first of all, this is the problem that should come into mind, that what is and why regularization? I think these two questions must be your first question over here. So, but before that, I'm going to highlight one something called as overfitting, and I think overfitting you all know, but just to those who forgotten about it, let's revisit that. So let's assume that you have an x and y plane, x here and y here. Okay, and here you have a data point. Okay, so you have a data point like this. Okay, and you fit it, and your model learns a lot. Your model learns a lot means your model is performing very best on the training set. Let's take an example that it performs, it is the error, the cost function over to here, means the residual error or the cost function over here will be approximately or very low to 0, and the accuracy on the training set will very high, because it tries to touch each and every point over here. Okay, and here your cost function means the difference between your predicted and the actual value, summation of I equals to 1 all around to the m will be approximately equals to 0. And if it is touching each and every point, so it's obvious that it is very best onto the training set on which it is trained, so it has learned a lot. But let's, for the sake of example, some example come over here. So what will happen? Your model will fail to generalize well onto the testing set. Okay, so that's why I'm telling that your model will fail to generalize well on testing set. So you can assume that you can say that this model is on overfitting, because you find out that your model is performing a very best on a training set, and then if you evaluate it, then you will see that your model is performing very bad. Okay, so that's the sign of overfitting. So we always wanted to reduce the overfitting. So how can we reduce our overfitting? We have something called as a regularization, and how it happens, it can happen if you have a lot of features, or your polynomial degree is very high, if you're using polynomial regression. Okay, so the major cause of problem is lots of features. Okay, so now let's see how we can remove this, how we can prevent, or how we can make our model less prone to overfitting. So we have something called as regularization. Regularization will help you to eliminate the features which are less important. So again, I'm saying it will help you to eliminate the features which are less helpful or contains less information. Okay, so it will eliminate that. So that's what the regularization is doing. It is saying that if the feature is less important, remove that. Okay, or make their respective hyperparameter to be equals to 0. Okay, make the respective hyperparameter to be equals to 0 means make the respective, not a hyperparameter, make the respective theta to be 0. So we will see how what it will do. Just for as an example, let's assume that it will help you to eliminate the features which are less helpful. Now let's see how it will do. Okay, so let's assume that you're working on some problem which is house price prediction. Okay, so you're working on house price prediction, and there you have some features. So here you have x1, so maybe the size of the house, my favorite, size of the house. Okay, then x2 is maybe your favorite, the number of fans in a house, Okay, number of x3, maybe the number of bedrooms, maybe another feature, number of maybe some fans is over, maybe ACs. Okay, air conditioners. So here we have 4 features. Okay, and let's now what we'll do, so for each feature x1, x2, x3, x4, we'll be having some parameter weights. Like theta 1 times x1 plus theta 2 times x2 plus theta 3 times x3 plus theta 4 times x4, and you can see over here that we have this is called the hypothesis function. So here these are the weights. These are the weights of these features, and we only have to learn these weights by just tweaking it. Okay, by just tweaking it. Tweaking means, let's take an example. I hope that you've already seen a linear regression, just as an overview, that your theta was this equals to 2.1, theta 0 equals to 2.1 previously, and you just take out the partial derivative of your cost function with respect to this theta, and then you update the theta. Okay, why? And just see the linear regression part, all will be very clear. Okay, So here, if you are being confused, please go to linear regression part. You will be not able to further continue. So please go back in linear regression if you're not able to understand what is theta and why it is. Okay, so this theta is a weight for the feature, and we can simply give, let's take an example that our theta 1 is equals to 2, theta 2 equals to 4, theta 3 equals to 2, okay, and theta 4 equals to 2. Okay, so we can simply multiply. So these thetas to be learned. Okay, so our user will give input. Let's take the size of the house. So 2 times size of the house may be 24 square feet plus then number of fans. So 4 times number of fans may be 4 plus number of bedrooms 2 times, because here we have theta 3 equals to 2. Let's assume that the user given 2 plus 2 times maybe number of ACs equals to 1. Okay, and this is the y hat of your model. So here you learn some weights, and usually you do the same. You have some parameter weights, which you learn by tweaking or by changing and taking a look if your model is performing best, and we just take out the partial derivative of our cost function with respect to this theta, and then see if our cost function decreasing. If it is, then we update the new theta, then we update our old theta with the new theta. Okay, so that's what we are doing over here, and I hope that you are understanding what I'm trying to say over here. So just for its intuitive examples, I hope that you understood what I'm trying to convey you over here. Okay, so let's assume that you have this. Now let's assume that this number of your model is overfitting. Okay, so what you do in regularization, you apply something called as ridge. So let's see the ridge regression, what it does. Ridge regression. Okay, so the equation for ridge regression is just add a regularization term at the end of the cost function. Okay, at the end of the cost function. So again, here we have theta 0 also. Here we have, oops, what happens? Here we have theta 0 also. Here we have theta 0 times x0, just a biased term, because an x0 is always equals to 1. Okay, so in ridge regression we add a regularization term. So here's what I mean. So j of theta equals to 1 over m plus I equals to 1 all the way down to the m, theta transpose xi minus yi squared plus, I'm saying plus, and here we have something called as learning rate, and this is just alpha. Okay, so don't assume that this is a learning rate, this is just alpha, or you can say that someone can write it as a lambda. Okay, so it is just a Greek letter, just we didn't note. Okay, so don't compare with that learning rate alpha. Do not compare. Here I will tell you what is this, what this alpha does. 1 over 2 I equals to 1 all the way down to the m, theta squared I. Okay, so here we have added a new regularization term, over here. So what is this? So this is simply what it does. It simply take the features which are less important and make that parameter weights closer and closer to 0. Okay, so what do I mean with this? So for an example, let's assume that the number of your model, using this equation, this is the L1 norm, it is the L1 norm. Okay, so let's assume, sorry, L2 norm, this is L2 norm. Okay, in ridge regression we have L2 norm, and here it's simply penalizing your theta, who is very less important. So let's assume that the number of AC or model find out that the number of AC is less important. So what it will do? So theta 4, our indicating the number of AC, the theta 4 is the weight of our number of AC. Then it will make theta 4 to be closer and closer to 0.000001. Okay, so it penalizes your theta. it penalizes your theta as it found that your number of AC is less important, so it penalizes your theta. And whenever you are multiply with penalize times the number of AC, then it will be also very means low. Okay, so that just helps you to less prone to overfitting. Okay, so it is not doing anything with your input value. It is doing, because if you multiply 0.00001 with whatever the number of feature, it will be approximately 0.00001. Okay, so like that. Okay, so what it does, it simply eliminates or penalizes your theta value by just making closer and closer to 0. Okay, so this is the L2 norm. Okay, and here we have something called as alpha, and alpha contains how harsh or how strict to be onto the certain feature. So let's assume that we have set some alpha. Obviously we don't touch alpha in scikit-learn, but here let's assume that your alpha controls the strictness. Okay, so if your alpha is large, I think so, if your alpha is large or lambda is large, some people may write this as a lambda also. Okay, so don't be confused. So if your lambda is large, then it will make it is making closer and closer to 0 now. It will make theta 4 equals to 0, fully 0. Okay, so it simply eliminates it. If you it is very strict. If you keep this, it is very strict. Okay, so it controls the strictness. What I think. Okay, what I like to remember is controls the strictness. Okay, so and here you can see that you are taking the L1 norm and you are not taking of theta 0. You are explicitly doing for theta 0, because theta 0 is your bias term and you do not want to penalize your theta 0. Okay, so we are not penalizing. We are going from theta I equals to 1 all the way down to the m. We are not going to I equals to 0. We are going to each and every theta. Okay, so we are not going to theta 0. So we explicitly do for theta 0, and we explicitly tweak our theta, or we take out the derivative for theta explicitly. Okay, because we don't want to penalize our bias. It's our bias term. Okay, so this is the rigid regression. Okay, so we have something called as a lasso regression. Lasso regression means lasso regression is it uses L1 norm instead of L2 norm. It's just the same. It also penalizes the theta value, but what it will do, I will tell you. Okay, so theta 0 equals to whatever your cost function will be. I'm just putting 1, 2, 3 plus, now I'm writing the regularization term, I equals to 1 all the way down to the m. You are not penalizing again theta 0. The norm of theta I. Okay, so this is what you, and here you are taking the L1 norm. Okay, so taking the norm, or you're taking the norm of your theta. Okay, so here you are applying the L1 norm. So what it does, if lasso regression is very strict, just assume it is very strict, whatever feature he finds, whatever I'm taking the gender as a he, okay, or whatever this lasso regression finds, whatever feature that less important he finds, he will directly make that theta 4 to 0. So here we assume, here we taken theta 4 equals to closer and closer to now. Then in lasso it will take it directly to 0. Okay, so it is very harsh. So both have specific use cases. Okay, so these are this is called the L1 norm, and this is called the L2 norm. Okay, so here we have studied about a regularization in detail, and I hope that you understood very clearly, and we have talked a lot. And there is one more, which is elastic net, which you don't need to worry about now. It's very kind of a just combination of both of them, but it's not used in the industry as we use this L1 and L2 norm. Okay, so thank you for seeing this video about regularization, and you can head over to the next section to learn more about machine learning and completing this course. Okay, so thank you for seeing this video. Head over to the next section.
Okay, so now we will talk about support vector machine in detail, so that you could be more powerful in machine learning, or you will be having a powerful algorithm in your toolkit of machine learning. So support vector machine is a supervised learning algorithm, which is both for classification and regression. We have seen logistic regression, and logistic regression is for classification,
And linear regression is for regression. So support vector machine is for both, which is classification, and one more, which is regression task. Okay, so regression task. So support vector machine can be used in classification, either your output in discrete value, or it can be used in continuous value. Okay, so I will dive into the support vector machine, but before that, let me tell you what we are going to study in this section. So we'll start with the introduction of support vector machine, then we'll go further into what SVM do, and then we'll talk about linear, hard margin, then we will go further into non-linear classification, and then we'll talk about empirical risk minimization, and then semi-supervised transductive SVM, and then we will talk about SVR, which is support vector regression. Okay, and in the next section we will do one project, which is stock price prediction project. Okay, so what is SVM? What actually SVM does? It's simply just what is like this. So let me draw one X and Y plane. So here is my X and Y plane. I hope that's beautiful. So here is my X and Y plane, and let me make a linear data. Okay, so here we have the one data point, and another data point is over here. Okay, so we have like this, and then we have this data. Okay, so let's assume that you are working on CAT and a non-CAT recognition system. Okay, so you are working on CAT and non-CAT recognition system. So what actually SVM does is, here you can see over, let's assume that white color is for CAT images, means the labels are CAT, and blue color let's take as a non-CAT. Okay, so these are data, and what SVM does, it constructs a hyperplane. It's construct a hyperplane like this. It's construct a hyperplane like this. Okay, and now whatever new point come on or beyond here, then this example will be CAT. Otherwise, if something come here, then it will be non-CAT. Okay, so this is what SVM does. But this is not the full procedure. I will tell you. But here what it does, it simply construct a hyperplane and two parallel hyperplane, and two parallel hyperplane with this margin. Okay, these are called the margin. So it always tries to maximize that margin. So it may sound a little bit kind of confusing. So let's draw it again. Let me show you once more time what actually it does. Okay. So here is a white examples, and here is your blue examples. Is it non-CAT and not CAT? So what it does is construct a hyperplane and a two parallel hyperplane over here, two parallel hyperplane like this. Okay, so, and this is called the margin, and SVM always tries to maximize this margin, keeping away the nearest data point far away from the hyperplane. What I've said is very crucial to listen what I'm saying. I'm saying that what SVM does, it simply constructs a hyperplane and a two parallel hyperplane that separates the data point and at a maximum margin. Okay, so it always wants to, SVM always wants to maximize that margin in such a way, so that the nearest data point, let's say xi, is far away from the hyperplane, this hyperplane. Okay, is far away from the hyperplane, so that it will be easily, so that whatever comes here, then it will classify as a non-CAT. Whatever comes here or here, it will be classified as a CAT. Okay, and what I'm saying, that the nearest data point is should be the far away from the hyperplane here. Okay, so it would be here. So these are called the support vectors, who are the nearest data point from the hyperplane. Okay, and that is supported by these are the support vectors which supports this parallel hyperplane to separate this. Okay, again, it may sound a little bit confusing, so let's revisit this again in a more detailed way. So let's say, let's take another example, that we are building a person has a cancer or a non-cancer, I think malignant, let's say a non-cancer. Okay, so you build X and Y plane, so let's build one X and Y plane, and then you put this blue examples which indicates as a cancer, and this white example which indicates as a non-cancer. Okay, so what SVM does, simply construct a hyperplane like this. Oops. It simply constructs a hyperplane and a two hyperplane like this, and a two hyperplane, and this is called the margin, and it always tries to maximize this margin so that in such a way that the nearest data point is far away from the main hyperplane. Okay, so you can see over here that this is the nearest data point is far away, so these are called the support vectors. These are called the support vectors. Okay, pretty much easy. Now I think that is much clear. We have taken 3 examples. Now I think this is much clear. Okay, so it may sound to you like it's like a linear regression. You have a linear data and you're just fitting a straight line with 2 hyperplanes. What does it mean? Yeah, it obviously means like linear regression. But if you come to the more in detail, the data are not linear. Okay, the data are never linear. So there are 2 kinds of SVM there. The first kind of is hard margin classification and soft margin classification. Okay, so let's visit hard margin first, and then we'll revisit soft margin. Okay, so here you can see over here that this is just like linear regression, but wait for a few seconds, few minutes, then you will understand why it is not like linear regression. Although it seems like that you have simply construct a straight line, but equation and is used for classification is quite different. Okay, so it's called the linear SVM. The what we have seen is called the linear SVM, where we are constructing a simple hyperplane and separating 2 data points. Okay, so what are hard margin? Hard margin means that we are not allowing any data point to come into that margin. Okay, that's called the violating the hard margin. So sorry, violating the margin. So we are not allowing any data point to violate that margin. So in that way we end up being an overfitting, or in that way we very much our model is being started overfitted. So let's see what I'm trying to say over here. So let's construct a let's construct one X and Y plane again. So let me construct one X and Y plane. Oops. Here is my X and Y plane, and let's just draw 2 data point. Again, let me draw 2 data point like this. Okay, and let's draw a white data point like this. Okay, so and now what SVM does, simply construct a straight line with 2 hyperplanes. Okay, with this hyperplane. Okay, so in hard margin we are not allowing any data point that you can see over it comes under in, so we simply kind of do like this. We simply kind of do means we simply minimize this margin like this. So we are doing like this. Or it is very strict. Hard margin is very strict. Hard margin is very strict. The reason I'm saying is very strict because it just does not allow any data point to come into that margin. But in soft margin, we allow some data points to violate that margin to avoid overfitting. Okay, so that's what the soft margin and hard margin means. Hard margin means we are not allowing any data point to come into that margin, and soft margin means we are allowing a little bit of data point to come into that between. And the width is the width of the margin. This is the width of the margin. Is adjusted by C. Okay, so if C is very large, then your width will be very small like this. Okay, let's say C equals to 0. This is the margin, my margin. So this is my margin. So let's say your C 100. C equals to 100. So your margin will be very the width of the margin is
kind of a low, means it's very slow, kind of it's very small. But if c equals to 1, then the width of the margin will be very, very large. Okay, like this. So it's kind of a very awkward thing that you can see over here, but that's what the convention said. Okay, so we have seen this kind of thing, and maybe you will see sometimes c to be named as a lambda. Okay, it's just the same, lambda and c are the same, just as convention we give it a c as a name. Okay, so let's just get now you got the overview of this hard margin and SVM. So we have seen a lot more things. Now it's time for getting into the little bit of mathematics, which is how do we construct that hyperplane. In linear regression, we are just making the straight line, and this is theta transpose x. But this was our favorite equations, like this, theta 0 times x 0. And in logistic regression, we are just doing the sigmoid of z. So these are our hypotheses. So from this equation, we were making our straight line, or maybe the sigmoid. So what happens in the case of a supported machine? Our hyperplane is defined by W transpose x minus b equals to 0. This is the condition that our hyperplane should satisfy. Okay. So what is this? This W is our parameter weight. In this in linear regression, we have seen is theta, and b is our biased term, which is in case of linear and logistic, which is theta 0. Okay, so we have just given a new name, which is W and B. Okay, and so we have made a W transpose x minus B, and this is our hyperplane that we have made as W and B are the parameter weights. Okay, so we have just given a new name, and transpose, you all know in linear algebra, and this is W is a parameter vector. Okay, so let's define some constraints for hard margin. So let's define some constraints for hard margin, how hard margin make predictions. Okay, so whatever the output of your model minus W transpose x minus b is greater than or equals to 1, then anything on or above this margin will be regarded as 1. In this case, it will be capped. Okay, why I'm saying like this is, let's say you have this straight line, and you have this, and you have the data point, and these two parallel lines, and again here you have. So whatever on this margin or above this margin is regarded as 1, means the positive attention, so it is regarded as a cap, as you know. Okay, and whatever below this is regarded as a 0. Okay, as a non-cap. Okay, so let's write the equation for that, and it's quite easy. It's quite rememberable. Like W transpose x minus b, whatever on or beyond this margin will be regarded as 1. Whatever below this margin will be regarded as a 0. Okay, as a negative attention. So that is the hard margin constraints, and that's how we make predictions onto support vector machine. Okay. Pretty much clear what I'm trying to say over here. Okay, so now let's dive into some little bit more further into math, is how actually it is being constructed like this. So let's say you had made a straight line, and this margin, you can see over here, this margin is written by this hyperplane. The main hyperplane is written by W transpose x minus b, and this margin is equals to the 2 over the norm of W. So to maximize this margin, we wanted to minimize this margin, minimize to W. Okay, if we want to maximize this margin, because SVM always has to maximize this margin. To maximize this margin, we have to minimize this norm of W, and this margin is written by 2 over the norm of W. Okay, and so as we have taken, the SVM always tries to maximize, so that is written by the 2 over norm of W, and to maximize that, we want to minimize the norm of W. So we can write an objective function, we can write an objective problem, like this. The distance between two hyperplanes, the distance between to hyperplane is written by 2 over the norm of W. So to maximize that margin, we want to minimize the norm of W with subject to yi W transpose xi minus b greater than or equals to 1. So what I have said. So let's understand this equation a little bit more further. What I have written over here. So for maximum, this is the minimizing, means we want to minimize to maximize that margin with respect to yi, which is your ground truth, means actual label, and this is your moral predicted value. And you can see over here, if it is on or beyond this, it will be 1, otherwise it will be 0. So if yi is equals to your moral predicted value, then your cost function will be 0, then your loss function will be 0. Otherwise, if it is not equals to y, then your loss function will be very, very high. So you want to minimize this norm of W to get the good predictions. Okay, so we have started this, and I really hope that you had understood the concept that I explained to you, and we can write our cost function in a hinge loss. For I'm talking about some soft margin, so we can write our soft margin like this. So we can write the loss function, the cost function, the loss function. We can write our loss function like this: 1 over n plus, I'm going to each and every training examples, max of 0, 1 minus y W transpose xi minus b plus regularization plus lambda over times the norm of W squared. Okay, so this is quite confusing a little bit, but let me try to explain you in more detailed way. So you can see we are going to each and every training example, but take note of max, and this is the hinge loss. If you can see, this is called the hinge loss. If you want to get into more detail about the hinge loss, you can have some Wikipedia pages for knowing about hinge loss. Okay, and this is your moral predicted value yi, and this is your ground truth yi, and this is your moral predicted value, and this is the lambda times. You can write C also. You can write C also because it helps you to adjust the width of that margin. So that's why it is a very, very important hyperparameter. Okay, and times the norm of W squared. Okay. Okay, so we are done with a kind of a linear classifier. We are linear SVM, means linear classification. So we have made our good loss function. So we have made a prediction function, and now it's okay. We want to minimize this norm of W to get the good predictions. Okay. Okay. So we have seen only the linear SVM. So let me formulate one example, which is like this. Let me make one again x and y plane. I'm making too much x and y plane. It's best to have this kind of things. Okay, so let me make one non-linear classification like this. Okay, so you have this kind of data and this kind of data, and let me make these white examples are cat images, and these white examples are non-cat images. So now if you want to make the straight line, you will be not able to do that. Means you're not able to kind of classify it. So it's very bad. So what you have to do, you have to make a non-linear, you have to do the non-linear classification like this. Now it will be okay. Now it will be okay. So SVM also is very kind of powerful in non-linear classification with something called as kernel trick. It's something called as kernel trick. So we will elaborate kernel trick in detail. So let's start with kernel trick. So what we do in kernel trick? So let me write an algorithm. So what you do, you write an algorithm in terms of x. You write the inner product. Let me write. You write an algorithm. You write an algorithm in terms of the inner product of x and z. And these x and z are two data points. So what you do, let me tell you what we do in non-linear classification. We take our data x, and we transform our data to some more. Let's say we have one-dimensional data to a two-dimensional data in non-linear classification. Okay, so we transform our data from one-dimensional to two-dimensional, like this. Okay, so we write an algorithm in the form of x and z are the data points. So simply in kernel trick, we transform our data from one-dimensional to higher dimensional space. So you will get to know what we are doing. So let me write the steps. So after we have written our algorithm in terms of the inner product of x and z, now what we do, we map our input this x. We map our input x to the phi of x, okay, to the phi of x. So we are just, I will tell you what this function is. Okay, so we write our function, we map our x to the phi of x. I will tell you what we do in this case. So we find a way to map our we find a function. So we map our x to the phi of x. So we write a function, or we find a way. So we find the x to the some phi of x, and it will transform your one-dimensional data to the maybe any kind of your data to be the high dimensional. Okay, so you write a function at k which transform a data the phi of x transpose the times the phi of z. Okay, so let's see what it does with the help of an example, and then what we do, we replace our x and z with our transform data, which is phi of x, and z to be the phi of z. Okay, so this is what we do. So let's see somehow what it does and what way it does. So we write the kernel functions are, one of the famous kernel is RBF kernel, that will transform your data x and z to the high dimensional space. So the kernel function is written by the RBF kernel function written by k of x comma z exponent of minus norm of x minus z squared over 2 over the sigma squared. Okay, and the x and z are the data points. Okay, great. And some more kernels are, which is polynomial, homogeneous, polynomial, inhomogeneous, which you can search on internet, but the most famous one is RBF kernel, which is widely used in the industry. Okay, so we have seen various kind of things and about kernel trick, how we do the nonlinear, the transform data, you're able to do the nonlinear classification. So here are some, we will discuss one primal problem which will help us to state our optimization objective, and then we will see the subgradient. Okay, so why I'm talking about primal problem, it will help you to formalize your objective function. So it will help you to formalize your objective function. So it's just the same, just as written, we write that. So for each I be the member of 1, 2, all the way around to the n, we introduce a new variable zeta. Where zeta I where is equals to the max of 0, 1 minus yi. So we introduce a new variable zeta I 0, 1 minus yi. Okay, and then in that we write w transpose x minus b. Okay, so this is just a hinge loss where we introduce a new variable. That hinge loss is storing. Okay, try to see what I'm trying to say you here. Okay, so then we write our function like this. You want to minimize 1 over n, I equals to 1 all the way down to the n, zeta I plus the regularization term c, the norm of w squared. Okay, with respect to or subject to yi w transpose x minus b greater than or equal to 1 minus the zeta I time is just where zeta I is greater than or equals to b for all I. Okay, so we have just formulated one problem. It is just equal to the hinge loss that we have seen. We want to minimize the objective function that we have seen so far. It's just equal to that. So we have formulated in such a way that you can use this. Okay, so we have an objective function which is our cost function. Now we can something called as subgradient, descent, and what we do, we make a convex function f of w and b. We take out the subgradient of our function. We take out the subgradient of our cost function, and then we update our parameter w and b. Okay, and that's the sub as a gradient descent what we are doing. Okay, so it's little bit different than gradient descent. Here we are taking the subgradient of our cost function. Okay, so this is what we are doing. This is called the primal problem, and then we take out the subgradient of that primal problem. Okay, pretty much easy what I'm trying to say here. Okay, so one more thing that is very popular among beginners or learning theory, something known as empirical risk minimization. What do you mean by empirical risk minimization? Given the input x1, x2, all the way down to the xn, you want to and given y1 all the way down to the yn, you want your output yn plus 1, given xn plus 1. So it's just the same. You give a function x and you want your output y. Okay, and the loss and the getting the error should be minimized. Means the risk should be minimized. So that's the empirical risk minimization, which we have already seen. So we just have to know the definition. What is okay. So as we have talked about nonlinear and linear, now it's time for getting into these support vector regression. I'm just going to give you the equations. Okay, it is kind of quite easy. You want to minimize your 1/2, the norm of w is squared. You want to minimize this to get your output with respect to or subject to the yi, the absolute value of yi, minus the inner product of w and xi times p times b, and it should be greater than or equals to the sum epsilon, and epsilon be the smallest positive integer. Okay, so just to be comfortable into that, so I hope that is quite clear, and this is for regression task. Okay, and we will see the implementation in our next section. So I hope that you really enjoy this tutorial, this section, and we will be carrying out this more into detail. Now, if we have gone too much into math, but if you haven't understood anyone, please feel free to put your comment in the comment box. I'll be very happy to take your comment and provide you answers over there. I will be taking a look at your questions, and we'll be answering soon at that point. Just put the timestamp where you're commenting, okay, so that I could know where you have a problem. Okay, so I think that we have gone in too much detail. If you haven't understood primal problem, subgradient, don't worry. It is not required for a beginner machine learning. So if you learn too much in machine learning and gone into deep learning, now you can come back to this primal problem to understand what I'm saying. But it's quite easy to understand, and the kernel trick, what I've said, etc. Okay, so thank you for seeing this video. Thank you for seeing this section. I'll be catching up you in the next section. Till then, you can do the programming assignment. Okay, I'll be catching up your next section. We'll be making one project which is stock price predictor. Okay, thank you.
So now we will make a stock price predictor, which is our end-to-end machine learning project. And here's the demo, and you can see over here that I have to you can just remove the I will show you where I have taken all those things. I'm not a web developer, but I had made a good front end of this, and also I made a back end using Flask. Okay, so we will code as I made a stock price predictor, and I will show you how you can build the same website like me, and you can also make beautify if you are a web developer. Okay, so here's my Jupyter notebook, and here first of all I'm going to download the data from Yahoo Finance, and you can simply pip install Y Finance. I've already installed that. You can install that. So you just want to import first of all the basic libraries. Let me do that. So first of all you want to import the basic libraries like this. First of all I will import NumPy as NP, then I will import Pandas as PD, and then I will import matplotlib, and I will import matplotlib.pyplot as PLT. Then with that I'm going to import the cbar, because I'm going to use cbar now, in this case as a visualization library. So NumPy is a scientific library, Pandas is a working with the data, the Seaborn is a visualization library, and Matplotlib is also a visualization library. Okay. Oh, and one more thing that I want to import is for my data, which is import yfinance as yf. Okay, as yf, and yf is just allies given to that. Okay, so let me run this out. And yeah, I can too add, this is optional, but I can too add over here like this, matplotlib inline, matplotlib inline. Okay, now it should work fine. Okay, so we had done with importation of our all the libraries, and now it's time for getting into a little bit more detail about the data, how we can load our data. So first of all, I just going to use I just want to in this project I will make a stock price predictor of natural gas. Okay, and you can do any of like gold, silver. Just head over to the Yahoo Finance, just head over to the Yahoo Finance, and just head over to that and just to search whatever the, let's say I want to go for gold. So if you go over gold, then you will see over here that you have a GC equals to F, which is the code of that. Okay, so you just copy the code, and here's just I will just show you what you can do. First of all, I will take input, which is enter the code of the stock, to download, enter the code of the stock to download. Okay, now it will take an input. Now I will just make a variable. Yf.download, and it will take the code from the stocks. Okay, and it will download from let's say 2008. It will download from 2008 in January to 1 till it will download till 2021 till 0, let's say 2, let's say 1, and till 18. Okay, so this is the favorite thing, and now what you can do, we can simply do this kind of thing, and let me run this, and it's asked the code of the stock. Okay, so you just give the code of the stock. So let me give the natural gas equals to F. This is the code. So it will download a stock like this, and then it will simply tell you the data how it looks. Okay, now if you can see over here that you have open, high, low, close, adjacent, close, and volume. Okay, so one more thing that you can do, you can write auto adjust equals to true. What it does is to adjust your all of the kind of data frame, and then you can see over here like this. Okay, so that's what it's doing till now. Okay, so we are done with this. Now it's time for getting into a little bit more detail about now we have loaded the data. Now let's take a look at the shape of the data like that. So data.shape, and it will tell us that we have a total of 3,256 training examples and 5 columns, including date 1, 2, 3, 4, 3 to 4, 5. We have 5 columns, and information about the data. You can take a look. We have a non-null values. We have this, we have that. What's the data type? You can also take a look at the mean, standard deviation, maximum, minimum of all those stuff. So let me do that. Okay, so you just see this, and now you can see that you have all of the count, the minimum, mean, standard deviation, minimum, 25%, and etc. Okay, now if you wanted to take a look at now we are done with data exploration. Now let's little bit go further into how it because stock price prediction is very non-linear. Okay, but one thing that I want to mention over here, they do not use it for personal purposes. It's only for educational purposes. Okay, only for educational purposes. The reason why it's very non-linear, and you can't you can't depend on your algorithm to simply predict the output. Okay, it may give you the wrong output. I don't know about this, very non-linear, so be sure to do not use it just for educational purposes. You're not working company, you're just making a simple project so that you could get a concept of how you implement, how the process whole looks like. Okay, so don't implement by yourself, use in yourself, and do not make a website like that. Do not, it is only for educational purposes. Okay, now if you're done with this, now we can analyze our data. Now if you want to analyze our data, you can write this close.plot. You can just plot it out, and now it will look like this. Oops. You can fix size. Let's say I just want to make it 10:7, and we have this, and here our target variable is close. Okay, our target variable is close, and means it will just tell you the direction of the stock. Let's say if the close is very high, then your direction of a stock is very high, means the close will very high. So here's very nonlinear. So it just starts in 2008 in very low way and gets up in 2009, then gone drastically down in 2010, and then kind of that. So you can see the non-linearity like this. So it's very, very non-linear, and it's not you can't depend on this algorithm or this predictor to predict your output in a good way. Okay, so now I think that we are done with everything. Now let me see what I have to do. Okay, now let's take a look at this, how we can plot the distribution plot. What's the distribution plot of our open, then what's the distribution plot of our close. Okay, so it will give us a more feel how we are proceeding with our data, or it will help us to choose the algorithm. Okay, so here's the thing that I wanted to mention. So first of all, I'm going to use Seaborn, and I'm going to use Seaborn, and then here I'm going to name as data. I just want to name as data, and I'm going to put over here this open, let's say close. Okay, so we will see if this is non-linear, etc., to take a little bit more feel. Okay, so you can see over here it's a little bit it's a non-normally distributed. Okay, so you can apply a log transformation that's called feature engineering, but that does not work well in this case. So we should leave like this, and then we will take a look at this plot, and then if you wanted to take a look at the open, then you will again see it's again normally distributed. Now we can do the same for other things to get the feel of what you are doing. Let's say we have done for high. Let's say we are done for high. And if you take a look at the high, it's also like this, a sweet. Okay, so we are done. We are done with. You can play with the data visualization and take out the inferences about the data inferences. Okay, now we have understood the data. What we have understood. Okay, let's write the conclusion. What we have understood till now. So we have understood the first and foremost is the shape of the data. And then we have understood how our data is distributed, how our data is distributed. Then we have understood how our it's very, very non-linear. It's very, very non-linear. Okay, so you cannot use for own purpose. Maybe you can use deep learning architectures like LSTM to get the direction of your stocks. And let's say if you maybe the 95% that works correct, or maybe the 80% works correct, or maybe 75 works correct. So you can just now do not use linear regression or any kind of things to make your own use, but definitely in future let's see what the researchers comes with for stock price predictor, because stock price prediction is also a competitive project to work on because it's very, very non-linear. Okay, so we are done with this, and now it's time for, we have studied how much algorithm, we have studied linear, then we have studied logistic, then we have studied some regularized linear models, then we have studied support vector machine, then we have studied principal common analysis, which we have not studied, so we will study principal common analysis, and then furthermore. Okay, so we will use support vector machine, but we will see that linear regression and regularized linear models works best in this case, and we will go with or saving the model of regularized linear model. Okay, so let's start with linear regression, but before that let's split our data into X and Y and then the training and testing set. So here I am, I'm doing X by convention, so I'm just going to make it like this, and our X variable will be all the except close, so I'm just going to remove this, and then in X is number 1, and then Y equals to data, then Y equals to data dot drop. No, it says we will not drop it, we will just simply keep it close. Okay, now if we are done with this, now X and Y data dot drop close X and Y. Now we are done. Now what we can do, we can simply import more kind of a model selection, which is train test split. We will import one thing which is train test split, which let's say you want to split your data. Let's say you have 100% of the data, so you will split your data 80% for training and 20% for testing to validate your model. Okay, so here I'm doing what you can see over here. We have a X train, X test, and Y train, Y test. Okay, so this is you can make the variable, and all the training, and means the labels of X train will be in Y train and label of X test will be in Y test, like this. Okay, now you have just give X and Y and just give the size of the test set, which is, let's say, give the 20%, means you just want to use 20% of your whole data for testing. Then you want to just random state, and you may think here what's random state does. It's simply let's say if you run it one more time, then your data will not be changed. Your shuffle, because shuffles also, so your data will be not changed. Okay, so we will take a look at the shapes of that so that we can get a more feel what we are doing, so you could understand to whom we are working with. Let me just copy and paste it over here, and just going to make it like this, and then I'm just going to make it Y train and this one Y test. Okay, and just going to make it a little bit more detailed. Okay, when you run this, you can see over here that you have a 2,604 and 4 columns, and the 5th column is 2000 the labels of Y. Okay, so that's the thing. And now what we can do, we can go further, and we have taken the close as our target variable, which will tell us the direction of our stocks. Okay, so now we are done with splitting. Now it's time for getting into a little bit more depth is modeling part. Means we are going to, first of all, I'm going to import the linear regression, because everyone thinks linear regression is very bad, but let me tell you, it's very powerful algorithm when it comes to linearity. But here we don't have a linearity, but still it works best when you apply a polynomial, etc. regression. Okay, but let's use a linear regression, and you can see over here that this is a regression problem and supervised learning problem, so we cannot use logistic. It will be very, very bad for us. Okay, so I'm going to instantiate, and I'm just going to call lr.fit, and I'm just going to give X train and the labels Y train, which is the labels of X train. Okay, the predict one means I'm going to use that LR, which is train model, to predict my X test. Okay, now if I run this, now if you see the predicted output, you can see over here that the let's see the first training example. So you can see over here, oops, this Y test now. So you can see over 2.918, and the predicted is 2.90, and the actual value is 2.918. Okay, see the things that is over here. This it's quite very, very good, because you can see over that's quite working very, very good. And yeah, linear regression works out best, but it may happen that may overfit your data. But let's see, let's calculate some matrix. So we are going to use some matrix which is MAE. We are going to use MAE, which is MSE, which is a mean square error, which we have talked about the cost function for linear regression. Then we are going to use RMSE, and simply it does simply the square root of mean square error. And then what you do, and then we will calculate the R2 square. Okay, and you can see if you want to get into mathematically, we'll talk about some matrix later on, but the best output of R2, if your model giving output R2 equals to 1.0, then you have a very good model, and it's a good model if it's giving good. Okay, so we'll see how much our R2, etc. So I will write one helper function like this. We'll write one helper function, calculate matrices. I'll just write a matrix, and then it simply takes the actual value, which is a ground truth, and it simply takes the predicted value of your model to calculate. And then first of all, I'm going to calculate the MSE, and it's just first of all I have to import, because you can also make your own function, but it's better to use vectorized or scikit-learn because it's already provided to you. But you know, it's very kind of easy if you wanted to define MSE. So you just define MSE and just take the sum of every data point and the residuals, and then just square them up, and then like that. You can do that. We have already, I think you have implemented programming assignments. Okay, so you can just make it import, let's say, oops, I just want to import the matrix, and I'm going to import MSE, mean square error. Obviously we do have mean absolute error, which you can also use, but for now I'm going to use these two. But by the way, we don't have RMSE. We have to code RMSE by ourselves. Okay, we only have R2 squared. So first of all, let's do this kind of thing, means mean square error, giving the our parameters ytest and ypred, and then RMSE. And you may think here how you can calculate the root mean square error. Just write np.square root is just taking the square root of MSE. Okay, that's easy. So R2 score, which is R2 scores, I'm just going to write is doing a spelling wrong, because maybe it will cause some error if you have a reserved keyword or like that's function. Okay, so you have R2 square, and then score. Now you just give ytest. Now you just give ytest. Sorry, yeah, ytest and ypred. Okay, and these are ytest and ypred are just. Let me write that. What is this? So ytest is your ground truth, is your ground truth, and ypred is your model predicted value. Okay, model predicted value. Oops, I think that I'm doing wrong. You can see the spelling. Okay, so we are now what I will do, I'll just print it out MSE, then I will print RMSE, then I will print RMSE, then I will print R2. Okay, R2 scores. Okay, in this I'm just gonna do MSE, just going to make it MSE like this, and here also I'm going to make it RMSE. Okay, and here also I'm going to make R2 square, R2 score, sorry, score, it's score. Okay, now I think that it should work. Now we are done. Now if you wanted to, now we are done with helper function. Now if you want to calculate the matrix, so we will just calculate for a linear regression. So we will just give a ytest, which is our ground truth, which I have made while spitting out data. Now we'll make a y prediction, and sorry, it's a prediction one that we have made in linear regression predicted. Okay, so you can see the MSE is equals to 0, means approximately equals to 0 is quite good, because in cost function your cost function should be very approximately equals to 0. Your root mean square is also, and your R2 is 0.999, means it's approximately equals to 1.0. Okay, so it's quite good. Linear regression performs quite good. Okay, now let's let me go further into some regularized linear models like Ridge and Lasso. So let's use that from sklearn.model, sorry, linear model. I'm just going to import Lasso. And if you may know about this Lasso and Ridge. Lasso, what it does, simply eliminates the less important features. And Ridge is just penalizes your less important features. Okay, so now let's make the two of them. So let's say LA as a lasso. So I'm just going to fit it over like this. It's a short form giving the X train and Y train. is a short form for doing that, and then I will do for the same for a ridge. I'm just going to go for the ridge, and it just fits the same thing. And oops, I should give it RA, I think RI, LAP. I'll just go LAP is the lasso predicted value, and then I'm LA X test. Okay, and here also I'm just going to make RIP equals to RI dot predict, and I'm just going to give X test. Let's run this. Now we are done. Now if you want to take a look, let's first take a look at the lasso, what lasso performs. First of all, we are going to give the ground truth, which is Y test, and then we will going to give the LAP. Now it's quite not good. It's 0. It's quite not good because simply it's very strict. It simply eliminates. So, but it's your with lasso, your model is less prone to overfitting. But here you can see, if I take a look at the ridge, it's quite for now it's quite good, because it is also a regularization. Now it's quite similar to linear regression, but this is less prone to overfitting. Okay, it's less prone to overfitting, so we are going to use ridge regression to save our model and build a website onto this. Okay, so one more thing that I want to mention over here, that we can use support vector machine, support vector regression for this task. So let's see how we can make this kind of thing. So let me SVM. So you can just, I think that support vector machine will not work well, but it should work well if you have a lot of features like index volatility, and then we have a different features which contain different importance. Okay. So I'm just going to import, and here you can obviously will not use it, but here you will learn how to do the fine tuning of any of the model using grid search CV. Okay, so dot model selection, and just going to import the grid search CV. Okay, first of all I'm going to instantiate SVR, and then I'm just going to make it params, and then I'm going to make it params, and then here I'm going to make it C to be maybe, and C is just a lambda which will tell us the width of your margin. So I'm just going to copy it out as I'm going to write it from there. I've already written over there. It's just I'm going to write it to minimize the length of the video. Okay, so it's just like this, and I'm taking C as to use these values and check how is model performing with different values, and kernel will be obviously the RBF kernel, because it's very kind of non-linear. Okay, now what we'll do, we will just make this, and then I will call my grid search CV, and then I'll give my params. I'm just gonna to give my params and SVR. First of all, SVR obviously. SVR, and then I'm going to give it param grid, and then I'm just going to ref it equals to true, and just ref it will tell you means the warnings. You can see the documentation, verbose equals to 3. Okay, messages done. Now if you're gonna to run it, let's fit now we will fit grid onto our training to check different values. Y train. Okay, now let's run this. It will take a little bit of time, but yeah, I'm just going to code it further. It will take a little bit amount of time. It is checking for each and every this 0.1, 0.2, etc., and checking the score, and whatever works best, it just will give out. Okay, just want to make it small. Okay, now let's wait for a few seconds, and I think this will end up being in a few seconds. In the meanwhile, I'm just going to just copy it out these things, because the parameter which we're going to get is like this: the C equals to 10 and gamma equals to 0.1 and kernel equals to RBF. And if you run this, if you will be left with a very good matrices, but it is very bad. I think so. This SVR performing is very bad. Because of that, we don't have a lot of features overhead, and SVR is not able to learn the model actually. But regularized linear models are more powerful in here. Okay, pretty much easy what I'm trying to say you here. Okay, now I'm going to just to see this, how much it runs. Still running. It's just checking for each and every this will take 1.8 seconds more to, I think it's 1.9 seconds. It's just taking a little bit of on time, but I'm just going to wait for a few seconds, and you can see over here that it's trying for each and every value, gamma, then C, then this, then that. Okay, so we will just wait, and then I will let's come back. I think we will just code it further, because we will just code it further, import joblib, and here we will import joblib to save our model, because we are going to use regularized linear models. Okay, so model joblib.dump, I'll just dumps, and just going to save its model.pkl. Okay, and then I will simply if I want to load my model, equals to joblib.load. I'm just going to, if you want to load your model, you can just write it down, and you can just make it model.pkl. Okay, that's what we are going to do over here. And now I think that's done. Now if you want to like this, and now if you want to make it like this, now we are done with this kind of thing. Now if you run this this support vector regression, and now if you run this, now if the dumps is not there, particularly very good. Okay, so we are done with this. Now let's see the in folder where we have the pkl file, and we can use this model to make predictions. Okay, so we can use this model to make predictions. So let's keep making predictions with this. So let me go to my let me go to my one of the MLO1 and then stock price predictor, and here I'm going to open with code. Okay, I do have made, which I will just copy. If I want to save my time, I will just copy and paste over there to save my time, so that it would be more perfect if I just copy the prediction out of HTML, because it's just simple HTML blocks. Okay, just going to cut it down, because I don't think that it should require further. It's just active. Let me cut it down. Okay, so now I think that we are onto this. Now what I can do, I can just make a app.py, and here first of all I'm going to, I think that all are able to see. Yeah. So from Flask, I'm just going to import Flask, and then I'm going to import the render template. And if you don't know what Flask, don't worry, it's quite easy to understand. I will walk through each and every process, but I don't know why it's not working, but it's okay if it's not working. It's my VS Code bugs a lot. I don't know why, but yeah, I will just keep trying it out. Let me again open with code. Let's again open with code, and then let's see what I can do over here. That we are just imported the Flask till now, and render template. Now I just instantiate my model like this. Flask name. Oops, it's just, I think name. I think it's correct. Yeah. So now I'm just to make a route, app.route, and it's just this simple home page to validate our server is working. Return a render template. I just want to take a render template from the index.html, and you may think, hey, you haven't made index.html, so let's make that. This I have not made, just I'm going to make it over here. So Flask looks for HTML files into the templates folder, so just make one templates folder over here. Okay, just make it, and then one more folder you have to make for your images, which is static folder. Okay, static, and all your images will be here. Now you can also make from here just to templates like this. Now just make a new file, which is index.html. Okay, now after making index.html, you can just type this down like this. And now if you go with stock price predictor, I will just copy it down. I will tell you where I have taken all those stops. So let me show you where I've taken from these all. So but let's see before that, how is it working or not? Like writing a hello world. Okay, just save this down, and now it's time for like this instantiating, for setting up your server. Name equals to main, and then I will just app.run, debug equals to true. Anything gone wrong? I think, yeah, no, it's true. Okay, now if I save this, if I run this down, it will take a little bit of time and it will run, and so is starting over here, and this is my URL address. If I see over here, now you can see over here that we have a beautiful website, but now you can see why it is running. The reason why it's I have to stop that server to get running. So let me stop that server because another server is running into the ML01 projects folder over here, which I have to stop it. I will debug it. I will to reinstall my Visual Studio Code, but I will show you where I have taken this all. So the first thing first, you have to keep in mind from where you have to take this is from tail block. So I will just annotate the code in my ML01 projects folder. Just I will annotate from where I have taken, which is from, first of all, I have imported the CDN. First of all, I have imported the CDN of Bootstrap and Tailwind CSS, and then I've gone to tailblocks.cc. I will gone to tailblocks.cc and grabbed my header, then this navigation menu, then I have to grab my header, and then I have this predictor, and you can see all the code is in my GitHub. Okay, now if I show you what the prediction.html does, is simply first of all what I've done, I have written a form into that. You can the code will be in the description, means the GitHub. You can head over to that. Okay, so I'm just using the request to get the form, the open, the high, which is the input variables, and then I'm pre-processing it. So how I'm pre-processing it, I'm putting into the 2D array to make prediction, then I'm loading the model, then I am predicting on the test data, and then returning the prediction, and then I'm just rendering the template from prediction.html, and prediction equals to prediction, which is gone through here. So if I go to the prediction.html, you can see that I have just I have made one layout. I've used Flask inheritance to inherit the template from layout.html, and you can see the layout.html is just a chunk of code. So prediction is just a prediction, and the prediction is derived from here. Okay, and it's just prediction is this, prediction is that, it's just given. Okay, pretty much easy. Let's see if it's working still now or not. It's still working, so let me put some value. So it's just, and it will tell the closing price, and it will tell, when it tells the closing price, it tells the direction of the stocks. Okay, so the closing price is 4.865888054. Okay, so that's the pretty much easy that we need to understand about making a Flask or Flask website and end-to-end machine learning project. And I really hope that you enjoyed this tutorial, this section and this project. In the next section we will be talking about principal component analysis, then we'll do one of our project, and then we have done till now 2 projects, which is an end-to-end machine learning project to get on a resume. And you can also modify it. Let me tell you how you can modify it. You can see over that we have an open, high, low, close, volume. There is a research paper, something called the stock price prediction using machine learning. They've given what the features they have used, like index volatility, like mean, etc. Selling price of the, sorry, 3 days price, 3 days previous price, and 9 days selling previous price. So you can do that kind of features and integrate over there to make it the more powerful model with a complex model. Okay, but do not make it too complex. You can see we had worked on lots of data to understand, and how we understood that this is good for linear regression. The reason that we have understood, because our data is not multicollinear. What do I mean by multicollinear? Because many of the interviewer asks that how you will perform when your data is multicollinear with linear regression algorithm. Your answer will be no, we cannot perform when linear regression when your data is multicollinear. It's only because the variables, linear regression does not work well when your variables are highly intercorrelated. Okay, when you're, let's say, it will be all same, means correlated, very highly intercorrelated. So if they ask you what's the way to remove this, so you can say, okay, we can use principal component analysis, which we'll study in the next section. So you can say, hey, we can use principal component analysis to remove the multicollinearity from our data, and then it's boom, you are done with your interview. I mean, it's kind of just one question as an asked in the interview, as I was asked in one of my interview. Okay, so that's the basic thing that we need to understand, and I really hope that you enjoy this section. The next section we'll head over to the PCA, and we had done 2 projects. Now it's good to see that all of you are doing projects, and I hope that you are very enjoying. Okay, you can leave your questions in the comment box. I will definitely pick up that question. Okay, thank you for seeing this section. I'll be catching up in the next section.
Okay, so now we will talk about principal component analysis, which is a dimensionality reduction algorithm. Okay, so you will get to know what is dimensionality reduction, etc. But before that, we should have a toolkit of some of the concept of linear algebra, like linear combinations or linear transformations, and eigenvectors and eigenvalues. Okay, so we will review linear transformation and eigenvectors and eigenvalues so that we can be on the same page. Okay, so if you want to get in more detail, there is a YouTube channel named 3 Blue 1 Brown, like this. You can head over to that. He has a very good playlist on linear algebra. They have a series of section videos. You can watch that if you want to dig dive into that. But for this, you don't need that. Okay, but what is linear transformation? Linear transformation is just like is a function. As we have seen, f of x, which is a function, so it just transforms your function, transform this x to maybe the square root of x. So this is a function. The transform from one vector space to another is that respects to underlying linear structure of each vector space. Okay, so if you have seen the 3 Blue 1 Brown videos, he has clearly mentioned that is a function. Linear transformation is a function that transforms your one vector space to another with linear structure, okay, or with parallel to each other. It's a linear structure of each vector space. If a little bit of non-linear gains, you will be not able to do the transformation of your vector. Okay, so that's called a linear transformation. So linear transformation can be written as T column. We are transforming our vector R to down. Okay, so here's an example of 1D linear transformation. So here's the function t of x, and a, b, the sum is scalar, and they have one-dimensional linear transformation t of x, which is our function that maps your from interval of 0 to 1 to the interval of 3 to 0. So we have a vector, the 0 to 1, and it scales, okay, by the factor of 3, to the intervals like this. Okay, so that's the linear transformation. Head over to the 3 Blue 1 Brown channel for more details. So eigenvectors and eigenvalues. I'm not going to dive into math of eigenvectors and eigenvalues, but it's just like what it does. Let's say you have the new transform vector. It's just a scale version of the original vector. So you have some vector, let's say v. You have a vector. We have a vector, let's say this, and it's the new transform is just a scale, means the new vector is just scaled from this vector like this. If I choose new pen, yeah, so it's like this. Then the original vector is the eigenvector of the original matrix. Okay, so if your new transform is just scaled from the original, then your original vector is known as to be eigenvectors, and the factor by which it is stretched, like this green color, is known as eigenvalues. Okay, and vectors that have these characteristics are known as eigenvectors. Okay, and eigenvalues means the factor by which it is scaled or stretched are known as the eigenvalues, which is denoted by this symbol, which is lambda. Okay, so that's the simple idea behind eigenvectors and eigenvalues. Again, let's revise what we have studied till now. Till now we have studied about linear transformation, and a linear transformation is a function that transforms you from one vector space to another with respect to lying under a linear structure of each vector space. Okay, we can write out here, we can write our linear transformation as a t of x. For example, for 1D linear equals to ax, and a be the sum linear, scalar. Okay, So what we are doing over in this example, here we have a vector of from the interval of 0 to 1. We are transforming it to 0 to 3 by scaling it by a factor of 3. Okay, that's the linear transformation. Okay, and here in eigenvector and eigenvalue, we have a new transform vector, which is the linear transformation which is happening. Okay, it's a linear transformation which is a new transform vector. It is scaled from the original vector, means from the original vector like this. It has been shown over here. Then it is the original vector is known as the eigenvector of the original matrix. Otherwise, it's just a vector. And the factor by which it is scaled here is 3. The factor by which it is scaled here is 3. Then the 3 is your eigenvalue. Okay, this is what the simple eigenvector and eigenvalues are. Okay, pretty much easy what I'm trying to say you here. Okay, if you want to get in more detail, there is a video by Gilbert Strang. Gilbert, I think I'm pronouncing correct. Gilbert Strang linear algebra videos, or a book by Introduction to Linear Algebra. You can have a look by Gilbert Strang, or you can have a look for a quick look at 3 blue 1 brown video on linear algebra on YouTube. Okay, so that's the kind of resources to learn more. But for now, if you know this, then you're good to learn about principal component analysis. Okay, so you may think, yeah, Yush, I don't want to do so much of math, etc. So you have a library known as NumPy, which you can have a look, which I have given the notebook in the description box below about NumPy, Pandas, so you can have a look. So we can just implement by this LA. LA is alias as a linear algebra. We are taking out the EIZ of the input, and input here is our vector. Okay, and this is the eigenvector and eigenvector of this matrix. Sorry, yeah, this is a matrix. Okay, so and this matrix is just a 2, minus 1, 4, 3. Okay, so that's the matrix of 2 by 2 matrix. Okay, so we have studied about linear algebra that is required for us for a principal component analysis. Now it's time for understanding why we are studying this all and why we need dimensionality reduction. So let's say you're working on kind of a large amount of data set. So this is 3,000 dimensions. And what do I mean by dimensions is like the size of the house is 1 dimension, then floor of a house is 2nd dimension, then number of fans is a 3rd dimension, then etc. So like that we have 3,000 features. Okay, so we have 3,000 features. So for that, first of all, it will cost storage. Second, it will cost time. It will even take months to train your model. So it will even take months. So you don't have too much of compute resources. Okay, so that's why, but in real world we have millions of dimensions data available. So what we do, we simply use dimensionality reduction method or technique, which is a PCA, to reduce your model feature, data features or variables. Okay, and we typically see this in text data or image data. So let's say you have some image. Let me draw one image of mine. So here's my image. So it will, the eye has 1 dimension, and it may be a millions of dimension data set, only one image, millions of dimensions. One image I have worked on, to that, which has 785 dimensions, 785 dimensions. So we have to work on this. Typically will be seen on your text data, where you will be working on natural language processing like word embeddings, or image data where we're working on images. Okay, so you need the principal component analysis. Okay, so what is principal component analysis? Principal component analysis is a method for dimensionality reduction that is used to reduce the variables or the dimensions of the data by transforming large set of features into smaller ones that contains most of the information. So let's say you have x1, then you have x2, then you have x3, and all the way around to the, let's say, x40, let's say 50. Okay, so what principal component analysis does, it asks you a component. Let's say you have given a 2 component, so it will try to put most of the information into the first component x1 and it will try to put, let's say, P1, and in the second component most of the information in these two components, because you have said to reduce from 40 dimension to 2 dimensions. Okay, so it will simply compress that like that, or put all the information into the first data variation into first and second. If you say it is 1, so it will try to put most of the information into first, and it will remove this all. So obviously you will lose some of the information from the data, but it's good to have not more than dimensions. Okay, I will give you a tip when you have to work on principal component analysis. Okay, so what is the basic intuition? Basic intuition behind principal component analysis is that we have a principal components, which is a new variable, which are the new variable, like let's say I have given you P1 and P2. They are the new principal components, which are new variables, okay, that are constructed as a linear combinations of the initial variables. Okay, so what we do, let's say we have x1, x2, all the way down to the x40. So we just try to put in all the first and second. So means is a hyperparameter. 2 is a number of a component is a hyperparameter. So let's say we have taken 2. Okay, so it will try to put most of the information into P1 and P2, and these are the new vectors or the unit vectors or the variables like this all, and it's just a linear combinations of these variables. Okay, of the initial variables. Okay, you will get to know that through visualization what I'm saying, and these combinations are done in such a way that the principal components are uncorrelated. They are uncorrelated, and most of the information from these variables, I mean size, price, etc., will be compressed into the first components and so on. Okay, and we are projecting each data point onto only the first few components to obtain a lower dimensions of data, preserving as much of the data variation as possible. So what is this we are projecting, etc.? If you have seen orthogonality concept in linear algebra, orthogonality, so what it tells, so here's a visualization of that. So here we have a data, and what we do, we take out the two components. Let's say we have two components like this first dimension, and then we have a second dimension like this. Okay, so we have a second dimension like this. Okay, these are the principal components which are constructed, which are constructed as the linear combinations of the initial variables. So what we do, we project our data point onto this. We project our each and every data point onto these principal components like this, and now our data point will be on this. So here's the visualization which is showing more about this. So we are projecting each data point onto the two components. Here we have first component, and here we have second component. Okay, this is the basic intuition behind principal components. So basically we have let's say this, and let's say this one, and you have a data point like this. Okay, so you just project the data point onto here. You project data point onto here to reduce the dimension of the data, preserving as much as the information as you can in the first component. Okay, so you will see the algorithm. So let's start seeing the algorithm to understand a little bit more detail what we are doing. Okay, but before that, let's review some of the concepts from previous slides. Okay, so principal components are the unit vectors. Means they are the unit vectors like the new variables that come out, let's say P1 and P2, whatever the P all the way down to P and P3 is the number of components as constructed because from the linear combinations of the initial variables. And these combinations are done in such a way that the principal components are uncorrelated. Okay, you will see the algorithm by this uncorrelated, etc. And most of the information within the initial variables are just compressed in the first and then second, like this number of components we are given. Okay, pretty much is what I'm trying to say here. Okay, and we have seen the basic intuition. Now it's time for getting into the algorithm. So the first step and the first and foremost step of this principal component analysis is data preprocessing. What do I mean by data preprocessing? Means we have to standardize our data. So in this step, you standardize your data. It simply means that your data should be falling in the same range. Okay, so let's say you are working on some system, like let's say the age, like the you have a one variable which is the age. So you have an age, and let's say the first person age is 20, second person age is 40, like this. So let's say a new person age is 200. It's far away or far different from these, means it's called an outlier. It's called an outlier, which is not in the range of age, okay, and which is not in the range of the common ones, okay. So let's say your data is like 20, 40, it's a 2, 3. So let's say it's a 4,000. So this is kind of an outlier, and principal component analysis is sensitive to outliers, okay. So what it will do, so that's why we do the standardization of the data. Sometimes we do normalization also. So we do the standardization of the data, so our data falls in the same range. And the reason why it's critical to perform, because it's quite sensitive regarding the variances of the initial variables. Okay, if you have seen the variance and mean if you have. And the formula for this is x scaled equals to x minus the mean of xi by the standard deviations. Okay, standard deviation, and then you will get the scale formula of your data. And don't worry how to implement this. You can also implement this just by coding in Python. So let's say we have made a function. Let's just standardize. It takes the value of x, then you try and make a new variable x scaled, then you subtract x minus the mean, is np dot mean of x divided by the np dot standard deviation of x. Okay, you can do this, but if more formally the vectorized code is in scikit-learn, you can use scikit-learn to implement it just 3 lines of code. Okay, don't worry if you are not able to implement from scratch. After the first step, after you standardize your data, now it's time for getting into the computing your covariance matrix of your data. So what do you mean by covariance matrix? In the covariance matrix, a p by p symmetric matrix where the diagonal are the variances of whatever the data. But if you can have a look on the internet what is covariance matrix. But here, after taking out the covariance matrix, it will tell you that tell us how the features of the input data set is varying from the mean with respect to each other. Okay, so here it tells a correlation like that. It's not a really correlation, but here we have an input data set like x, and it's out of how much the input data set are varying from the mean with respect to each other. Means the x1 how it's varying from x2 and etc. It is sometimes important because they are some variables are highly correlated and they contain unnecessary information to work on. Okay, so you can remove that. Okay, so that's how we compute the covariance matrix. Pretty much easy one I'm trying to say here. Okay, so you just denote covariance matrix with C, and for implementing covariance matrix, you can use the again numpy for the scientific numpy.np.conf, and you just give the data as your features, let's say x, and you get your output as a covariance matrix. Okay, pretty much easy I'm trying to say you here. So let's see what I've seen so far. We've seen first we have to pre-process your data like data standardization or normalization. Then we have to compute the covariance matrix of your data. It tells you how the input variables are varying from the mean with respect to each other variables. Okay, because it's sometimes important because some variables highly correlated and they contain unnecessary information. Okay, the next step is computing the eigenvectors and eigenvalues of the covariance matrix. So let's review what we have seen in eigenvectors and eigenvalues. So in eigenvectors we have seen that if our new transform vector is just a scale from the original vector, and the factor is called the eigenvectors, and the factor by which it's stretched is known as eigenvalues. Okay, so that's the eigenvectors and eigenvalues. The reason why I made this PPT is if I write on blackboard, that will be not beneficial for you, because I would be saying, so I had make it as a note so you can have a look on the future also to see how it's working, and it's better to have a text onto the screen to while you're listening. Okay, so what we do, you compute the eigenvector and eigenvalue of the covariance matrix. Means you come eigenvectors are the transform vector from the original vector, and the factor by which the is stretched is called the eigenvalues. Okay, you can easily compute the eigenvectors and eigenvalues in Python, and then what you do, you sort the columns of eigenvectors matrix V and eigenvalue matrix D in order of decreasing value. What do you mean by the step 4? Let's say you compute eigenvectors and eigenvalues, and those who has high means high information or high numbers, so you just sort the means the larger one in the first, then larger one in the first, then larger second, third, fourth, fifth, sixth, seventh, like this. Okay, and then after that, what you do, you simply let me do that. You simply compute the cumulative energy content, how much the content each eigenvector is having, okay, and then you select a subset of eigenvectors as a basis vector. Means, let's say you in scikit-learn there is in any other, you should choose how many number of components to use. Okay, that's the main thing. So what you do, you simply sort in decreasing order, and you compare the content of each eigenvector, and then you select who has the high energy or content from the top. And if you choose the principal component 2, then only two highest will be choose, those who have highest number of information. Okay, and then you take this two and to project onto the you project data onto the new basis. Okay, so you have a large amount of and then what you do, you remove this, or you project this principal component this eigenvector onto the new vectors. Okay, and this is the formula, and this is randomized, and this is the feature vector transpose. Okay, so we have seen so far, and here's steps. What were the algorithm of steps? And I have not written last step, which is projecting the data. You can have a look, but because my was not fitting. Okay, so first you pre-process your data, then you compute the covariance matrix, then you compute the eigenvector and eigenvalues of the covariance matrix, then you rearrange the eigenvectors and eigenvalues, then you compute the cumulative energy content of each eigenvectors. Although it is not necessary, because when you sort the in decreasing order, the top will be having the highest information, and then you select a subset of the eigenvectors as basis vectors. Okay, so I think that we have seen so far, and I really hope that you have enjoyed this tutorial in this section. Previously, I think you may find it's quite intimidating. Now I think that you are able to grasp that concept of linear regression, logistic regression, support vector machine, principal component analysis, and then you have coded projects, and then you have coded Boston house price prediction, stock price prediction, and classification project. You have coded logistic and linear from scratch. Now in the next section, we will code principal component analysis from scratch. We will do with ourselves to get the more feel of the principal component analysis. Okay. So I really hope that you have enjoyed. I'll be catching up your next section. So let's start with the next section to learn something new. Okay, so now we'll start with learning theory. Again, one of the most important concepts to learn in machine learning, and I think gaining something or less, we will see the topics which we'll study in this course, in this section is, we will see why it is very important. Means maybe it might look a little bit more not sense over here, but maybe if you are going to deal advanced version of machine learning like deep learning or NLP or computer vision, it should surely make sense that learning theory actually works. And in learning theory, in this section, we'll learn about these three topics. Our main talk onto this, like bias and variance trade-off, and then we will move on to approximation, estimation, error. Then we will move on empirical versus minimization. And this will be our new concept. these are just a definition, just a problem framed, okay, just a definition which is needed, because in many of the research papers they have listed empirical risk minimization or approximation estimation error. The reason why they have maybe some in history they might have different choices. Okay, so we will study, we will just see the definition of this, and it will surely make sense. But if it is not, please be sure to ignore it for now. Continue with this course, and you feel free to come again. Okay, you feel free to come again and then watch this two concept, because it will surely make sense. Okay, so let's start with bias and variance. Okay, so in bias and variance, here we will study about bias and variance trade-off, and here is your warning. Warning is one of the easiest concept to learn, as instructed by even when I heard that it's easiest concept to learn, and it seems the easiest, but it's very hard to master, very hard to master. And I hope that you heard Andrew Nung saying this, and I think this actually makes sense. If you're a beginner, then it might not, because you will understand everything, but when you are actually developing the product, it's a very important to keep track of bias and variance trade-off and etc. Okay, so let's start with bias and variance, but before that we are going to recall our two problems, which is my favorite, overfitting. Oops, not my favorite, it's an overfitting and underfitting. Okay, so here is my favorite diagram from the Google. So here, let's assume that we have a time in x-axis and values in y-axis. Okay, so maybe some kind of problem. Okay, so here you have these data points. Here you have these data points, and what you do, you just fit a straight line. Means a simple linear regression. Simple linear regression. Okay, you just fit it a simple linear regression, which is just theta 0 times x0 plus theta 1 times x1. Okay, so, plus theta 2 times x2. Okay, so here you just assume that you have fitted a straight line using a linear regression. Okay, but you can see over here that it is not performing well on the training set. Also means this is my training set, so it is not performing well. The residual error or the cost function will be very high. Okay, the cost function, which is j of theta, which will be very high in this case. So we call it as an underfitted. Okay, so the major problem that make this problem occur is that we have a low amount of features, or you have low amount of data, or you have a low amount of data. Okay, so these two causes the problem. So you low amount of features, low amount of data. Okay, and that can be sensed using just by adding more data or adding more feature, or if you don't have feature, you can do feature engineering to generate more features. Okay, so just do not focus on feature engineering for now, because it's not a data science course, but obviously you just need a simple feature engineering, means it's just generating more features based on our features. So let's put an example that you are building a spam detection system. So let's assume that you are building a spam detection system where you have one column which is of text, another column which is the label, whether that text is a spam or ham. So it is a label. Okay, so you can generate more feature like length of the text, what is the number of a text in that, what is the number of words in that text, what is the number of a character. So using this text feature, you generate more 3 features, and that's called feature engineering. Okay, so I will be, if you say, I'll be very happy to make a video on feature engineering. Okay, it will be a full-fledged data science course. Okay, so here after this we have our simple linear regression, which is just like this. Now this is called underfitted, and major problem that I've seen so far in my experience is a low amount of feature stack that we have. Okay, so in general, the underfitting means is just that your model is not performing well on the training set, and it's obvious that it will not perform well onto the testing set. So that's why we call this underfitting. Okay, the next picture of here is good fit slash robust. Robust means it will be very robust. It is a very good fit, you can see. It is a very good fit. The residual error is low. The residual error is low, and we have a very good polynomial kind of thing, non-linear, or I can say we can say non-linear or a polynomial regression over here. We have applied polynomial regression, and here's what we get as a hypothesis. Okay, so here you can see that is a very good fit, and this is the robust model. Okay, so we can say that this model is performing well on the training set as well as on the testing set, because whatever example will come here, the residual error will be low. Okay, so like that is performing well on the training and testing set. Another picture which tells you about overfitting. What do you mean by overfitting? Overfitting simply means that your model performs very, very well, or I can say that your model learns very, very well on the training set, where your cost function of j of theta is equals to 0. Okay, where you don't have any residual error, or approximately equals to 0. Okay, so your cost function is very, very low, so you can assume that your model learned a lot. So just touching each and every example, so your model learned a lot. So that's why your cost function is very, very low. And cost function is just denoted by the summation over I equals to 1 all the way down to the m, h of xi minus yi squared. Okay, and it's just taking out the difference between the predicted and actual value. And here the predicted and actual value are on the same line. So here your model learned a very nonlinear hypothesis. It happens that if you have a lot of features, and here you have a low features, and here if you have a lot of features, that happens. Okay, and maybe you have used too much degree in polynomial regression, so that's why it happens, or maybe something kind of a very kind of complex architecture, or you have made a very complex function f of x with the highest degree x4, etc., like that. Okay, so this is the problem for overfitting, and whatever new example come over here, your model will be very, very high. Whatever come here, the residual error will be very, very high. Okay, so your model will fail to generalize well onto the new training examples. Okay, so in general, overfitting means that your model perform bad, or I can say your model perform very, very well on the training set in which your cost function is low, is equals to 0, which is actually good, but you may think it is good, but just wait, that your testing set error is very, very high. Okay, so that indicates the problem of overfitting. So we can prevent overfitting by selecting some of the important features, or regularization. So regularization is just an advanced version of selection of features. So let's see what it does. Okay, so I have already told you about regularization now in our regularized linear models, and I hope that you understood that. Okay, so now we will see the bias and variance trade-off by taking a look at some scenario of your model. Okay, so let's assume that you are building some model. Okay, so you are building some model, and your model gives 1% error on a training set. So you have one training set like this, and you divided this training set into training and evaluation set. So you have this whole data, and you divided this in training and evaluation set. Okay, so what you've done, you've taken a 1% error on the training set, 1% error on the training set, which is if you see over here, 1% error on the training set, and 15% error on the evaluation set. So you can assume that your model is, you can see that your model is overfitting, because your error is very, very low in training set, but your error in validation set is actually 15%, which is very high. Okay, according to this. Okay, so it is performing very, very well on the training set, but it fails to generalize well onto the testing set, so it is overfitting. And in this case, we say that the model is having high variance, and we use bagging to reduce high variance. which you will see in Ensemble Learning methods or section. So don't worry, you can come back again to this section to watch this. Okay, so this is how you identify if your model is having high variance. Next is that let's assume that your model is giving a 15% error on the training set. Okay, 15% error on training set and 16% error on evaluation set. So it is not performing well on the training set. Obviously, it will not perform well on the evaluation set. So it seems to be underfitting. So here it has high bias, and we use boosting. To reduce bias. Okay. So this is what I'm saying. And let's take for the sake of an example example that your model is having both high bias and high variance, where you have a 15% error, which is obviously high variance, and 30% error on evaluation, which is obviously high bias. Okay, so it is both overfitting and underfitting, and obviously it has a high bias and high variance. Okay, the next last example of this bias and variance trade-off is your model gives 0.5%, on a training set and 1% on a testing set. So it seems to be a perfect model or a robust model where it's not learned too much on training set. It is a very robust and good model. Okay, here it seems to be a good, so we can say it has a low bias where it has a very small error, and it has a low variance where it has on training set is a very good. Okay. So this is what we consider for low bias and low variance, and all of these we take assumption. Do you know what assumption? Oops, you don't know, but because you were watching. But we take an assumption that base error or human level performance or human level performance is approximately equals to 0%. So what do I mean with this assumption? What do I mean with this assumption? That we take our base error to be approximately 0% in all of these examples. In all of this example. Okay, so let's see what's that human level of base error is. So here you can see that you're going to build some classification model, or maybe the face detection model. Okay, so you have built a face detection or face recognition or real-time face recognition. So your algorithm, even you will fail to identify this person. Even I will fail to identify this person. The reason why? Because it's very blurred, very blurred. Okay, so even a human error. Okay, HLP. Even a human error will be very high, because he will be not able to identify who this person is. Okay, so you cannot expect that your model should be very great over here. You can expect that your model is your model is also giving the same error as you are giving, because you are also not able to identify, as well as your model also not able to identify. And actually this is here the HLP is very high, or I can say the base error is very high. So we can say that here you cannot expect your algorithm to work best. But let's assume that you have a fresh image, and where the HLP is equals to 0, means human level performance is equals to 0, and now you can expect your algorithm performance to be good, because it is the human level performance is equals to 0. So that's called the base error. And I hope that you understood. The next. We have talked about bias and variance trade-off. You can again rewind this video to understand again. But what is approximation estimation error? This is just a definition. So the approximation estimation error in some data is the difference between exact value and the approximation of it. And this approximation indicates your f of x. Means the outputted model, the output from the model. So here your f of x given some approximation, and this is the ground truth, which is y hat. Okay, so difference between these both is called as approximation error. Okay, so here I've taken one example from Wikipedia. Again, it's a scale example, but that's generally mean. I already told you, in cost function you take out the difference between, that's approximation estimation error. Okay, so it's just like this. If the exact value is 50 and the approximation is 449.9, then the error will be 0.1. And that's actually what you do when taking out the error for one training example. You just subtract this. In the regression problem, what you do, you just subtract y hat minus y, and then and you get your answer. Okay, and then you add summation for every I, etc. Okay, so this is what you do, and this is just a definition because you will see a lot in your research papers. Okay, next one is empirical risk minimization. Again, we have seen, so an algorithm receives as an input on a training set S. So I'm going to just make you familiar with this, what I'm saying, that an algorithm receives as an input a training set S. Means we get our training set, which is a sample, from the large distribution D. Okay, so we get our sample from the distribution D, means large. We just take out some sample and labeled by some target function y. Okay, so here we have our training set, as well as we'll be having the labels for it, because this is framed on supervised learning. Okay, so here we will be having label as well as the samples for each training example. Okay, and should make a predictor. We should make a f, the predictor, that maps our input variable x, means these features, to the output variable y. Okay, and the goal of this algorithm is to minimize the error outputted with respect to the unknown d. Means now we will feed a new example that a model has not even seen, and your model should be very minimal, or your model should be, or your model errors should be very minimal. Okay, so this is what the full definition is saying, and it simply means that we want to come up with the predictor L subscript S H. We want to come up with the L of H with subscript S, where S emphasizes the fact that the output predictor depends on S. Okay, so whatever the output will be, it depends on S, because we have learned the weights, we have learned the W, we have learned the theta 1, theta 2, all around theta n from these S. So that emphasizes, that minimizes the risk or the error, which is called the ERM, which is called the empirical risk minimization. Okay, so I hope that you understood this concept very much clearly, and I really hope that you had enjoyed seeing this section. And I have talked a lot on empirical risk minimization, learning theory, and etc. So I hope that you will utilize this way. And we have already talked about and now you can continue further. If you haven't understood anything, you can feel free to ask in the comment box below. I'll be very happy to take your doubts, and be sure to have a look at the course website, which is already available in the description box below. So meet you in the next section.
Okay, a very warm welcome in this section, and in this section we will be talking about decision tree, one of my favorite topic to talk on, as I will go in depth of decision tree to make you understand everything in decision tree with intuitive examples, with solved examples of decision tree. As I have seen on YouTube that they are some instructors are doing great job, but they are not doing depth into decision tree, means for free. So I just want to make you familiar with decision tree, whoever is watching this tutorial, into depth, and I really hope that you will enjoy this section. But before that, what we are going to cover in this section are as follows. First, we will start with introduction, geometric intuition, basic intuition about decision tree, what the decision trees are. And then we will go further into how we will be building that decision tree. So for building, we will learn sub-concept, which is like entropy, information gain, Gini impurity. Okay, then after that we will build our own decision trees, and then I will show you the implementation of decision tree. Okay, but before that, let's understand the basic intuition of decision tree, as there will be more topics which we will cover as I will discuss later on. Okay, so let's start. So first of all, what is decision tree? Decision tree is a supervised learning algorithm. Okay, so it is a supervised learning algorithm, and what do I mean by supervised learning is that we are having our x1 with our label y1 all the way down to the x2, then we have y2 all the way down to the xn, and we have yn. Okay, so we are having labels. So it is a supervised learning algorithm, and it is used for both, like support vector machine is used for both regression and classification. So it is used for both classification and regression. Okay, so you will see how we construct the decision tree like that. Okay, so let's start with the basic intuition of decision tree. So the definition of decision trees, that they are nested if and else statements. Okay, if you're a programmer, then you will be relating this concept, which is if and else, and the Python is a prerequisite, or any programming language is a prerequisite. So what is decision tree? It is just a nested if and else statement. So it is a nested if and else statement. So I don't know why it is so bold. So it is a nested if and else statement. So what is just, it just ask a question and it splits the data. Okay, so let me write the formal definition to make you more intuition behind. So they are nested if and else statements. Okay, so it's just ask questions, and splits the data. Okay, so it's just ask question and splits the data. So let me take one example of iris data set. Okay, so what we do in iris data set. So but let me make you familiar with what is this data set to make you more clear understanding of this topic. Okay, so iris data set is simply like this. You have a data set which has 4 features, like sepal length, sepal width, petal length, petal width. Okay, and you have the label, which is the species of that flower. Okay, so this is a task of flower species detection on the basis of 4 features. Okay, so this is a classification data set, binary classification data set. So you are having and like this. So let me change my color. I don't know why it is so bold. Okay, so you have like this. First you have sepal length, and then I hope that you understand what is sepal and what is petal. So sepal width, then you have petal length, and then you have a petal width. Okay, and then you have one more column, which is the label, which indicates what is species. So let's take an example: 2.2, 4.30, let's say 3.2, 4.6, and the label is setosa. Okay, so you have 3 classes in this data set as a label, which is setosa, which we label as 0, versicolor, which we label as 1, and virginica, which is labeled as 2. Okay, so the output will be either 0 means setosa, then either it will be 1 means versicolor, or virginica as in quoted as 2. Okay, so that's the iris data set that I had just make you familiar with. Okay, so what we will do, we will not make use of any library, we will not make use of anything. We will simply what we will do, we will simply make a decision tree by yourself by making just if and else condition. Okay, so we'll make a simple classifier. Obviously it is not so formal, but we'll make a simple classifier that will simply classifies your flowers. Okay, so that's what we are going to do. So let me remove this, and I really hope that you understand what this data set is, and more if you want to more in detail about what the data set is, you can search online. This is a famous data set like iris data set, which is just for flower species detection system. Okay, so let's start. So first here we have an variable x's. Here we have our x's, which is sepal length, sepal width, petal length, and petal width. Okay, so we are having these features, and we have a yi, which indicates either 1 or 2 or 0 or 2. Okay, so that's the basic intuition, means the data set part. We are given this data set. Now what we will do, we will make a classifier like this. First, if we write if, let me choose another pen. Okay, I hope that I should choose a better pen like this, blue. Okay, so if the petal length is smaller than some a, and a may be some number. A may be some number, let's say 2.3. A may be some number. If petal length is smaller than a, then consider y to be versicolor. Okay, so let's consider y to be 1. Okay, if not, if it is petal length is greater than a, then what to do? Oops, I hope that it is getting not clear. What happened? I have to buy my new computer. I don't know why it is so much lagging. Okay, so if it is smaller than a, the petal length, then consider your flower means a versicolor, and we have made one. And if it is petal length, if your petal length is greater than a, then what you will do? You will write else if sepal length, you take again one feature and says if it is smaller than b. If sepal length is smaller than b, then you consider your y to be Virginica, means 2. Okay, if both condition fails, then say that your output is setosa. Okay, so here is our simple decision tree. We're using 2 features. We have made the decision trees using 2 features. So let me make it more intuitive. I hope so that you are able to understand. Okay, so that's why I'm speaking very slow. So here, let me tell you if petal length, here we have taken 2 features, which is petal length and sepal length. Okay, we had not taken this 2 features. Okay, but you can make that. But this is not a formal decision tree. This is just for an example. This is obviously not correct. Okay, so you had to made one if condition that if the petal length is smaller than some a, and a can be anything, 2.3, 4.3, that is usually I'm taking anything, but it is usually taken which we'll see in one of our data set. We will see how it is chosen, and you will obviously see how it is selected. Okay, so if it is smaller than a petal length, then consider that y to be equals to 1. If it is not, let me check the recording is on. Yeah, okay, recording is on. Okay, so if the petal length smaller than a, then we consider our y to be this Virginica. Okay, if the petal length is greater than a, or is this condition fails, it then goes to else condition, and in else condition this is again a nested if an is control flow. So check if your sepal length is smaller than b. If it is, then you say that y equals to Virginica. Okay, and otherwise if this condition also fails, then it says else your y means y should be setosa, and you have this whole into this nested loop in this, and you have this whole classifier, and this is your whole classifier. So this is the decision tree. Yeah, so let me make this diagrammatically in the terms of decision tree. So in terms of decision tree, we can write this if and else statement. First, we have our root node. We make our root node like this. Let me make one root node. Here we have our root node with this condition: if a petal length is smaller than a. Okay, then if it is yes, then you say your y to be 1. Okay, if it is no, if your petal length is no, okay, you again make one more condition, which is sepal length is smaller than b. If it is yes, then you classify this y equals to 2. If it is not, then you take it as a 0, and your whole 3 variable target variables are covered. And this is the decision tree, and this is the decision tree I have made in yellow. This is the decision tree. Is just ask a question on the data set: if the petal length is smaller than a, if it is, then consider y equals to 1. If it is not, then again we have made another decision, and then we if it is yes or if it is no, like this. Okay, so this is the decision tree. It's damn easy like this. Okay, so here again I'm saying this is what you do. Just believe me. Yeah, we had this is the decision tree, and how it is constructed we will see. Okay, so we have made this if and else statement, nested if and else statement like this, and this is what the decision tree is. So here are certain terminology that we will have to see over here. So here are the details that we should know. Okay, so the first node, the head node, is known as a root node, or parent node. Okay, this is the root node. Obviously this is also a parent node, and these are the child node. Okay, child node, and this is the parents node, and this is also the parent node, and this is the terminal node. This is the terminal or leaf node, because you are not splitting this node into further nodes, so this is called the terminal. And this is also a terminal node, this is also a terminal node. Okay, this is also terminal or a leaf node. This is sometimes called a leaf node when you are not splitting further. Okay, so this is a leaf node, or you consider it as a leaf node. This is the whole thing is called branch. This whole thing is called branch. This whole thing is called branch. Okay, and that's the basic terminology of this. Okay, and this is the splitting of your data. Okay, this is what you are doing, which is splitting. Okay, if you're removing some node, let's take an example this, then you are pruning it. Okay, then you are pruning this node, but we don't want right now. Okay, so that's the decision tree, and I hope that you understood this example clearly, and I really hope that you will that you got a very good intuition of decision tree in much smaller span of time, in much easy way. Okay, so I hope that you remember this terminology. Either I will make you familiar with terminology by the time also, if it is not required for remembering all those things. Okay, but it's best to take a paper and a pen and write notes with me, whatever I'm writing. Okay, and just listen me carefully. After listening me, you can make notes. Okay, so now let's see what's the decision boundaries will look like. Okay, what's the decision boundaries will look like, or the hyperplanes will look like. But what do I mean with hyperplanes? I mean with hyperplane decision boundary is, let's take an example of linear regression. In linear regression, we are making a straight line. This is called the hypothesis, decision boundary. Then we have a hyperplane. It's called the hyperplane. In support vector machine, we are also making hyperplane. In logistic regression, we are also making hyperplane, means a decision boundary. So in the decision tree, we also have the decision boundaries, okay, or hyperplanes. So let's see how it is constructed. So I don't know I will be able to make that image or not, but I will fully try that. Okay, so here let me make one x and y plane, x and y. Oops, please anyone help me to make this. Okay, let me do that. Oops, I'm just freaking out. Let me do it again. Yeah, okay, great. So I have made one, and this is my x-axis. This is my x-axis, and this is my y-axis, and we have two features, which is sepal length and petal length. I think so, yeah. So we have petal length in the x-axis, and we have sepal length in the y-axis. Okay. So I have just made it. You can remove this y-axis. Maybe it will confuse you. In our x-axis we have petal length, and y-axis we have sepal length, because we have taken only two features in this example. We are not taken more features like petal width and sepal width. Okay. So what we consider, what we have done, we have considered this full reason. We have considered this full reason to be y equals to 1. Okay, this hyperplane, let's name it as a first hyperplane. So this full reason is our y equals to 1, means whatever data point will come is considered y equals to 1, and this is just This is just the if statement that we have seen. If petal length is smaller than a, okay, then y equals to 1. So this is the full reason, okay, means we have not further split, so it is just a full reason where y equals to 1 if that condition passes. Okay, then another hyperplane we can construct. Let me choose another pen. Another hyperplane we construct that this region would consider y equals to 2. Okay, y equals to 2 if the sepal length is smaller than b. If the points come in this region, then it will consider y equals to 2. Another we have hyperplane. Let me take another pen. Let me take another pen. Let's take an example of blue. Okay, another we can consider that as a y equals to 3. Okay, if that falls in this region. So here we are constructing hyperplanes, and if something come here, then it's consider y equals to 1, it's y equals to 2, or y equals to 3 with these two features. Obviously it will be more dimensionally high when you plot the 4 features. Okay, so you can see that we have a hyperplanes where we are able to make predictions, okay, and we have made a simple classifier. Okay, but something to note over here, that all your hyperplanes are axis parallel. Okay, are axis parallel means this is parallel and this is parallel. So you can see over here that all the hyperplanes are axis parallel. Okay, so that's the I hope that you understood decision trees in depth, and this is the basic intuition that I want to give it to you in more sophisticated way, or not sophisticated, it's just a good way. Okay, so as I've tried it to keep it as simple as I can, and I kept it. Okay, so let's start building, or let's start with mathematical region, that how we construct these kind of decision trees, how we construct. Okay, so but before that we have what we do, how we choose the variable, or how we choose the feature to be the root node or the branch, or this how we split. So we have an attribute selection measure, and if you select randomly, like I have choose a petal length, if you choose randomly, then you will be ended a very bad model. So we have different attribute selection measure with like entropy, information gain, gain impurity, which we'll see in detail to understand how we select the attribute to be as a root node or like this. Okay, so let's take an example of this data set. If you want to split this data set, what feature you will use? What are you going to use? Outlook as your feature, root node, or temperature as a root node, or humidity as a root node, or wind as a root node. Okay, and play tennis is our label. So which you will use? If you choose randomly, maybe you will be ending up with a bad model. Okay, so you have to do that kind of thing. No, so we scientists or researchers have done a very great job. Even you all have to do all this kind of thing, research, and please keep contributing to the AI community. That maybe I'm also doing research in machine learning, and definitely will come up with something extra. Okay, so different attribute selection measure are entropy. We have entropy. Then we have the second number, we have information gain, which we usually write as IG. Then we have Guinea impurity, and simply IG. Okay, so we denote like this. Okay, so we will talk about all of these three, and I hope that you will understand each of them. Okay, so let's start with entropy. Okay, so entropy, let me write it more formally. Yeah, so first of all, what is entropy? Entropy is an attribute selection measure. It's the measure of randomness. Okay, how pure that attribute is to be used as sub nodes or a root node. Okay, so it's the measure of randomness. So let me write the definition, because definition is also important. And if you want this kind of all my notes, you can simply write with me along. Either you can comment or join the New Era community, Discord community, and ask me there. I will be able to give. Okay, so ask me there, I will be able to give all this entropy, etc. Is the measure of randomness. It's the measure of randomness. Okay, the higher the entropy is, the higher the entropy is, the harder to draw any information from them. Okay, so if the higher the entropy is, it's very hard to break your node, okay, or to choose the node. So our entropy should be low to be considered as a leaf node. But still, don't worry, I will dive into the cases to make you more understand what do I mean with these terms. Okay, but first of all, let's take I will show you one equation, and then I will show you how first of all one example, and then I will show you properties of entropy. Okay, so first of all, let's take an example where you are given, you have y to be maybe y1, y2, all the way down to the yk. And in this case, you are not, this is not examples, this is this is like maybe setosa, means what is the number of classes you have. Okay, so maybe you have binary classifier or you have a multi-class classifier. Okay, so what is the number of a classifier? So maybe you have in the iris setosa, we have here's setosa, Virginica, and versicolor. So here we have y equals to y1 to be setosa, then we have Virginica, then we have versicolor, means 3 y's. Okay, so that's what I mean with this. Okay, so let's first of all let me give you the equation. Okay, so the equation is defined as like this. H, we define our entropy by H equals to, let me choose white color because I like white much. Okay, minus this minus is very important, minus the summation I equals to 1 all the way around to the k, and k here is the number of your what is the number of a class. Okay, p of y, probability being y, log of base, and b is usually taken as 2 or e. Okay, to 2.713. Okay, so b is usually taken as 2 or 3, but we usually take b as a 2. So if you are taking b as a 2, then you can consider it as LG. If you're taking b as a e, then you take as L and natural logarithm, and you have a log 2 base, log 2 with the log with the base 2. Okay, this means LG. Okay, so you take log of p of yi. Okay, and that's the whole equation of your entropy, means it just measures the randomness. Okay, so let's take one example, because it is I know that is making no sense to you, and I know that is making no sense to you, but I will make sure that it will make sense. Okay, so first is we want to measure our randomness for playing golf. Okay, you want to measure your randomness for playing golf. Okay, so let me write play golf. Oops, let me write the data set first. What's the data set we'll be using? So we have this play golf data set, play golf data set, where if it is what is the number of yes, which is 9, and what is the number of no, which is 5. Okay, so this is our data set like this, and let me make this also. Okay, so this is a data set, and you want to take out the entropy of playing golf. Okay, playing golf. Okay, and here we want to take out entropy of being no, and being yes. Okay, so what you do first, you take out the entropy of 0.36 log 2 0.36 minus, means this is your first this is your first yi, this is your first y, means yes, sorry, no, this is for no, and minus, let me make it up, okay, minus 0.64 log base 2 0.64, okay, this is what we have, and the answer is 0.94. okay, so here what we are doing over here, that first we are writing this equation p of yi times the log of for no, and then we are writing for a yes, okay, and there is subtracting, and we have entropy as 0.94, and it can be further split. Okay, so this was the basic calculation of entropy, but let's see some cases of entropy to make you more sense of this entropy attribute selection measure. Okay, so we will see some properties. So let's consider that we have y to be two class, means we have a binary classifier where we have two class, one is yes, and other one is no. Okay, any kind of yes or no, whether it is playing tennis or etc., it's yes or no. Okay, so let's take an example of let's take one scenario. Let's take one scenario number 1. Okay, so here is our scenario which tells, here is data, here is your data, and number of a yes is 99%. Number of a yes is 99% in your data, means these are your y labels. So we have two unique values in your y labels. So here you have yes and no. So in that case your yes is around 99% and your no is about 1%. Okay, this is your case 1. So let's take out the entropy for this. H of y minus, you're taking minus 0.99, means 99 log, means LG, I'm writing log not 2, maybe I'm writing a log of 0.99 minus this is for my yes, means this is for my yes, because we have added a summation for each y variable. So we are doing for each y variable. Okay, minus 0.01, the log of 0.01, and your output is 0.0801. Okay, so that's your entropy. Okay, so let's take one more scenario. Scenario number 2, and here let's take an example of your data having the yes to be around 50% and your no is around 50%. Okay, so if you take out entropy of this, minus 0.5 log of 0.5 minus 0.5 log of 0.5, which is equals to 1. And the maximum entropy is 1, and it is very hard to split this. It's very hard. Okay, so its maximum entropy is 1. Let's take another scenario. And if you have a binary classifier, I'm taking an example, your maximum entropy is 1 if you have a binary classifier. If you have a multi-class, then the equation changes, okay, which you can see on the internet. But most of the cases, if you understand binary, you will be able to understand multi-class. Okay, let's take another scenario. Scenario number 3. Okay, scenario number 3 tells you that your D, which has yes to be around 0% and you have no to be around 100%. So your entropy over here would be 0. Okay, your entropy will be 0 and the minimum entropy is 0 over here. Okay, so you can see some cases that is if you have ID3 follows, if you have some algorithm, means a decision tree follows that if you have entropy equals to 0, then you consider that as a leaf node. And what is leaf node? As your prediction. If your entropy is 0, then you consider that as a leaf node. If your entropy is 1, then it needs further splitting, or if your entropy is big, means your entropy is, for binary is generally greater as like this. Your entropy is generally like this. Entropy is in between or equals to. Okay, so your entropy will be in this range. So some algorithm follow ID3. There is one algorithm called ID3. It's a subset of decision tree algorithm. So ID3 follows if your entropy is 0, then you consider, or is small, then you consider as a leaf node. If it is 1 or large entropy, then it needs further splitting. Okay, so that's the entropy, and I really hope that you understood entropy in detail. So let me make you familiar with what we have seen so far. So we have talked about decision tree, which you can reverse back to see more, but I'm going to recapitulate the entropy. So what do I mean by entropy? Entropy is the measure of a randomness that measures if your attribute needs further splitting, or it considered as a root node, or it could consider as a leaf node, or like that. Okay. So we have taken one example of playing golf, and then we have taken some three scenario where we have seen that it is very hard to split. It is very hard to split if you have. It's very hard to get information if entropy is high, so it needs further splitting. Okay, so if you have yes to be 50%, no to be 50%, then entropy will be 1. If you have another scenario, then it will be like this. Just see the calculation. You can see the calculation if you want to understand it much better. Okay, so that's what this entropy is. But let's see the diagram of entropy visually. It's a bit interesting. Okay, it's a bit interesting. So let me draw one diagram of entropy. Okay, so here we have our, let me draw a good one. So here we have 0, here we have 1. Okay, so I hope so that I'm not able to draw it, but let me try at least. Okay, and the highest entropy is 1. The highest entropy is 1. Okay, is 1, and this is the diagram of entropy. This is the diagram of entropy. Okay, so the highest entropy can be 1 if you're taking with this equation. I have already showed you or proved you. So this is an example of entropy. Okay, great. So we have seen the entropy, which is the measure of randomness. So now let's talk about another attribute selection measure, which is information gain. Okay, we'll talk about information gain. Let me write it down. Information gain, and I will take an example of, I will explain you information gain with the help of one data set, which is, I have already showed you. I thought I will give you a surprise with that, but I've already showed you. Let me show you again. So here we have that data set. Let me show you. Yeah, here is our data set. Okay, let me draw back to like this. Okay, so here is our data set, which is play tennis. Okay, this is a play tennis data set, and what we will do, I will make you familiar. Just see this data set. Look at this data set. I will be looking. I have already looked at. Okay, so here you have a play tennis as target variable, and you have these features. So we will see which feature to use or which feature to not. Okay, so here you can just see what you have around 1, 2, 3, 4, 5 as a no, and 1, 2, 3, 4, 5, 6, 7, 8, 9 as a yes. Okay, so we will just see this, and now let's come back to information gain to understand. First, I will give you an overview of what information gain is, and then we will dive deep. Oops, where is my I don't know why my computer is lagging. Just give me a comment why it is very lagging. Okay, so here is my information gain. Okay, great. I hope that everyone is able to see. Yeah, okay, great. So let's consider you have the data set B. Okay, so you have the data set D like this. Let me consider this as a data set. Let me consider D. Oops, wow, we have a data set which is D, and what you do, you further divide this data set into your further data sets, further smaller subsets of this data set. And how we will divide this subset of this data set? It means that you divide this data set into versions. And what versions? Maybe let's take an example of iris data set. Okay, so what you do, you divide this Setosa, versicolor and virginica into 3 data set which contains Setosa, versicolor and virginica. Okay, so whatever examples of Setosa will go in this data set, whatever examples of virginica will go in this data set, whatever examples will go versicolor will go in this data set. So that's what you do, you divide your data basis on the number of labels, and I'm talking about binary classifier or classification task over here. Okay, so what you do, you divide your data set. First you divide for dv1, then you divide for dv2, then you divide it for dv3. Okay, dv3. Okay, and what you do, you take out the entropy, of this dv1, you take out the entropy of dv2, then you take out the entropy of dv3. Okay, and maybe there's this kind of Setosa, versicolor, virginica, you take out entropy, and then you take out the entropy of your whole data distribution. Okay, before splitting. So you take out the entropy before splitting, and then you take out the entropy after splitting. Okay, so you take out entropy before splitting like this. Okay, after that you minus it, you subtract your h of d. The function, the entropy means previous entropy, this entropy h of d, which is the entropy before splitting, minus, let me write it down, minus the weighted entropy, which is this, which is whatever the weighted entropy will come. So let's see how we, with the help of an example, what I'm talking about, how do you calculate one example to make it more familiar. Weighted entropy, how do you take out the weighted entropy? So you just minus it with the weighted entropy. Okay, after splitting, entropy after splitting. So let's see how it is done in more detail. Okay, so I've just give you what the formula is. You just divide your data into subsets of your data, like the divisions, and then you take out the entropy before the splitting, and then you take out the entropy after splitting. Okay, so let's see. So first let's take out the entropy of division number 1. Here I'm going to take out entropy of division number 1 with the help of that play tennis data set. Okay, so h of dv1, which is there we have 3 5, means first I'm writing for 3, means first I'm writing for yes. Okay, first I'm writing for yes, where we had divided our data set into a yes or no. So there we are having total of 5 examples, where 3 examples are yes and 2 examples are no, and out of 5. Okay, then the entropy will be 0.64. Okay, but what you do, you take out entropy of your division number 2, it will be 0, and in the same way you take out the division number for division number 3, 0.97. Okay, what you do, you take out the average entropy, and that's equals to 0.64. That's equals to 0.64, and the formula for calculating your weighted entropy is like this. Just wait for a few seconds. The formula for calculating your entropy, weighted entropy, is like this. Let me write it down. First, what you do, you take out this. I think it's not 64. It's, yeah. So I will just multiply with the first division number 1. Here we at d1, the norm of d1 divided by d times the entropy of d1. Then what you do, you plus d2, the norm of d2, times entropy of D2 plus norm of D3, and this is the division number 3 data set divided by the norm of D. Okay, and this is your full data. This is D is the full data, so you take out the size of that full data. Okay, then you again D3y. Okay, and then this is your weighted entropy that you get after all of this. After you've taken out the weighted entropy, then that will be equal to some number, and then what you do, you subtract your entropy, previous entropy, you subtract your entropy before the splitting, you subtract your entropy before the splitting minus you get after splitting. So let me write the formal equation for Ig, what you get. Okay, so Ig equals to y, and any var means variable. Maybe variable can be outlook, or temperature of that, from that, or windy or humidity. Okay, so in that we will check if the higher the entropy, higher the information gain is, we can select that as a root node. Okay, so what you do, you just take the entropy of your data, full data, and then you means of your data, and then you minus it, minus I equals to 1 all the way down to the k. The norm of di means the division of your data, and this is simply the maybe setosa or then versicolor or yes or no, like that. So divided by the full d times the entropy of di. Okay, so this is your weighted entropy, this is your weighted entropy, and this is your entropy. Okay, before you're splitting, and then you will get the information gain for that variable. Okay, so we will see one more example later on when we will be building our own decision tree by ourselves mathematically. So again, let's recapitulate what we have seen so far. We have simply seen, so let's go back to that data set. So where is my data set? I don't know actually where. Yeah, here is my data set, and here what we do, we take this data set and we simply divide this data set into multiple divisions, into 2 divisions. Okay, so we divide this data set into yes and no. Okay, and whatever number of examples will come, we take out, let's take an example. Here we have 9 over total number of data examples, and here we have a 5 over total number of examples. Okay, so what you do, you simply 9 by 14 log of 9 by 14 minus 5 by 14 log of 5 by 14. Okay, then you will get some entropy, which is your entropy of your data. Okay, entropy of your data before splitting. Okay, so that's what the entropy is, and I hope that you understood what I'm trying to say over here. And this is your for yes, and this is your for no, because you have added a summation of your entropy like this, I equals to 1 all the way down to the k. Then you have a probability of yi minus the log of, means with base 2 probability of yi. Okay, so that's what we are doing. You are doing the same over here, but this time you have 2, so that's why you're doing 2, and this is only for binary. You can see equations for multi-class. Okay, so that's what the information gain is. And here what we do, we take our data and we divide our, first we take out the entropy of that data, and then we divide our data into multiple divisions. And here we have 3 categories, so we divide it into 3 categories. If you have 2 categories, you divide into 2 categories, and then take out entropy of that categories, and then you take out the weighted entropy. Okay, without rather taking out the average, you take out the weighted entropy of that after splitting these all. You take out the weighted entropy, then you subtract. And how you take out the weighted entropy, here is an equation. I'm going to give it to you. It's just I have already given, but more formally, this is the equation for weighted entropy. Okay, so what you do, you simply, it's the norm of D means no divided by what is the number of a full, means here we have number of a no, number of no divided by total number of examples times the entropy of that di. Okay, so that's how you take out the weighted entropy. So after taking out the weighted entropy, you subtract the previous entropy minus the weighted entropy. Okay, so that's what we are doing in information gain. I really hope that you understood information gain. Okay. Okay, so please see if on some blocks, if you want, either you can ask me in Discord server. I'll be very happy to help you in the new era. You can find the Discord server in any new era, new video on new era. You can find that and you can join, and there is a lot more that you can. And also, if you want to support, please kindly go to New Era YouTube channel, and please subscribe that YouTube channel. Okay, and if you can watch the whole tutorial on New Era, okay, because you are going to get the whole ad free over there. Okay, so now we have seen entropy, then we have seen information gain. Now it's time for talking about Gini impurity. Okay, so this is also the most famous, it's most similar and most famous that is used today, which is Gini impurity. And it just equals to, it's very similar to entropy. It's a very similar to entropy. This is, I use things very similar sign. Okay, don't comment it like this. It's just, I have just said it like this. It's not I use thing. It's just it's very similar to entropy. So let me give you one equation. The equation for calculating the Gini impurity. So G, and it is not information gain. This is the sign for a Gini impurity of y equals to the 1 minus I equals to 1 all the way around to the k, and again it is your y variable, not anything, it's the y variable. Again, I have already seen y equals to yes or no, meaning 2, or it also vertical, so unique values in your I times the probability of yi squared. Okay, so that's the thing. And again, it's if we take the same scenarios, how I'm saying it's if we take the same scenario as we have taken entropy, some scenarios. Let's take an example of scenario number 1, scenario number 2. Scenario number 1, where your yes, we have, let's take you have y to be 2 class category, where you have unique value as a yes or no. Okay, so what is the probability, means what is the number of a yes is 0.5, and what is the number of a no is 50%. Okay, 0.5. Okay, so what will be the Gini impurity? Gini impurity will be 1 minus 0.25 is 0.25, because if you square this, because here we are squaring, so if you square this and again you subtract it, minus 0.25, then you are going to get a 0.5, and 0.5 is maximum in Gini impurity. 0.5 is maximum. In entropy we have 1 as a maximum. If it is this 0.5, Gini impurity is 0.5, then it needs further splitting. If it is 0, then it's not need. If we can consider that as a leaf node. Okay, so that's the scenario that we have already seen. And if it is in the case of Gini impurity, our Gini impurity in this case where you have 50% yes, then that will be 1. So we have, but you may ask, here Ayush, what is the advantage of Gini impurity rather than using the entropy? So it is an alternative to entropy, just to increase the just to make it fast. Because in Gini impurity, if you have seen, we are just taking h of y equals to the minus the summation I equals to 1 all the way around to the k, p of yi minus the log of p of yi. So here you can see we are taking a log, and taking a log takes time. Okay, so as an alternative, researchers comes with a very easy and understandable way, 1 minus, and this can be derived. These are derived in information theory. Okay, but I'm not going to go in information theory, but you can see this is for Gini impurity, and this is most used as an alternative to Gini impurity that entropy. Gini impurity is most used as an alternative to entropy. Okay, So that's the thing, and I hope that you understood Guinea impurity also. So let me make you familiar with the diagram. So here is the diagram. Let me make first for entropy. First here is for entropy. So here we have 0, here we have 1. So here this is for entropy, where your maximum is 1, and this is for, obviously something will differ, so but the maximum is 0.5 in Guinea impurity. So yellow one is Guinea impurity and the white one is entropy. Okay, white one is entropy. So I hope that you understood the why I'm saying. But why we use Guinea impurity? Because it is more faster, because we are taking log and that takes time. So it's more faster than entropy. Okay, so that's the whole definition of whole decision tree, and I'm recording till 51 minutes, and I hope that you understood all of this. I hope that I've written a lot. Okay, so we have learned a lot, and I really hope that you understood also. Okay, so now we will make one decision tree classifier, and I will show you the decision tree numerically. Okay, how we do regression task and decision trees. Okay, so first let's do in a fast way. I do have not a lot of time over here, but I will show you this data set. So here is my data set which I'm going to use. Okay, so first of all, what we do, we take out the entropy. Okay, we take out the entropy of this whole data set. We take out the entropy of this data set, h of d. Oops, where is my pen? H of d, and simply what we are doing here, we have two y's. So here we are taking the entropy of our data distribution d. Okay, so that will simply equals to 0.94. As I've told that you have to take out entropy before splitting. Okay, for information gain. So we take out the entropy of this data set, as you have around 5 no and 9 yes. Okay, so in that way you can take it out. If I want to make, I can simply make like this: 5 by 14 log of 5 by 14 minus 9 by 14 log of 9 by 14. Okay, so after you calculate, you will get this. Okay, so but feel free to correct me if I do anything wrong in calculation. Okay, feel free to correct me in the comment box. Okay, in mathematics we do, I'm just doing it fast, just we have to remember the concepts. Okay, so after you calculate the h of entropy of your distribution, now what you do, you calculate the information gain. You calculate the information gain. You calculate the information gain. Okay, how? First you calculate the information gain for y with respect to outlook variable. Means we have to check how much information that outlook variable contains. Okay, so in outlook, here we have outlook variable. You can see over here that here we have outlook variable. So let me take out. So in outlook, if you see the y variable, we have in sunny we have 2 yes and 3 no's. We have 2 yes and 3 no's. Then we have in outcast, we have 4 yes and 0 no's. Okay, then in rainy we have 2 yes and 3 no's. Okay, so this is your outlook variable, and here you have a 2 yes and 3 no's, 4 yes, 0 no's, 2 yes, 3 no's, and this is for sunny, this is for overcast, and this is for rainy, and you can see over here. Okay, sunny, overcast and rainy. Okay, so this you can see that if you take out the entropy of this h of d2, h of d2, then you will see that this is equals to 0, and you can take this as a leaf node, and it does not need further splitting. Okay, so you can take this as a leaf node. Because this does not need further splitting. Okay, now what you do, you take out the entropy of this h of d1 of y. Okay, then you take out this h of d2 d3 y. Okay, so you have taken this data set, large data set. Okay, taken this data set and split it. You've taken this feature and split it. Okay, so we have this before splitting, and then what you will do, you take out the weighted entropy, weighted entropy, which is equals to 0.69. okay, so what you would, for information gain, you simply subtract 0.94, means the previous entropy minus the weighted entropy, 0.69. okay, and weighted entropy I have already shown you previously. Okay, and you do the same for temperature. You do the same for temperature, where in temperature you have Y, in temperature where you have around, you have three classes: high, I think mild, let me see, high, mild and hot. Hot, mild and cold. Okay, so in hot we have 2 yes and 2 no's, and here we have in mild we have 4 yes and 2 no's, and then in cold we have 3 yes and 1 no's. Okay, then you take out like this, and then you do for humidity, then you do for humidity, and then you do for windy. Okay, then you do, and it's found that the information gain in outlook is very high. Okay, so what you do, you take that outlook as your root node, okay, then you take that outlook as a root node, then you divide this, so here let me go to one of my favorite decision tree PDF, where I will just explain you what this is. Okay, so you take this outlook as a root node, then what you do, you divide this as we have divided into sunny, overcast and rainy, sunny, overcast and rainy. And overcast, you can see that we have a entropy equals to 0, so it does not need further splitting, so we can consider that as a yes, means we have 4 yes, so we can consider that as a yes because it's very pure, and then it needs further splitting, and this also needs further splitting, and then at some point they also become pure where the entropy equals to 0, so, or the gain impurity equals to 0, then you consider as a leaf node. Okay, so this is how we make the decision trees, and this is how we calculate the information gain. This is how we made our decision tree. Okay, great. Now I really hope that you understood decision tree, and now it's I also enjoy very much when I make these kind of tutorials, and because it's just amazing, just helping students to make this understandable things. Okay, great. Now as we have only talked about classification, so as regression is not too much hard also. So in regression, let me show you what we do in regression. So let me go to the scikit-learn decision tree scikit-learn. I hope that is stable. Yeah, here it is. So it explains very good. It explains in very good way. So let me make you what do I mean with this. So let me take an example of this petal length and petal width. So in the same way, here what you do, your petal length is smaller than or equals to 2.45, then gain impurity is high, then you split it. Okay, here the gain impurity equals to 0, then it does not need further splitting, but it needs further splitting, so it splits that. Okay, so here it seems to be overfitting, because if you leave the decision tree to ask as much question, then it will overfit. So what you do, you either stop at certain depth, you either stop your decision tree at a certain depth to make it more robust, or you prune your decision tree by removing some branches from here. Okay, and you can see the same way that we have seen that we have made this kind of decision boundary, hyperplanes. Okay, great. Let's see some more. Oops, I use Brave as my browser, but soon we'll try something. Please make sure that you can put your comment below if I can see. Okay, and regression, what decision tree we can apply in regression also. So you can see over here that here what we do, let me get back to some good pictures. Decision trees regression, but I will soon go to documentation to show you more sophisticated, in a good way. Okay, so here is my decision tree regression. and let's take an example of this. As you can see from this also, yeah, so here we have a good example. So here you have predictor and you have a target variable. Okay, so here what you have taken outlook, and then you divide into sunny, overcast and rainy, and sunny needs further splitting but overcast does not. Okay, so most of the time you average it and then you take out 46.3. okay, and then you split it again. What you do is split it. If you take out the average, again I'm saying you take out the average. Okay, that's what you are doing. And again, if I go further into this, it is very well explained. You can go to this, it's very well explained, but yeah, it's only for regression, but it's so much of but what we do, we simply, again, all the things are same. For attribute selection measure, you simply you can sunny, overcast and rainy. Overcast over here is, we have 4 this is your leaf, this is your concept, this is a so pure, so that's considered as a leaf. And then what you do, you take out the average like this, you take out the average, and then you take out the 39.8, 46.3 over here. After taking out average, then you split your sunny into false or true. Then if it is false, then your output will be 47.7, and if it is true, then it is 26.5. In the same way you do the regression. Okay, so I hope that you understood, and you can go again to understand it more detail. So what you do, you take out the hours played and hour average, standard deviation average and hours played, and then you count it, and then you simply do some calculation, and that's not too much hard. Okay, great. So we have seen so far about decision trees regression, and I really hope that you understood this also. Okay, so you can go to this node, this website, sadesad.com, decision tree reg. You will be able to understand it, but it's more important to understand attribute selection measure, because people usually confuse us at this, and we have taken lots of examples for this. Okay, great. So now what we will do, I will show you the documentation, the implementation for decision tree. I will show you the implementation of decision tree regressor and decision tree classifier. Okay, so that you can know, because it's very important to learn from implementation. Okay, so I will explain you in more intuitive way. So let me open my ink to go. I hope that I'm just using it. Let me see if this works for me or not. Okay, great. Let me choose this pen. Yeah, so here you can go to this website, thistable.com, and here you will be able to find more. You can go to scikit-learn.org and documentation of this decision tree classifier. Okay, so here again is what is the criteria to choose the attribute. Here we have Gini, and here we have entropy. Okay, so Gini is the default. You can choose entropy also. Okay, the quality of a split. Supported criteria is Gini, and the entropy is for the information gain. After splitter means, do you want to choose the best splitter or random splitter? Okay, best means it will choose the best, random means any randomly. Okay, max depth, this is very important hyperparameter, which you can tune it using grid search CV, or a randomized search. Okay, you can tune it. Okay, so that's what you will do. And what you do, you just make your decision tree to, if you do not make, then it will overfed, or then your decision tree will overfed. Okay, so the maximum depth of the tree, okay, if it is default as none, okay, if you do, it will learn a lot. It will make a lot of decision bound. It will learn a lot until and unless its leaves are pure. Okay, so it will learn a lot, so that's why it will overfit. So this is a very important hyperparameter. Then again, you have a minimum sample split, means here the default is 2. Again you have to tune it. The minimum number of samples required to split an internal node. Okay, an internal node is just that node, the minimum number of splits that require. Okay, this is 2, but you need to be very cautious into this. Okay, then we have minimum sample split, then we have minimum sample leaf, and then the minimum number of samples required to be at a leaf node. Okay, so what is the minimum number of samples required to be at leaf node? Again, it's 1, but you can also tune it, but it's not that, but it's very good to tune it using grid search CV. Then we have a minimum weight fraction leaf. Then we have what is the max features, means the number of features to consider when looking for the best fit. If you have a larger number of features, then you can consider as an the default is none, but you can use this, but it also has some disadvantages. Okay, then we have a random state, control the randomness of your estimator. Again, it's you can read some more details on random state. Max leaf node, the grow of a tree in a best first fashion. It is a default none. It's just like a max leaf node or the minimum impurity decrease. The node will be split if the split induces a decrease for the impurity greater than or equals to this value. But I've not used it if I say very much right. It's just a limitation that you can make to prevent overfitting. Okay, I think this is deprecated. Then you have a class weight. What is the default is none always. Then we have alpha non-negative value. So that's the basic intuition. Okay, so we had talked about this, and then you can see some examples, and then there is something called as let me show you. You can also use this as a understanding the decision tree structure. So I will just show you one example of this. Okay, so here you can use the graphist tool. Here you can use the graphist tool to plot your decision tree like this. You can he has used tree.plot tree. It is plotting the tree like this. Okay, because decision tree has one more advantage. It is easy to interpret. Okay, so that's the basic intuition behind decision tree. Okay, so let's go to decision tree regressor. Okay, so let me see where is regressor. Okay, let me see one more. Great, where is decision tree regressor? Here it is. Okay, so in decision tree regressor, it can be used for for regression task also. So here you have to choose certain criteria. The function to measure, here we are not using any entropy, here we are using the quality of your split. You can use mean square error, means how much it differs. Okay, so mean square error or mean absolute error or Poisson. So you can see a Friedman MSE, but most uses MSE or MAE or RMSE. Okay, a splitter, again it's best, again the same thing, max depth, obviously to control your depth to prevent overfitting. This is an important hyperparameter. Again, I'm saying this is very important. VVI, this is also a very important to tune. Okay, then you have minimum sample leaf, and then you have the same as we have discussed. Okay, and then you can see some examples of decision tree like this, how we make, and then there are certain methods like plot or etc. Then you have some examples which you can see from here, and this is usually you can use. We will talk about ADA boost also later on. Okay, so you can see some visualization in this library, and decision tree is used to fit the curve with addition, noise, or observation, and it's just controlled by the depth of that by the max depth. And the blue line considers the 2 and the max depth to be 5. If you take that, it will perform very well on training set, but bad on testing set if you do not control your max depth. Okay, so we have talked a lot on decision trees, and I really hope that you understood decision tree in depth. Okay, so in the next section, the reason why I've taken this too long to make you understand decision tree, because it's very important concept to understand, and I think it's very important. Okay, so you can have a look if you want onto this notes. Okay, but you can ping me on Discord or LinkedIn. I will very happy to give you these notes if you're not able to write. Either I will recommend you to write these things. Okay, I will just you can ask me to make this all wrong. Okay, so that's it for this video, for this section. So sorry for this section, and my throat is also so much paining, but yeah, that's it for this section. And in the next section we will start with Ensemble Learning, and again then we will go to Unsupervised Learning, then we'll talk a little bit on neural networks, and then we will end up this course, and you will be having enough understanding of machine learning to get started making projects in machine learning and getting a job or internship, but you have to do a lot of practice. Okay, so you can do that. Okay, great. So thank you for seeing this section, and again, if you have any kind of question, you can ask me. To the newer, be sure to subscribe if you wanted to support this content. Okay, so let's meet at the next section. Till then, bye bye.
Okay, so now we'll talk about ensemble learning, one of my favorite topics to teach and to use in my professional experience. So why I think ensemble learning is one of the best for Kaggle competitions. For Kaggle competitions, ensemble learning methods or techniques are most popular. 99% of the Kaggle winners uses some kind of ensemble learning techniques. So that's why I think that ensemble learning is a must-know technique. It does not involve a lot of mathematics, but it do involves only techniques, concepts, and a little bit more maths. Okay, but in differential we involve some mathematics, but here we do not involve a lot of mathematics. We require a little bit of mathematics, but there are a lot of techniques and concepts that we need and approaches that a particular Kaggle winners gives. Okay, so it's very we will dive into ensemble learning, covering the three techniques. I think the three techniques of ensemble learning. The first technique will be a bagging, which we'll talk about. Will be in a separate sections, subsections. Okay, so this is our main section, and in the separate subsection we will talk about bagging. Then we will talk about boosting. Then we will talk about stacking. Okay, so these are the three techniques that we will talk about in ensemble learning, and also we will see the implementation of each one of them, and I will also show you some of the Kaggle competition winners approach, or we will make one model seeing the changes, what changes they bring into your system, how your model accuracy increases. Okay, so great. But before that, let's let me just forget about the ensemble learning. Let me recall you some concept which is high variance concept. Okay, so high variance and high bias concept, so it should make sense to you. So let's recall, in high variance we have overfitting model. We have our overfitting model, if I'm correct. In high variance we have our overfitting model, and in high bias we have our underfitting model. Okay, so our models should be low bias and low variance model. If you have a high variance, then your model is overfitting. If you have a high bias, then your model is underfitting. And that's what the regulation that we need for this ensemble learning, just to make sure that we are on the same path. Okay, so let's start with a simple example of a small example. Okay, so if we have played some quiz, let's take an example that we have played some quiz of maybe in Kahoot or any kind of quiz, or if you are in competition, you have played some quiz. So it's a maximum percentage that the let's take an example that we have some question. We have some question here, and we have some option which is A, B, and C. Okay, so let's take an example that the majority. Let's take an example, A is the correct answer. So it is very obvious that majority of the students will go with A, and if the majority is on A, then it's likely to be A be the correct answer, and it's actually the correct answer. Okay, so it's like whatever the majority will say, we will go with that. Okay, here majority is saying A, and in this case A is the correct answer. And if you think about, the majority is more accurate than 1. Majority is more accurate than 1, and in some exceptional conditions it can be different, but in 99% the majority will win. Okay, majority will win if you have seen some quiz. Okay, so if you see that the option has got a highest majority and you are also into that, then you can think that is a correct answer. So in the same way ensemble learning works. Ensemble learning is an ensemble of models. Okay. So let's take one more example to get more feel. Let's take an example that some election is happening. And in that election, let's take an example that why we do not take only 1% vote and select any prime minister or president. Why we take the majority of votes which will go on to that party that will win. Okay, so the majority will make a right decision. Okay, will make a right decision in most cases. Okay, so that's what the ensemble learning also says. Ensemble learning has an ensemble of models. So let me tell you what we do in ensemble learning. We have a model 1, model 2, all the way down to the model K. Okay, so let me make this that it is visible. Yeah. Okay, so you have these kind of models, and you train your model onto your data. Okay, you train your model onto your data, and you take predictions from each of the model. So let's take an example that you are making a diabetes prediction system. So your outcome will be either 0, means non-diabetes, or 1. Okay, so let's take an example that model number 1 says it's a 0, model number 2 says it's a 0, model number 3 says it's a 0, model number 4 says it's a 1, and model number 5 says it's 0. So then what we have one more model, a big model, which what it will do, it will check the majority of votes, and here the majority is 0 and only one has given 1 and the majority of 0, so we will give our prediction as a 0. Okay, so we will see how it is trained later on, but here what the actual thing is, what is happening, we train our model and each model is giving predictions, and in each predictions we are taking into classification, we're taking majority of votes. It means majority means M1 is saying 0, M2 is saying 0, the frequency of 0 is more than the frequency of 1. Okay, so that's why our final prediction, which is y hat, is equals to 0. Okay, and it will be high chance that if one model predicts it's a 1 or 0, and the ensemble of a model predicts a 0, then they are more accurate rather than this. Okay, so that's the basic overview of ensemble learning. And you may think, here in classification we choose the majority of votes, but what about regression? What about regression problems? In regression problems, what we do, we take out the mean or a median output from each model. So let's take an example that your model M1 given some prediction which is regression value 2.4, model 2 given 2.6, model 3 given 2.5. So what you do, the final prediction will be the average of these outputs, the average or mean or a median of these outputs. Okay, so that's how we do in regression. We do not take the majority, we take the mean or a median of the output from the base models, and these are called the base models over here. Okay, so these are called the base models in ensemble learning. Okay, so don't be confused, what is base model? Base models are the ensemble of models that are being trained. Okay, so that's the basic intuition behind ensemble learning, and I really hope that you understood ensemble learning in depth. Okay, so just want to make sure that how we train, what are some of the techniques used in this, bagging, what are the techniques used in ensemble learning? So we have techniques like bagging, then we have a boosting, then we have a stacking. Okay, these are, and one more which is cascading, which you can learn, which is not yet in the industry yet, but yeah, one is just cascading, which we will see if we want, otherwise it's not necessary. Okay, so in bagging we will see one algorithm which is a random forest, which is something called as a random forest. Okay, which is just an ensemble of decision trees. And then in boosting, we will more prone focus on gradient boosting. We will more prone focus on gradient boosting, and we will focus on adaptive boosting, which is just an advanced version of gradient boosting. We will focus on adaptive boosting. Then we will see one Kaggle winner, which is XG boost. Okay, so we will see these algorithms or these techniques in this boosting. Then in stacking, we will see ML external library, how we do the stacking and what's the intuitive understanding. And you can see there is no any kind of math. This is only the concepts. Okay, so that's how that's what we are going to see. And the study motivation for this, for Ensemble Learning, why do we study Ensemble Learning, has a great reason behind them. The reason being, why do we study? This is the great question to ask whenever you do any kind of thing. Why? Let me use this good color. Why do we study? I think that is not visible in most of the cases. Let me stick to white. Okay, so why do we study? Why do we study this Ensemble Learning? The reason being is most of the Kaggle competitions, most of the Kaggle competition winners, uses some kind of Ensemble Learning. Either they use bagging, either they use boosting, either they use stacking, either they use cascading. They use some kind of Ensemble Learning techniques if it is a machine learning problem. ML problem. Okay? Okay? Just think that machine learning has also a power. Okay? So, but there is a difference in internet companies like Amazon, Google. They also uses these algorithms, XGBoost, AdaBoost, gradient boosting. Then we have a random forest in their own products in production. Okay, so Quora uses random forest for quotient matching. Okay, so they also use machine learning, these kind of algorithm, and these are very powerful algorithm. Which is often used in industry also, which is often used in many kind of Kaggle competitions, and around 99% of the Kaggle competition winners uses this kind of any kind of Ensemble Learning. Either if it is a machine learning problem. In deep learning problem, you'll obviously go with it. If it is an image problem, you'll go with CNN. If it is text, you will go with some word embeddings, and then you can use any of the techniques, and you can use RNN. So it depends. So you can use any of the technique if you want, but in most of the Kaggle competition in the past, we have seen that they are the winners if they use them. Okay, so you can see the case studies if you want in detail. Okay, great. So we have talked about Ensemble Learning, and in this section, now we will start a subsection which is bagging. Okay, we will start a subsection which is bagging, which we will dive into the bagging. Okay, so it's also called the bootstrap aggregation or bootstrap aggregative. Okay, so we will see just in a second. Okay, so just to recall, Ensemble Learning is an ensemble of base models. It can be logistic regression, it can be naive based, it can be support with the machine. Okay, it's a classification algorithm. Whatever the majority of votes will be, it will take the majority of votes and then gives you a y hat. Okay, so that's how it works. Okay, so and in regression we take out the mean or median of your values. Great. Now we'll start a subsection. Which is something called as bagging. Which is called as bagging. Okay, so in bagging, it's again Ensemble Learning technique, and sometimes it's called bootstrap aggregation. And from bootstrap we derive the word which is bagging, like this: bootstrap aggregation. Okay, I think my spelling is a little bit wrong, but just bear with me. Bagging. Okay. So that's what from the derived word from bootstrap aggregation, just in short. Okay, okay, great. So it's a statistics term. If you heard about bootstrap aggregation, means it's a statistics term. If you can relate with your statistics and probability classes, it's a statistics term. So let's see the geometric intuition. Okay, let's see the basic overview or intuition behind bagging. Intuition behind bagging. Intuition behind bagging. So what we do in bagging? So let's take an example that you have a data set. That we have a data set D. Okay, you have a training data which is D. So you have a data. So you have a data like this, and what you have done, you divided your data 80% for training and 20% for testing. Okay, so now what you do, just to make sure that you are on the same page on the division of your data also. Okay, so you take your training data, training data, and your data is just you take your training data like this, and your training is a supervised learning algorithm. So you have xi and yi. So you have your xi with your label yi for all i equals to 1 all the way around to the m, and m here is the length of your training examples. Okay, so this is your data, this is your training data, this is your training data. Now what you do, you sample some points. Let's take a sample k points, or let's take an example that you sample k points from this data set. You sample k points with the replacement, you sample k points with the replacement from this data, and you feed this to this model, which is now you got D1, which is D1. Okay, so you have sampled the subset of a data from this large data set. Okay, sample k points, you sample k points, and now what you do, you train your model using this subset of a data. You train your model using this subset of a data, and now you got your model as a M1. Okay, this is your M1 model. Okay, but you may think, yeah, can you repeat it again? It's all gone above your head. No worries. Again, I'm explaining. It's usually gone. Okay, so what you do? So I'm highlighting in white. So what you do, you take your training data, which is the supervised learning problem, where you have the labels. Now you take out the samples with a replacement. And what do I mean by sample with a replacement? I will talk about just after I make another sample. Okay. So as of now, just understand. We take out some sample with a replacement around the k points. We sample k points or m points, and we sample some points, or we take out a sample of a data from this. Let's take an example. This amount of data from this. This amount of data means any random data. Means we have this is a hyperparameter. We have to choose the number of samples from this data, and then we call it as D-1. Okay. Then we feed to the model. Means we train the model onto this data. Okay. Then what we do, we again take out the sample, k points with replacement, sample k points with replacement. And what do I mean? If your data is here, means if your data is here, then it can be also here, It is not necessary that your data should be different. It can be same. Some data can be same here and here also. Okay, so that's the sampling with replacement. Okay, now you samples again the random data, and it's not necessary that your data should be different from the D1. Some data points can be included. Okay, so you again sample k points, and here you have a sample of a data from the large data, and then you train your model onto this data, M2. Okay, you train your model onto this M2. Now again what you do, you take out the sample, k points, you do it for your number of base models, means the number of times. If this is also hyperparameter. Okay, how much you want to sample until you have your data points till k. Okay, till k. dash. Okay, and then you train your model till km k. And then what you do, you have your k models. Now you aggregate this into a large model. You aggregate this into a large model. Okay, m, large m. Okay, and in case of classification, the majority of votes will go as, let's take an example of ensemble learning that we have seen. That let's take an example of diabetes and prediction. Okay, so if m1 gives 0, m2 gives 0, and m3 gives 0, and m4 gives let's take an example 1. So the majority is 0. So the majority of votes will lead to the final prediction y hat. Okay, in case of classification, we take out the majority. In case of regression, we take out the mean or a median. Okay, so that's the basic intuition behind bagging, and I really hope that you understood. Okay, so let me explain it again. Those who have not understood, please pause this video if you can, because many students are still here that may not understand this. Again, I have to recapitulate or give a summary of this. Okay, great. So here, what we do, we have a large training data set, which is D. Now what we do, we sample our data, sample k points from that data. We sample k points from the large training data, and let's take any sample our data, and then we train our model on the sample, which is M1. It can be logistic regression. Okay, now we sample again k points with replacement, and also it is with replacement, so it is not necessary that your data should be different from the D1. It can be same, or it can be some data points can be same, and then you again train. So let's take an example, you train support with the machine. Let's take an example, you train 9 days. Okay, so you train, and the majority of votes is like ensemble learning. Okay, so that's what your backing is intuitively, and you can see that we are not involving any mathematics. This is just a bunch of concepts. Okay, so just I will make sure that you all are on the same page. That what it helps. It is great question. It helps you in reducing the variance. Bagging. Let me write. Bagging helps you in reducing the variance. We will discuss 10 minutes onto this also. Okay, yeah, okay, so bagging helps in reducing the variance. Okay, but before that, there is one term that I want to highlight over here, that here we have our all base models. These are our base models, M1, M2, and all the way up to MK. These are our base models. These base models are usually high variance model. These are usually high variance with a low bias model. And what do I mean by this? It is usually, we do not do lot of fine tuning. So that's why it is just overfitting, and we had done overfitting, so that's why it is good on training data. So that's why it is not underfitting. Okay, so we have the base models are high variance and low bias model. So we do not do lots of fine tuning. Just we do a simple let's say in random form, we just initialize with no number of depth. Okay, it can go as much as we can. So it is overfitting. Okay, so here we have high variance model and low bias. So what it helps? Bagging helps in reducing your variance. How it helps? In reducing your variance from making your model more robust. Okay, this is just what it does is combines them. So you have a low bias, high variance model. Now if you combine them, the majority of votes, then obviously we'll get a good amount of good output, or a correct output. Okay, so you combine the models, you combine base models, and then you get low bias and low variance problem. Okay, so this is what you get after doing bagging, and this helps in reducing your variance, and this is very good, Okay, So there is some I want to highlight over here, that here we are doing the row sampling. So just understand that this is a point that bagging helps in reducing your variance, because usually your base learners or base models have high variance and low bias. The bias and variance of that trade-off, that is high variance and low bias models. So what you do, you combine them, combine the base models with into a large model, and then you get a low bias and low variance models, low bias and low variance M, which is a large model. Okay, so that's the different. Now I think that you understood why we call it as it reduces variance. Okay, so here, how we sample our data? Okay, how we sample. This is a great topic to talk on. How we sample our data. Okay, so here we are doing row sampling. We are doing row sampling. We are not doing column sampling. We are doing a row sampling. So let me write it down. While sampling our data from the large distribution of a data. So let's take an example. This is my large data, it's training data. Now while sampling, what we do, we have this, we do the row sampling. We do the row sampling while sampling our data. Okay, so let's take an example that we have D columns and M rows. Okay, so we have this, we have D columns and we have M rows. Okay, so we sample only rows in bagging. Okay, so it can be like it can be go to D1. Okay, only rows in bagging. Okay, so that's what we do in like a row sampling. Okay, so we'll see in random forest we also do the column sampling plus column sampling. Okay, in random forest we do this, but in bagging we do not do the column sampling, we only do the row sampling. So I hope that you understood the bagging also. Okay, it's also called the bootstrap aggregation. First you bootstrap and then you aggregate your base models. Okay, so that's why they name it as a bootstrap aggregation. Okay, so just to make sure that you all understood, so I'm just recapitulating the subsection, as you can reverse the video to know about ensemble learning, because I don't want to just spend my time onto that. Okay, so here just want to make sure that here you have your training data. Here let me see here. Here you have a training data, and then what you have done, you take out the sample endpoints with replacement, okay, into your data, subset of a data, and then you train your model M1, which is your base model. It can logistic, linear, okay. Then you again sample K points in D2, then you again train your model onto these subset of a data. You do for K models or K subsets, and then you combine the majority of votes. Majority of vote will lead to classification, and if you use regression problem, we take out a mean or median of most output from the models, base models. Okay, so that's the intuition behind bagging, and it helps in reducing your variance. Because your base models are usually high variance and low bias models, so it combines the base models to bring up low bias and low variance model. That's actually good. Okay, so and in bagging we do the row sampling. Means we have a D features and we have M column, M rows, so we do sample of our M, not D. Okay, so we take whole column, we take all the columns. Okay, but we take subset of a rows for training. Okay, so that's what we do in bagging, and I really hope that you understood this bagging technique. Now it's time for learning one algorithm, one good algorithm, one powerful, one Kaggle-winning algorithm, one production level algorithm, which is random forest. Okay, why I think random forest is a very powerful algorithm to work on. It's a very powerful algorithm to work on. Let me write a random forests. Okay, random forest. It's a bagging algorithm. It's a bagging technique, or you can call it bagging algorithm. Okay, so why do I call this very powerful? Because in also my professional experience, I think that I have also used a random forest a lot, and it seems like it's this very powerful algorithm, whether you want to build a Kaggle competitions, which is a machine learning problem, or you want to make a production level machine learning. Okay, so random forest usually used by Quora, then we have Google, Amazon. They all use this random forest, but it has some basic intuition, a basic concept that instructors are not teaching, and it's very, very important. Okay, so first of all, what we do in random forest. So let's recall our decision trees. Let's recall our decision trees into this. Now our decision tree will play a role. Now here we have a decision tree. So let's recall our decision tree. So what we are doing in decision tree, we are doing it is a simple, it makes a decision and splits your node. Okay, so what we are doing is a simple if and nested if and else statements. Nested if and else statements. Nested if and else statements. So we take if the sepal length is smaller than petal length, then you take a y equals to 1 like this. Okay, so it is a nested if and else statement. Is just ask a question, is just ask a question, is just ask a question to the node, and then splits the node, and then it splits the node. Okay, so you can reverse for the section of decision tree. We have some attribute selection measure like entropy, then we have information gain, then we have a Gini impurity, which we have seen in detail in 1 hour of section of decision tree, and I hope that you enjoyed that also. Okay, so that's the decision tree. Okay, so what is random forest? Random forest is a combination of decision trees DT plus bagging plus feature bagging, or we call it as a column sampling. Okay, so what do I mean with this? Let's understand this step by step, so it makes sense to you also. Okay, so what we do in random forest, we have our decision trees. Okay, so you know about decision trees. So we have there's a 500 decision tree. Okay, so random forest is an ensemble learning algorithm. So we have a lot of base models, means decision trees, lots of base models. So here we have a large distribution of a data. Okay, and here we sample our data D1 and we train a decision tree onto this data. Okay, decision tree. Then we sample D2 with replacement. Then we train our decision tree onto this subset. Okay, so you are not using different algorithm. You are using only decision trees. Okay, with the row sampling with bagging. Here we are doing bagging, means the sampling with replacement, means here we are doing a row sampling. Okay, plus in bagging we are doing row sampling and aggregating your model, means whatever the majority of votes you will aggregate your model. Okay, so you are doing the row sampling plus the column sampling also. Okay, so here in this bagging we are only doing the row sampling. We are taking whole column, whole features, but you are only taking the rows. Okay, as a subset. But here we are doing also the column sampling. Okay, so let's understand what do I mean by column sampling or feature bagging. Okay, so the column sampling means that you have this your data like this. You have this your data. Okay, now you have D features, you have your D columns like A, B, C, D, and you have M rows. Okay, we have M rows. Okay, so what you do, for replacement you take any rows, for sampling you take your rows, random rows. Let's take an example. You took this row, okay, this row, and you took A and B as your column, and then you train onto this. You are not taking full columns or features. You have taken this A and P, and then you train, and then the next you took C and D. Okay, you took C and D. Okay, and then you train with one row. Just an example, you train decision tree. So they are different, and if they are different, it's much higher chance that your model will be very, very good. Okay, in ensemble learning, if your model is different, then it's very, very good. Okay, great. So that's the random forest. Okay, so we have a large number of decision tree, means base learners that are trained using a bagging technique. means it's sampling with row sampling plus column sampling. Okay, with row sampling plus column sampling, which is column sampling also called the feature bagging. Okay, train different trees, and then you in majority of votes, and then in classification you take the majority, or in regression you take the mean or a median of the outputs from the base models. Okay, so that's what you do in this. So that's what you do in this a random forest, and I hope that you understood. Okay, so let's understand it more intuitively, that there is something called as OOB. It is something called as OOB, out of bag points, out of bag, and this is called in bag points. So it's something called as out of bag points. So let me not recall this concept just now. So let's take an example. Let's take an example. So that what you have done, you have this DN, you have this large training set which is D. Okay, which is D. Okay, so what you do, let's take an example that you've taken this sample of a data as a D1, and the rest of the data is called the out of bag points. It's called the out of bag points. So what you do, you subtract, means the training data minus the DI, and I is the sample. So these are called the left points after the sampling, which is out of bag points. Okay, out of bag points. Okay, and this can be used for cross validation, for evaluating your model. Okay, so if you set in scikit-learn, there is a very good library which is scikit-learn. If you set OOB score to true, if you set OOB score to true, then it will give you the OOB score also. Okay, so that's the basic out of bag points, and I hope that you understood out of OOB points. Okay, so now let's recapitulate our bagging and random forest, what we have seen in random forest and bagging. Okay, so in bagging we have seen that we have our data D. Okay, what you do, you take out a sample, you sample with replacement D1. Okay, then you train your model onto this subset M1. When you again do D2, then you train your model onto D2, and what you're doing is sampling with row sampling plus column sampling with the replacement. Okay, and D3, then you getting your model D3, getting your model M2, M3. Okay, so the majority will go, and a large model means you just aggregate your model, and then you get your final prediction, which is Y hat. Okay, this is the whole pipeline. So in bagging you only do the row sampling, and random forest you do with column sampling, as well as you only take decision trees as your base models. Okay, so in bagging you can choose different kind of models, but in decision tree and random forest you take your decision tree as your base models, and decision tree are trained on different data. Okay, so that's the basic intuition behind the random forest, and I hope that you understood also about what is column sampling, or what is feature bagging. Okay, and obviously this also helps in reducing your variance, as this is a bagging technique, so obviously it will help you to reduce your variance. Okay, so that's the basic intuition behind random forest. So let's see the runtime train and runtime complexity of this, because if it is very it's very required to talk about train and runtime complexity of this random forest. Okay, so in decision trees, the train complexity in decision trees, the train complexity, let me write in DT, the train complexity is order of n log n times d. Okay, times d times so it is in decision tree we have n log n. So in random forest we have d number of decision trees times k number of samples. Okay, k number of models. So that's your model. That's the train and runtime training complexity of your random forest, and the decision tree is just a n log n. Okay, so that's the, and d here is the number of k is the number of the models. Okay, So it makes sense also. If you take an example of your D as a large data set, okay, let's take an example that you have a D, okay. Now you take out a sample with replacement with row sampling plus column sampling, with like feature bagging, okay. You take out a subset and then you train your model like M1, then you again do the D2, then you take out M2. So here, all the way around to the MK, here you have a K models and then you have a D decision trees, okay. So, and also this is a trained, trivially parallelized. It's a trivially parallelized. What do I mean? You can train this model onto parallelly. Okay, you can train the model. You cannot. You can train this parallelly. Okay, you can take out a subset. You train D1 parallelly, D2 parallelly, D3 parallelly. So this is a trivially parallelized. Parallelized. I think I'm pronouncing it correct. Okay, so this is a trivially parallelized. You can do trivially parallelized also. Okay, so that's the decision. Train and runtime complexity of random forest. And I hope that we have talked a lot in short span of time. And I hope that you're enjoying this video or section also. And I hope that you are enjoying a lot. Okay. So there is one more concept that I will talk on and end this video, which is, this section, which is extremely randomized trees. Okay, extremely randomized trees. So what we do in extremely randomized trees is very become popular after the scikit-learn releases its this API, which is something called as extremely randomized trees. Okay, trees. So what is this? This is in random forest. We are doing column sampling plus row sampling with bagging. Okay, with bootstrap aggregation. Which is bagging. Okay, so in random forest and RF, we are doing like this. So in extreme trees, we try out the possible values of Fi to determine the threshold. Means the decision trees. In decision trees, let's take an example that in decision trees we have some epsilon and its checks is greater than or equals like that. For identifying in decision tree, we are trying out every value, and that is taking time. Okay, so what we can do instead of trying out every values, we sample some subset of column, some subset of rows, and check with that and choose the threshold according to that. Because in random forest we have a lot of decision trees, and identifying the threshold is a key over there. Okay, so if you take whole possible values, then in that will be computationally time taking. So what you do, you try out the sample of values from that whole column. Okay, so then you try, and that's called the extremely randomized trees. Okay, so that's what I want to talk about, extremely randomized trees, just to make sure that we are on the same page. That what we were doing in random forest, we have decision trees, we have column and row sampling. Okay, and that reduces the variance. Okay, so here in random forest we are trying out in random forest we have decision trees, and we are trying out every possible values, and we are for that epsilon. So it's time taking. So what we do, we take out the sample of values from that column and as a sample, and then we check that for that epsilon for getting that epsilon. Okay, so if you're a little bit getting confused, don't worry, it's not a popular algorithm which is extremely randomized classifier or regressor. It is not a popular algorithm. The reason being, if you take out a sample, there is less chance that your model is good as compared to random forest. So I rarely use this extremely randomized forest. This is popular. I've heard of this as a popular algorithm. Okay, so we have talked a lot. I think that we have talked a lot onto this. Now I hope that you understood bagging. Then we have understood random forest. Then we have understood some decision tree, and then we have understood the ensemble learning. Now we have talked about bagging. Okay, now in the next subsection, Point 2, we will talk about boosting. Okay, and boosting we'll talk about gradient, adaptive, XG. Okay, so we will talk about 3 algorithms. Here we have talked about a random forest and extremely randomized trees. So there we will talk about 3, which is gradient, adaptive, and XG boost. And gradient boosting is also called GBDT. GBDT means gradient boosting decision trees, because they also use decision tree as their base models, only decision tree as a base models. But what are some of the disadvantages of random forest? Some of the disadvantages of random forest, that it is very bad choice to use a random forest or decision trees on large data set. Okay, so you don't, because it's very time complexity taking. Okay, so don't use that kind of, but you can obviously try it out at least. Okay, you can see some more assumption on the internet for this. Okay, great. So now we have talked about everything. Now it's time for getting into the implementation part of random forests. Okay, we will talk about random forest and decision trees. Okay, either way, I think that we have talked about decision trees, so I will talk about a random forest. Okay, on scikit-learn a library. Okay, so let's see the implementation. Okay, so I'm on my Brave. Okay, so here I will write. I started using Brave in some just days ago, just some days ago. So here, what I will write? I will write a random forest, scikit-learn. Okay, and we will see one project. Which will be doing all of this implementation with grid search CV, fine tuning the hyperparameters. Okay, so let's deep dive into this. Let's understand this concept. Let's see the implementation. A very finest explanation of a random forest right here. So let me take out my ink to go again, because it's my 12 days left until the license expires. Okay, so here I will take my pen. I will take medium. I will take a red color. Yeah. So you can go to this API, which is sklearn ensemble. You can also import by just calling from sklearn .ensemble, from sklearn.ensemble. You can go with this, and then you can use this API. So the first now you can use the random forest classifier. This the first parameter is n estimators. The first parameter is n estimators. N estimators is the number of decision trees that you want. Okay, like what is the number of base models that you want? What is the number of base models that you want? So you have this data, and you take this sample this data. So what is the number of? So here we usually take 100 decision tree as a default. Okay, but also this is a very important hyperparameter. So you fine tune it using a grid search CV or randomized search. Okay, we will see implementation of these two. Okay, so you can use this is the number of decision trees. After you have, what is the criteria? What is the criteria to use in a decision tree? What is the attribute selection criteria? So the default is Gini impurity as the best impurity. Either you can use entropy, but it's computation a little bit expensive, means time taking. Okay, you can the default is Gini impurity. Is now what is the number of depth of your tree? The minimum number of samples required to split, and the maximum depth of the tree to stop. Okay, then the nodes will expand. Means if it is none, then it will it has a high chance that it will overfill. Okay, now it is also hyperparameter. Minimum sample is split with number of samples required to split an internal node. Means what is the minimum number of samples to split? Okay, samples means what is the number of data points. Okay, then you have, let me delete this again. Then you have oops, where is my pen? Then you have minimum sample of leaf, which we have already seen. Max features means what is the you want auto or a square root or log. You can read the documentation. impurity. Then bootstrap. Bootstrap obviously equals to true. It involves bagging with the row sampling, with the column sampling. OB score, which is out of bag data points, which is out of the bag after sampling, okay, which is false. N jobs, if you take this n jobs equals to -1, if you take this n jobs equals to -1, then it will obviously understand your codes, and then it will run parallelly. Okay, it will run parallelly. It is fast if you take n jobs equals to -1. Usually people take. Okay, verbose, I think it's for printing out something texts. Okay. Now you can see the class weight. Let me see, I've also forgotten about class weight. Let me see. Class weight is, yeah, verbosity when inferring and predicting. Class weight is just the weight associated with the class. Okay, so it is obviously in the default is a none, but you can see how it is calculated. Okay, it's not max samples. It bootstrap equals to what is the number of a max samples. If you set it in none, then the default is the x dot shape 0, the number of the samples. So you can set some max samples. Okay, so you have some attributes. Base estimator, the child template used to create the collection of fittest sub-estimators. Then you have a number of classes here, number of features, the number of number of outputs when a fit is performed. The feature importance. It is also, you can use feature importance, this attribute, to understand what is the number of feature, means what is the importance of your each feature in your model, means columns. OB score, if it's obviously it will give you in the float value. Okay, so that's the decision tree, random forest, and you can see more about this into here, and you can read about attributes. And this is how the feature importance looks like. Means you can also plot it like this. You can also plot it to show which feature, and you can use it for feature selection. Okay, great. Let's see, the second one is a random forest regressor. Let me see. Yeah, there I am under the same path. Okay, so let's see again. It's very similar to classifier. It's very similar to classifier. Here we have an estimator which is number. Oops, I don't know why it is very bad. Here we have number of estimators, criteria to be MSE, RMSE, MAE, okay, max step, minimum sample width, bootstrap equals to true, obviously take this, okay, OB score equals to false, you can take yes or no, okay, summer default you can read is quite similar to that, and max sample is none, and it takes a default as x dot, so I don't know why it happened. Max depth is x dot shape, the shape of your, okay, of your samples. Okay, so that's the basic intuition behind this, and max sample is also one hyperparameter. Great. So we have talked about a lot about bagging, and we have spent 1 hour onto this. Now you can see some more attributes. You can see some more attributes over here to understand it much better. So let me show you one diagram that I found very interesting. Okay, so you can see some examples using random forest regressor using stacking. So we will also see the stacking. Okay, stacking is also a very good technique as a Kaggle winning technique to use. Okay, but here you can see that we only have MSE. We don't have RMSE. Okay, so RMSE is not default. You have to make your own function for RMSE, just squaring the root your MSE. Okay, but you cannot use, if you want here, your RMSE. Okay, you have to make your own. You have to make your own. I don't know why it is not running well. I have to complain this. Okay, I think this. Okay, so for RMSE, you have to make your own. Okay, but here you cannot use with this library. Either you can make a pull request or on scikit-learn API. Okay, just adding your own RMSE. Okay, great. So now we have seen these algorithms. Now we have seen, yes, I'm going to quit. So now we have seen extremely random. There is one more left, which is extremely randomized trees. I just forgot. Extremely randomized classifiers. A scikit-learn. It's obviously in scikit-learn because it's a new release of scikit-learn. Let's see this out. Let me open it again into Go. It's very important now.
So here again we have n estimators, criteria, max depth is just the same, and then we have bootstrap equals to false. Here bootstrap equals to false, it should be true. You can make this as a true, okay. Then we have some more odd to square root, etc. You can, it's just the same as that, but there is some difference. That is that I've just told you that we choose randomly. What we do, we choose randomly, a sample, and then we take out the sample epsilon. Okay, so that's what we do in a random forest or extremely randomized classifier. So let's see for regressor, and regressor is just the same. I think that I'm not correct over here. Okay, let's see regressor, and here the same thing over as we have seen, and here bootstrap equals to false. Your end jobs is jobs that you understood to run trivially parallelized to create that option. Okay, great. So now we have seen about a random forest, and I hope that you understood everything here. Okay, so now in the next subsection we will talk about boosting. Now I hope that you will understand that also. Okay, so let's wait at the next section. Till then, bye bye. Okay, so now we will talk about another ensemble technique, which is boosting. Okay, so boosting is one of the most popular as bagging, that we have already talked about bagging. Just I will recapitulate something about bagging that is necessary. Okay, so we have talked about bagging, and now we will talk about boosting, which is one of the technique of ensemble learning, and I really hope that you will enjoy this section. And in boosting we will talk about something called as gradient boosting, and then I will just give you a geometric intuition, or I will just show you the implementation of adaptive boosting, which is often called as AdaBoost. Okay, then I will talk about extreme boosting, XGBoost. Okay, so these three algorithms means XGBoost works best in some cases. XGBoost works best. Okay, so gradient boosting also works best, but it is also works best. So we will see these three. Okay, so let's start with this tutorial, but before that I just want to tell you that you can do the problem set, which is on GitHub, and you can subscribe the YouTube channel just by going to the https://youtube.com/c/newera, because this highly motivates me to make content like this for you all for absolutely free. Okay, so you can go to this New Era to subscribe this YouTube channel with 500 just I have 500 subscribers. Soon putting a deep learning tutorial. There's an announcement coming up soon, putting a deep learning tutorial soon. Okay, so let's start with this tutorial. And okay, so first of all, what is bagging? What is bagging? That we have already talked about. You can rewatch that bagging section if you want, maybe in a fast way. So bagging, we have low bias model, and high variance models. Okay, so our base models usually have low bias and high variance. Low bias and high variance means our base models usually have this low bias and high variance, and using bagging we reduce this, we reduce high variance, we reduce this variance. Okay, so our output will be, after applying bagging, we have our low bias and low variance model. Okay, so what we were doing in bagging, we are just simply doing the column sampling as well as the row sampling. Means we are doing the column sampling as well as the row sampling in case of random forest, but it is just take an example of random forest, and then we do the aggregation. Okay, so that's what we are doing. And let's see just a recap what we do. We have this large data set, DN, and then what we do, we simply divide this data set into subset of a data with the replacement. So I hope that you remember what is breadth replacement, that the data which is here, the data points which is here, it needs not to be different here. It can be same in the second data set also. Okay, so you sample endpoints, then you again sample endpoints with the replacement, then you sample endpoints So you take in 3 subsets of your data, and then you train your model onto this data, like M1 onto this data, maybe logistic regression, maybe linear regression, or maybe support vector machine. So you have 3 models, and then if it is a classification problem, you simply take the majority of votes that this particular example is of a particular class, or if it is a regression problem, then you do the average or you take out the mean or a median, okay, in case of regression. So that's what we are doing. And in random forest, these are called our base models, and in random forest we have our base models as a decision trees. Okay, so this usually helps in reducing your bias, okay. So that's the bagging. So let's see what we have in boosting. Boosting is just opposite in case of bias and variance trade-off. So just now I think that you know why we have learned bias and variance a lot. Okay, so in boosting we have low variance, in this case we have high variance, but we have a low variance high bias model. Here our model is underfitting. We have high bias model. Okay, so it is not performing well on the training set. Okay, so here we have a high bias model, and then what we do, we additively combine. What do I mean with this? This is a very great question. This is what we do. And here in bagging, we are doing the randomization, we are doing the bagging, means column sampling, then row sampling, then we have aggregating the model. Okay, but in boosting we have additively combined. That here it combines the weak, it converts the weak learners, weak models into a strong model. Okay, so different weak model tends to be a great model. Okay, just we will see how it tends to be a great model. So it is just combined. So let's see the core idea. So the basic idea of using boosting is to reduce bias. If you have a high bias model, then you likely to use boosting to reduce the bias of that model. Yeah, there is some other techniques also that we have already seen, but it's just we use boosting to reduce the bias. Okay, so let's see the basic intuition about boosting. So let's take an example that you have your data, you have your training data. So I'm just writing my training data. Where do I write here? You have your training data, which is your training data. I'm just writing train D. Okay, this is a supervised learning and a supervised learning technique. So you have xi and yi, which is a label, and it goes I equals to 1, or we can write I equals to 1 all the way down to the maybe m. Okay, here m is the number of training examples into that training data. Okay, and then you make a model, M1. So let's take an example that we have made a model M1 that's simply a function f of that is simply a function f of x, which is our hypothesis. Okay, so now what we will do, this is the core idea behind boosting. So you have a training data, you have your training data, like which is your training data, and you train your M1 model onto that. Now what you have seen, you simply take out the error. Means the cost function, the loss. Okay, loss for ith example. So for each example you have yi, which is a ground truth, minus your model predicted value. Model predicted value is f of x, which is when you input x, then you get your output. So model predicted value is f of x. Okay, this will give you the loss. Okay, the loss for if it is 0, then it is very good. If it is large, then it is very bad. Okay, so here we are using just a simple regression loss, means just a loss. So if you add a summation over here, I equals to 1 all the way down to the m yi minus f of x, then this is the like MSE, but you do a square in MSE. But now because of the gradient descent to effectively compute the derivative, but here you can just see just as a simple conversation what we just we are taking the loss for each training example. So here let's take an example that we have taken a loss, and then what we do, and then what we do, we train our model onto this loss. Means we train our model to reduce this residual error, to reduce this residual error. Okay, we only focus, or we more focus onto the data which is misclassified, or which has a very large error. Okay, so we focus on that. Okay, so what you do, so you want to reduce this error. So how you want to reduce? You want to make a model M that is given xi, means you fit this residual. So let's take an example. I'm just going to take an example to make you this statement clear at what you do. So let's take an example that you have a regression problem statement. So you have a regression problem statement. Oops, I don't know why I'm making a bad, yeah, why my x-axis is not working great. Yeah, here is my x-axis, a bad x-axis, and you have a x like this, and then what you have fit in a maybe this line. Okay, a straight line. So here for this training example, the loss will be very high, so it will more pronely start focusing on that, and it fit on that residual covering this. Okay, so maybe it will do like this. Okay, it will also cover this if the residual is very high. So it always tries to minimize that residual. Maybe it can make a non-linear, either the example is too much lengthy, but either it can make a non-linear hyperplane. Okay, so what we do, we fit our error. So we make a model M1 that minimizes the error by fitting onto the error. So here is Li for I equals to 1 all the way around to the M. Okay, for each training example we are fitting a model. Okay, so it is more pronely focusing on the data which is either misclassified or which has a high the particular MSE or MAE. Okay, if it is a regression problem, then we take MSE or which is misclassified. So it is more pronely focusing on that. Okay, so that's the basic intuition. So let me make you the full equation how it looks like. So you have f of x with k, means and some just a model, a big model, means f of x. Okay, for each training example I equals to 0 all the way down to the k. Okay, all the way down to the k, you have one alpha times your model, ith model. So you will not only have one model, you have in first model that fits some, that second model that covers that fits that residual, then third model that fits that residual from this model, fourth model that fits that residual from this model, means error. Okay, so we have a different models. So we have a large model, this k, and we go through each and every model with some just assume it's a lambda. So we have this just as of now, just consider this as we have computed this somehow. So we will see how it is computed. Okay, we will see when we learn about some gradient boosting. Okay, so just assume that we have some just a lambda, a constant. Okay, here this f of ix that is trained to fit the residual, from the previous model. Okay, from the previous model means this model, this M2 trained to fit the error we get on M1. Okay, so this model may have some different thing. This model is able to correctly classify the error from this first model. This M3 is able to classify the errors from the M2. So like that. Okay, so that's the basic intuition behind boosting. Okay, so I think that you have understood about boosting. So now this will end it up, this function will be ended up giving you low bias and low variance model. Okay, but there is a problem. So you may think, hey Ayush, can you name a problem? Yeah, sure, I'm here to name. Okay, but before that you can take a break if you want, because it will just take more 1 hour to complete. I think so, it's my approximating time. So it will take 1 more hour. You can take a break, or you can do just a problem set if you want, but start with a section and then complete a section, then see the problem set, then see some challenges given to you in my GitHub, and I really understand that you will be able to do that. Okay, so here you have this one. First you have a training data, then you have a loss for each training example, then each model tend to fit the residual error given from the previous model. Okay, and in that way they end up being a low bias model. It's very good on training set, but there is a problem. The problem is that if it is too much good on the training set, means only 100% accuracy on training set, then what will happen? It will start overfitting. New training example will come, then it will able not to classify or detect a good prediction. Okay, so that's why we have to take care of how many number of base models, so that we have a lambda. We will understand this all. Okay, great. So we have understood this, and so the core idea behind bagging is not too much hard. It's just saying is we just use bagging. Sorry, it's boosting. It's boosting. The core idea behind boosting is to reduce the bias on the train, like that. Okay, this converts the weak learners into the strong learners, and here we have a good fine-tuned models which is converted into majority of votes and then in bagging, like that. Okay, so let's see. So that's the basic intuition behind boosting. So there are some of the techniques that we'll study about, like a gradient boosted decision trees, which is often called as GBDT. Okay, this is because in random forest we have our decision tree, and here in gradient boosting we have our base learners as a decision tree, and gradient boosting we have a base learner as a decision tree, and then we have adaptive boost, which is often called as adapt boost, which is a little bit more advanced version of gradient boosting. Then you have extreme boosting, which is XG boost. Okay, which is again a family of a good algorithm, and it's always outperform. It's very powerful algorithm, XG boost, as I've seen so far, and I will show you the implementation of XG boost also with some. I will show you how it is implemented and everything in this section only. Okay, so. And that's the basic intuition behind bagging, and I really hope that you understood bagging in detail. Just to recap that and why I'm saying bagging, it's a boosting. Okay, so boosting here, in boosting we have low variance and high bias model we additively combine in which we convert our weak learners into strong learners, and the core idea is to reduce the bias. It simply means that we want to improve our error on the training set. Okay, so that's the basic, and we have 4 which we'll cover in this section, which is gradient boosted decision trees, adaptive boost, then we have XG boost. Okay, so I think that you understood about boosting. Okay, so now we will talk about gradient boosting, which is again a good very fantastic, brilliant algorithm. Okay, so to just use in internet companies or very big companies, which is used in ML in production. Okay, so which is usually launched in 20s, these algorithms. Okay, so we'll study in detail to make you understand each and every concept of gradient boosting, and then we will see the implementation, then we will see the adaptive boost, then we will see the XG boost, and then we are end up with this ensemble models. Okay, then we will go with unsupervised learning techniques. Okay, so let's start with gradient boosting. Now we have talked about the boosting, the basic intuition behind boosting, what actually the boosting are. So now I will start talking about gradient boosting. Okay, so gradient boosting is one of the most powerful algorithm that I've seen so far. One of the most powerful algorithm which is yet to just learn. It's very to have a good in your toolkit. Okay, so I'm on a Wikipedia page. Which I found a great algorithm, which is again which just tells you a very good intuition behind gradient boosting, rather than just I make use of my blackboard. Either way, I will make use of my blackboard over here. Okay, so what is gradient boosting? This is a great question. So gradient boosting is a boosting algorithm that just converts the weak learners into the strong learners. Okay, so let's start with this gradient boosting, and you can search for gradient boosting wiki, and then you will see the gradient boosting Wikipedia articles, and then you can read the full articles. Either I will cover everything in short period of a time, but I've already covered some of them, and of my I have covered more than this Wikipedia. Okay, so I will give you some real world examples of gradient boosting also, where it is used and everything. Okay, but first of all, let's understand this algorithm. Okay, so let me see my pen is at least working or not. I hope that this is working. Yeah, this is working great. I'm just happy that my ink is working. Just if the ink to go, if you're watching, please help me to improve this. It is not that much good. Okay, just to improve this, but it's very good tool. Sometimes it lacks, but it's very good tool. You check it out, it's very good, great, for free. Okay, so you have this training data, which is a input training data. You have this input training data, which is the set of, let me write the training data, which is simply your xi and yi, and simply goes from I equals to 1 all the way down to the n. Okay, or m, which is our, let's stick to our formal notation, which is m, which is the number of training examples, number of training, or the size of our training examples. Okay, so that's our given data, and we have a differentiable cost function. Then we have a differentiable cost function. Okay, so what do I mean by differentiable cost function? Differentiable cost function means that this cost, because we take out the derivative of our cost function, we take out our derivative of our cost function with respect to some value. Okay, so let's take we are taking out the derivative of our j of theta, partial derivative over j of theta. Okay, so that's the basic that's the differential equation that I know. If you're a calculus student, then you might interpret that we have a differential. But if you're not able to get what is this differentiable, feel free to leave this differentiable. Just think that it should be derivable. Okay, for our gradient descent, or we will because we have to take out the derivative of this particular loss function with respect to some weights. Okay, so we are given a training set, which is dtrain. We have a given a training set, which is value xi and yi, which goes from I equals to 1 all the way down to the m. Okay, where is my eraser? I think that this is my eraser. Yeah, I equals to 1 all the way down to the m, and then we have a differentiable equation is given. So let's stick to the j of y f of x, and this is simply just the error, means just a minus your motor predict value for each and particular examples. I equals to 1 all the way down to the m, and then we square it all up. Okay, so that's our cost function. Maybe it can be mean square error, or it can be log loss for classification, etc. Okay, then we are given the iterations. Then we are giving the number of iteration, which is m, and m here is the model. M here is the base learners. M here is the number of base learners. Number of base learners. Okay, so this is the number of base learners, which is m. Now let's start with the algorithm. So what this algorithm tells you, so let me choose the different colors so it might make sense. So we initialize our model with some constant value lambda. In that case we have in alpha, but now we had changed a little bit that we have our favorite lambda. Okay, so we have to find lambda. Okay, let's just think of it as that we have a lambda. That we have to find that lambda that minimizes this training error, this loss function. It should be told here, but I told you here just in my excitement. So what you do, you initialize your model with some lambda that minimizes this cost function. Okay, so this first to initialize this, and we will see how this lambda is computed here. But first of all, you initialize it, and then what you do, you iterate through each and every model. Okay, first you do this for first model, then you do again for second model. Means you apply a for loop where for m equals to 1, first you 2m, means you want to go 1, 2, 3 all the way down to the m. Okay, so you do this, and then okay, so here then what you will do, then I hope that then you initialize your model, then you compute the residuals, you compute the pseudo residuals, and then here it is named as r subscript I and m here denotes the number which model, and I here for each training examples. Okay, so here you compute the I and m, and then you take out the partial derivative. Oops, why it is not working? Partial derivative. Hey God, please help me. The partial derivative of your cos function yi, and f of x. So this is your loss function with respect to this function. Okay, f of x, your model predicted value. Okay, and then you want to fit your model onto your previous residuals. So for you go to I equals to 1 all the way down to the n. So here you take out for f of x, means means here you are fitting your model, means just you are making the model to be f of m minus 1, means the previous model. Okay, so compute those residuals, and then you fit the base learners. Okay, that I've just showed you in my previous just in a boosting, that we fit the residuals. Holistic example, we have m1, m2 and m3. We have taken the residuals, and here give some residuals. This m1 is trained to fit the residuals from m1, this m2 trained to fit the residuals from m2. Okay, and this is m3. Okay, so it is trained to fit the residuals of m2. Okay, so then you fit a base learner or a weak learner. Let's take an example 3, closed under scaling of h of mx. Here is your two residuals, to pseudo residuals, means you fit the learner to fit the residuals from the residuals got from the previous base learners. That is to train it using the training set, this one. Okay, and now here RIM is in our case, which is LI on M model. Okay, so then you fit your model that I've already showed you, just similar that we have seen, and then you compute the multiplier, which is a constant multiplier lambda m. For each model you have lambda m, okay, which is a one-dimensional optimization problem. For solving the one-dimensional optimization problem, so you may ask, yeah, Yush, why do we are choosing this lambda m? So for solving one-dimensional optimization problem, going into 1D optimization is out of the bound of the course, but you can see on the link. Okay, how you compute lambda for each model that minimizes the loss of y, which is ground truth, from the previous model plus lambda times our just model that we have now. Okay, now what you do, you update the model. Now you update the model to be fitted by the model that fitted the previous residuals. Okay, so f of mx, here m is our model number, means model number, then we have this f of m minus 1 previous model plus lambda m, which is some constant for solving the one-dimensional optimization. Okay, because we are taking the partial derivative of our loss function yi and f of xi with respect to f of xi, and f of xi is our model predicted value. Okay, times h of mx, and then you get your output as a f big model m big model all the way down to the x. Okay, so here when you cover all of this, when the loop is done, then you get the final model, which is fmx, that is simply f of m minus 1x plus the previous model. This previous model plus the model that we got after solving this 1D optimization problem. Okay, so that's the gradient boosting algorithm that I really hope that you understood. But let's just as a recapitulation to help you understand it a little bit much better to understand this problem. Okay, so what we do, let's understand what we do over here. So we simply, first we have a given our training data. We have a training data xi and yi going from I equals to 1 all the way down to the n, and n here I just hope that it should work now, and n here is your number of a training, your number size of your training set. Then you have a differentiable loss function with the number of base learners that you want. Okay, then you initialize the model with some constant. Okay, then you apply a for loop. In that for loop, you take out the residuals. For and then you name it as a r subscript I, which is the number of a training exam, the index of the training example, and m is your number in the index of your model. Okay, minus the taking of the derivative or partial derivative of your loss. Okay. Okay, and then you fit a base learner or a weak learner, because it just makes you a weak learner to the strong learner. Okay, to closing under h of mx, which is your got from the weak model, means you just fit the base learner to the residuals. So it's simply that you are going to fit your model into xi and your li, which is simply li is this. Okay, now you compute the multiplier lambda subscript n for each particular m, means the model index, for solving the one-dimensional problem. So it's just you find the lambda m that minimizes the loss that you get yi comma the output from this model. Okay, this is the whole model now. This is a previous model, this is a new model that is fitted to fit this residual. Okay, and then you update your model. Okay, then you have to output a big model, which is f of mx, that is simply this fm minus 1 of xi plus your big model. Now you just, after your full iteration, you'll be ending up being a big model. Okay, so that's the basic intuition behind gradient boosting. I really think that you understood about gradient boosting. Now it's time for getting into the something called as a regularization and shrinkage. Okay, but before that, why do we need even regularization and shrinkage? So why do we need, as we have already talked about, that we have in boosting, we have high bias. Let me see, the recordings are on. Yeah, oops, we have our high bias and low variance problem. Sorry, high bias. So we use boosting to reduce the bias. So high bias is just doing bad on training set. So we just, after each iteration, we are fitting the previous model residual. So it is making a null. It means it is doing very good on training set. So very good on training set. So it may happen that it may start overfitting, and our low variance goes to high, where going to high variance, means our low variances start increasing, and now it's converts to high variance. So that actually can cause overfitting. Okay, so for avoiding, we add regularization and shrinkage, which is again shown in the Wikipedia page. Let's see. So here I think that I can teach you better than Wikipedia page. Okay, so you have this big model, f of m x, which is here you have a h0x plus you do for I equals to 1 all the way down to the h, is number of your model, lambda m, or you can say m, the number of a model. Okay, h of mx. Okay, so that's your model that we, and then what do you do then? If the number of a base models increase, means it will fit more residuals. If it will fit more residuals, then your overfit will then it will start overfitting, and if it is start overfitting, then your variance will start going up. Okay, so that will cause the problem. So what you do, you shrink by a factor of there's a Greek letter that I even don't know, that is something called as a v. So let's assume that is a v, which is a parameter v. Okay, so we have our parameter v, which will help us, which is just a parameter for controlling it just shrinks to do not go that much, means it gives a weight. It is just a learnable parameter, just gives weight. And empirically it is found that v equals to 0.1 tends to be a dramatic improvements in your models. Okay, so that's why we use this v to be 0.1, and again your v should be in between 0 and 1, and it's found that v equals to 0.1 would be dramatic improvements in your models. Okay, so you add a new weightage to that model, means to this model. Okay, you add weightage to this model that I've just shown to you, add weightage to that model, and that's called the learning rate, for how much rate it should learn. Okay, so that's we add v to that model. So let me add that. So what you do first, you just shrink your model big model by going f of m minus 1 x plus v times lambda m h of m x, and v here is in between 1. Okay, and empirically it is found that v equals 0.1 works best. Okay, so that's about gradient boosting, and I really hope that you understood this also. Okay, so now it's time for we will take a look at implementation. Okay, so now we will take a look at the implementation of gradient boosting classifier and gradient boosting regressor. Okay, but before that, let's see the training time complexity of your model. So let's recall of decision trees. And decision trees, we have our training runtime complexity. So here we, and decision tree dt, I'm writing dt, we have all n, oops, why I'm writing this, n log d, and here d, and then a random forest, you have o order of n log n, number of a decision tree means k. Okay, now when gradient boosting decision tree means here we just take our base learners as a decision tree rather than different models. So we have o n log d times the number of models. Okay, so that's the basic time complexity of your gradient boosting decision trees. Okay, great. Now we will see something called as now we will see the implementation of this gradient boosting decision trees in scikit-learn API. Okay, so let's see. So let me open gradient boosting implementation. Okay, in sklearn. Let's see. Yeah, here we found. Just wait for a few seconds, it's just loading. Okay, great. So now here you are on a page of scikit-learn API gradient boosting classifier, and then you can see over here that now let's see some of the parameters that we are over here. So here that you have a loss, which is deviance. Deviance refers to the log loss, and exponential refers to the which is just the adaptive version, which is if you set exponential, then your gradient boosting will be called as a adaptive boosting or ADA boost. Okay, so in adaptive boosting, it is more pronely, we will see the implementation. So in ADA boost, it is more pronely focusing on unclassified. Okay, more pronely focusing on unclassified, but it's not being used too much. Okay, so we have a loss equals to deviance, which is used as logistic regression loss or log loss. Okay, then you have a learning rate, means the rate to shrink the contribution of each tree by learning rate. Okay, so this is used to reduce your variance. Okay, so that's your model does not start overfitting. Okay, so this is your learning rate, which is default 0.1, and leave it 0.1. Okay, because it's found that most dramatically that they work best in most of the cases. And then you have a number of estimators, which is number of decision trees, subsample, criterion, min sample split, min sample leaf, min weight fraction, max depth for each tree, min impurity. These are particularly for each trees. And then you have let's see something more of that we have a validation, eternal change, and then total CCP alpha. That's not too cool. Okay, so we have this, and these are some of the hyperparameters that I know that you had understood everything. Okay, so you can see more about this in the parameters in detail here, but we have already talked about decision trees already. Okay, so let's see the implementation. Means the implementation of this gradient boosting is just one line of code, which is here. And you can use predict probability. It simply gives the probability of that being true, okay, for that class. Okay, so first you import from sklearn.ensemble, import gradient boosting classifier. Here is your data, means, and then you call your with n estimators, learning rate 1.1, okay, 1.0 max depth, random state, and then you fit it, and then you get your score. Okay, so that's the basic intuition behind a gradient boosting classifier. Okay, now let's see the gradient boosting regressor. Gradient boosting regressor, regression in sklearn. Okay, so this is a very good to learn from the documentation. Okay, this is very good to learn from the documentation. So let's see. Okay, here we are on documentation of a scikit-learn API. Now what we will do, we will just let's use the pen, and then you can see over here that we have a loss function to be optimized, means L as that refers to the least squares, LAD means least absolute deviation, is more robust. Okay, so we have a Huber, then you have a quantile, but the default is LS. Okay, then you have a learning rate, how many, this is a for shrinkage, then you have a number of estimators, then you have subsample, criterion, min sample split for each particular decision trees. These are for each particular decision trees, and then the same thing that we have seen so far. Okay, so now we are this is the basic for decision trees, and I hope that you understood. Okay, now let's see the implementation of this. I'm a little bit going far because I have to teach also that XG boost and ARA boost. Okay, so you just call the gradient boosted regressor, then you call your train test split, then you split your data, and then you call your gradient boosting regressor with the default parameters. Okay, then you fit it. Okay, and then you simply do the gradient boosting regressor, then you score it, and it uses the sum scoring parameter, means the log loss, or sorry, not log loss, maybe it uses R2 or MSE, you can see. Okay, so that's the basic intuition behind how we implement regressor and classifier, which we will do in project just to showcase you how you can assess from documentation. It's very good to learn from the documentation. Now it's time for learning from now it's time for that we'll learn about XG boost. We will learn about but before that let's learn about ADA boost. Okay, ADA boost. So let's see, I want implement sklearn. Okay, so if you set your loss to be exponential, okay, to be exponential, then it will be equivalent to ADA boost classifier. Okay, so it will set your loss to be like this, and it's just the same as that we have already talked about. We have two algorithms given by Sammy and Sammer, which is in Sammer, which is also for logistic regression, if you have seen as the scikit-learn API. Okay, so how you implement from ARA boost classifier, then you call this, and then you fit your model, and then you are done. Okay, it's very simple. I think that but just remembering the concepts is very, very important, because it's not always you have to implement maybe your own something algorithm in your company. Okay, you may think, yeah, you can't we just study the implementation? No, you cannot study. Okay, but scikit-learn API is very, very slow, very slow. But it's great. But what you can do, you have to in some companies for production, because it's a Kaggle winning algorithm, that we need to understand what is happening, how we can tune the hyperparameter. Okay, so here you can see again for regressor. Okay, and here you have a loss equals to linear, and then you have a square, and then you have exponential. Okay, and here maybe we do have a not loss. You can see state the number of a classes, how many number of a class with a classifier. Okay, so now we know about this, and I really hope that you understood the following. Now it's time for learning about extreme boosting. One of my favorite, but I think AdaBoost is not used in production. Not uses too much in production. Maybe I'm not right over here, but I think so. Okay, so now we will learn about XGBoost, which is one of the most popular algorithm which I've seen so far. Okay, okay, it's a good algorithm. It's a good algorithm, but it's one of the best algorithm that wins your Kaggle competition. Okay, so now we will see what XGBoost does. It's just the advanced version of gradient boosting. It does have gradient boosting decision trees, plus it has randomization with row sampling plus column sampling. And so in gradient boosting we are not doing this, but it's at randomization, which is row sampling plus column sampling. So that's why we name it as a extreme gradient boosting, and it works best. Okay, it works brilliantly in some cases in machine learning problems. Okay, but it needs fine tuning a lot. Okay, so you have a gradient boosting decision tree. Now you have a row. It's just how it differs from gradient boosting decision trees. You do the randomization by doing feature bagging, and then you have a row sampling. Okay, and it's just for a simplicity. Let me explain you what we tend to learn about this. What we do, we simply sample the rows as well as the columns for our data. Okay, and specifically for bagging we don't do columns, we don't do column sampling, but in a random forest we do both. So in XGBoost we do the gradient boosting decision trees as well as a random forest plus column sampling. Okay, so that's what we do, randomization, and that's the XGBoost. Okay, so now we will see in detail what actually the XGBoost implementation, XGBoost, from the official documentation. But it is of course implemented in the implemented in Scikit-learn API. But it's very good to use because this is fast actually. It is fast actually. It's very good to learn from here rather than there. Okay, so I think that we can get the Python package, because we have different package now. Setting parameters. Oops, where it is XGBoost Python package. Okay, so here we have some parameters in XGBoost. I think that my Brave is not working. I have to again switch to my favorite Chrome. Why I have switched to this? It's bad. Brave is actually not good for me. And in some cases, actually, who am I to say bad? But it's good. But it's all, of course, sometimes it does very bad. Okay, so let's see some of the parameters. So we have different packages that already been implemented this algorithm. So here you have booster, which is GB tree, means gradient boosting tree. You can use GB linear or Dart. Means we usually use GB tree. Then you have validate parameters. Default to false means it's just you want to validate your parameters or not. Then default to maximum number of threads. Then you have an evaluation metric. Then eta is learning rate. Okay, is 0.3. Okay, gamma, which we have seen, which is the constant, which is 0 as default, and is just we just randomly initialize means, and then we find a good like gamma. And then what is the max depth for each tree, and you can read the documentation over here more. Minimum child weight, minimum delta step means what is the step should one maximum delta step we allow each leaf output to be. It means there is no constraint. Okay, if means it's just like that. It's just helping you to not too much proning to overfitting, means more robust model. Okay, so you can see your lambda means L2 regularization like lasso, and this is for regularization, that is alpha regularization. Okay, then we have a tree method, which is XGBoost construction algorithm using XGBoost. You can see the reference. You can see obviously see the reference. It also supports hist and etc. Then it's have a scale pose weight. updater, which is process type, grow policy, maximum number of leaves, but it's default to 0, to be added. Okay, so max bin, predictor. Then we have a GPU, CPU, but this needs a lot of fine tuning. It takes a lot of time in CPU. Okay, so we have this much, and you can see more about this. It's a very long set of parameters, but we usually use the main parameters that we have listed. Okay, so you can see a Python package. First one, you want to install it. You can just pip install xgboost, and then you just call xgb.dmatrix. First you convert that into a D matrix, then you do that. Means you can do also for pandas using the scikit-learn API, but it's okay to use it. But you can see over here implementation sklearn. It's also for regressor that we have seen. I think that they have removed. I think not. They haven't removed. No worries. So you can see from here how it is used and how we train this model and how we save this model. It's just like a neural net. As you know that TensorFlow has also added decision trees and like that. Ensemble Learning started adding, because one of the most powerful algorithm in Ensemble Learning. Okay, so we have seen a lot in decision trees. Okay, in Ensemble Learning, like bagging and boosting. Okay, so now one last step is left, is stacking of your stacking. Okay, so after this section we will start with stacking to help you to better understand what actually stacking is, and it will obviously help you. Okay, so we have seen a lot of applications of this, and I really hope that you enjoyed it also. Okay, so this section is just amazing. We have learned about boosting, we have learned about gradient boosting, then you have adaptive boosting, then you have learned about XGBoost. Okay, and so one of the projects will fine tune, will use XGBoost, adapt boost with fine tuning. Okay, one of our project. Okay, so that's it for this section. In the next section we'll start with stacking. It's a 20-minute session on stacking will take, and then we just with some summary or revision of Ensemble Learning. Okay, so let's meet at the next section.
Okay, so now we'll talk about our last Ensemble Learning technique, which is called stacking of our models. Okay, so we will see the implementations of stacking, and we will see how it works and how it changes your accuracy. Okay, so let's recall something called as bias and variance of our bagging and boosting. Okay, so in bagging we have high variance and a low bias trade-off. Okay, and in boosting you have high bias and low variance trade-off. Okay, so remember these two for stacking. Okay, so here I am on my ML extend, which is a library for implementing the stacking classifier. Okay, so we will see the implementation of this stacking classifier, but before that we will learn how actually stacking works. You can get to this page by just going ML extend stacking classifier and click on the first link. Okay, so let's start. So here is our data set. So let me take out my favorite ink to go. I hope that you remember my favorite ink to go. Sometimes I roast it also, but here it is very good just for annotating these kind of things. Okay, so here let me take the pen. As of now, let's take red, which I like a lot. Let's take a medium. Okay, great. So here is in bagging what we were doing. We have a large training data. And then you are multiplying, or you are just taking out a subset of this data, D, N1, D, N2, D, N3, with the replacement of training the decision trees, or maybe some scene-based learners. Okay, so in stacking we have different base learners. We take out the data, okay, and then we train our model, different model onto the each data. Like C1 is a model which is trained on different data, then again means on the data D1, then C2 is trained on D2, all the way down to the M. Okay, so here C1, C2, all the way down to the CM are different models. Okay, so what do I mean by are different models is quite simple. Let's take an example. Let's take an example that you have your favorite logistic regression. Okay, you have a logistic regression. You have a logistic regression as a C1. Okay, as a C1. Then you have your support vector machine as a C2. Then you have your favorite naive-Bayes algorithm with maybe with extensive fine-tuning using grid search. Okay, so here we have C3. Here we k nearest neighbors, which is C4. Okay, with extensive, with maybe k equals to 4. Okay, with extensive fine-tuning. Okay, so we have 4 base learners, and we have a different logistic regression, support vector machine, naive-Bayes, k nearest neighbors, and there are 4 different models. Okay, and a train of different thing. Okay. And the major difference between the bagging and boosting is in bagging that I've told you to recall. Bagging and stacking is in bagging we have high variance and low bias models, which is a base learners, and in bagging we use bagging for reducing the high variance. Okay, so base learners are usually high variance and low bias, the trade-off between them. Okay, so what is the difference between stacking? In stacking, our base models or base learners are highly well tuned. Okay, highly well parameter tuned, and they have a good bias and variance trade-off. Okay, so in bagging, we have high variance where our base learners are not that much good, and also in boosting, our base learners are not that much good. But in stacking, our base learners are very good with extensive fine tuning. So maybe you have changed the logistic regression fine tuning with a learning rate, support vector machine like C, your regularization parameter, and your gamma, and then maybe some of the other parameters. Okay, in naive-Bayes algorithm you have also done, it's not required, but you have done some extensive fine tuning. You have k nearest neighbors, we have chosen what is the number of a k. Okay, so you have done an extensive fine tuning of your model. Okay, so that's what I mean. Here I'm taking one classification example. Okay, so here what we are doing here, what we are doing is just the models are highly trained, means highly fine-tuned. Okay, very much extensive fine-tuning are very good models. They do have a very good bias and variance trade-off. Okay, and here it gives prediction. Let's take an example that C1 gives you a prediction as a y-hat1, then C2 gives you a prediction as a y-hat2, and all the way down to the y-hat-m. Okay, so each model gives your output. Okay, the prediction. Okay, so what you are doing, so let me do this. So as a motivating example, so can I delete this if I can? Yeah, let me delete that. So what you are actually doing is simply taking a training data, which is taking a training data. You are dividing your training data. Into subset of training data, D1, D2, and D3. For an example, let's take for D3. Okay, and you're training your base learners, which has a good bias and variance trade-off. Okay, the base learners are very good bias and very good model. They are not either low bias or high bias, because here in bagging, again I'm saying in bagging you have high variance and low bias model. And what do I mean by high variance? It means it performs very well on your training data, but it fails to generalize well onto the testing data. Okay, so that's why so that's why it's called high variance. And in boosting, it is underfitting. It means that your model is either underfitting because it has a high bias, which is not performing well on the training data, and low variance like that. Okay, so here we have intuition about bagging and boosting. Okay, so here we have a highly tuned model with extensive fine tuning, and then what you do, you take out the prediction y hat 1, y hat 2, y hat 3, y hat 3. Okay, after you take out this, now what you do, you train your model, you train your meta classifier, which is just trained on the predicted class labels from the base learners or their probabilities from their ensemble. Okay, so they are usually trained on these things, on the predicted class of our favorite classification or base learners. They will either take the class labels or the probability of being that class. Okay, so maybe 0.65, or in predicted class it may be 0 or 1 or 2. Okay, so that's what the basic intuition behind this stacking. But again, I'm very I will recapitulate you so that it works. It makes sense again. Okay, so what you do in stacking, so let's just for an example, in the stacking we are just taking a training data, okay, and then we are training, and then we are dividing our data into subset of a data, and then you're training different classifier onto that data. Okay, here we have a C1, here we have a C2, all the way down to CM, which is new data. Okay, new data we are training, and then what it happens, and trains our C1, C2, all the way down to the C3 and CM onto that data, and takes out predictions. And the major difference is, the first difference is that the bias and variance trade-off of the base learners in the stacking, is good. In the stacking is good. Okay, is good. Whereas in bagging we have high variance and low bias. Okay, and in And in boosting we have high bias and low variance. High bias and low variance. High bias and low variance. Okay, so that's the major difference. Next thing is that after you get the prediction from each of the model, because you have done a lot more fine tuning of your hyperparameter, you get your P1, P2, all the way down to the PM. Now you train a big or a meta classifier, which you usually call as S dash, onto the prediction of H1 of X, means the 1 classifier, second H2 of X, second classifier, all the way down to the HM of X. Either you train onto the probabilities given by these models, or the predicted class labels from these ensembles. Okay, and in bagging, we are aggregating the majority of votes. We are aggregating, okay, the majority of votes from that models. Then you are taking that as a final prediction by hat. But we have a different chance of here we have different approach. Okay, so let's take a quick look at the stacking algorithm. But I have already explained you just above, but just as a formal definition. Here you have your training data, which is usually xi and yi, which goes from xi equals to 1 all the way down to the m, where xi is the member of R, which has an n-dimensional, maybe it can have multiple features, and whereas the yi will be the member of the number of the classes of y. Okay, so that's the thing. And then what you do, and its output will be the ensemble classifier, which is edge dash, or a big edge. Okay, first what you do, learn first level classifiers, Means you learn T classifiers. Maybe it can be logistic regression, naive Bayes, it can be k-nearest neighbors, and one all the way down to the P, and P here is the number of Bayes models, okay, based on the distribution data D. Now you construct new data set. Going from I equals to 1 all the way down to the M, and then that contains xi hat prime by I, where xi is simply the prediction from the each model, from the each Bayes learner's model, okay, from the each models. Now what you do, you train your second level classifier. First you train the first level, now you train your second level classifier, and here it simply trains to make a hypothesis of train onto these models. And these this meta classifier can be anything. This meta classifier can be logistic regression, can be naive Bayes, can be k-nearest neighbors, can be support vector machine, any one model. And we are not aggregating, we are not taking mean, we are not taking anything, we are just training a second level classifier that is just trained on the output from the Bayes learners, and Bayes learners have a good bias and variance trade-off. Okay, so that's the stacking, and I hope that you understood about the stacking. Now I will just take a look at the formal, I would say the implementation of stacking. Okay, so you can see over here, the paper, which is in some of the research papers they usually call as a stacked generalization. You can in some research paper we call that. Okay, so let's make a simple stack classification. First, what you have done over here, we have simply loaded the data set from the sklearn data set, which is an iris data set, and iris data set is not too much hard. We have sepal, we have a sepal length, petal width, and petal length. Okay, so we have 4 features, and basis on that we have to predict what is the species of that flower, which is either can be setosa, versicolor, or virginica. Okay, so that's our data set. Now you can see first we import the model selection, which we'll see what it does. Then we import the logistic regression from linear model API and scikit-learn. Then we import KNN, which is again from neighbors API and scikit-learn. And then you import Gaussian naive Bayes from naive Bayes. I have not gone into too much of algorithm, because learning algorithm can just, you can see the Wikipedia. You are now capable of learning any algorithm. Okay. Now you just import the random forest classifier from Ensemble Learning, Ensemble API of scikit-learn. Now you import from MLXtend library classifier, import a stacking classifier. Either you have to first you have to install this using pip install if you have a Python MLXtend, but then you can do this kind of thing. Okay, where is my, let me delete this. Okay, after that what we have to do, we have to simply import the numpy as np, is alias, and import warnings. Okay, now you're going to ignore the warnings given by the models. Now first, your first model is CLF1, which is k neighbors, which with the neighbors of 1. If it is bagging, if it was bagging, then we have to, if it is random forest, we have taken only decision tree, but we are taking different models, and that's what makes it perfect. Okay, random classifier, Gaussian naive Bayes, logistic regression. Okay, now what we have done, we instantiated our object, everything. Now instantiate our stacking classifier, which is the number of a classifier will be CLF1, which is CLF k neighbors, random forest, which is the CLF2, and these three these three are CLF2, CLF3 are the Bayes learners. It will give output like this. Okay, now what you will do, you want a meta classifier, which will be the logistic regression, which will the logistic regression. As I've told, you can take logistic regression as a meta classifier. Okay, now you perform a threefold cross validation. Right, now you perform threefold cross validation. Now you perform threefold cross validation. Now in threefold cross validation, you are just looping through CLF as well as the label. It's zipping the CLF1, CLF2, CLF3 and SCLF. Okay, now KNN, a random forest, naive Bayes and stacking classifier. Now you select the best model. Now you select the base model by training each of the model, whether you are taking a scoring equals to accuracy. Now you check the accuracy, and you can see that this stacking classifier has around 0.4% of increase, as is better. I mean, it's quite better than this random forest. The stacking classifier works best in this case. Okay, and now what you can do, you can what happened? What you can do, you can actually plot the KNN. How it is plotting means the decision boundaries of the models, how they are plotted, the decision boundaries or hyperplanes. Okay, using the matplotlib. So let me annotate what it's doing. First you import the matplotlib, then you import the plot decision regions from MLExtend, then import the grid spec, then you import the iter tools, then you set the area, then you set the area. Again you loop through by jipping, and then you take out the product, and then you fit it, and then you plot it, and then you plot the decision boundary, then you title the lab. And lab here is just KNN, a random forest, naive Bayes and stacking classifier. Okay, after you plot it, now you are done with the stacking classifier. Okay, now as I've already stated you, either for training the meta classifier, you can use either this that I could say that maybe the prediction from the base learners. So you can either take prediction class or the probabilities as the meta features. Okay, so you can say that use proba equals to true, use proba equals to true, and average proba equals to false. Okay, and you can see here are a little bit of the documentation over there. Okay, great. Now we have seen this, and again the same thing is not too much harder. We are using the thing, and now we will see here is an example of stacked classification using grid search. It's your task is to do this, but I'm just going to annotate what the this kind of thing will do. Grid search. So here you are just first of all you are just now you will tune, you will have a good bias and variance trade-off. So you are going to check between 1 to 5. You are going to check, and then meta classifier, and then fit the grid search. You find the best grid search. Then you plot the results. Means you take out the results. What is the best parameters and the accuracy? So after applying that, you will get a set of values which are the best. K-nearest has these best features and like that. Okay. Now you can import the same thing for doing the K-nearest neighbors and random forest classifier, and then we have one more, which is the meta classifier. Okay. Now using the grid search. Stacking that operate on different subset of features. You can also do that by selecting the column separator by calling the make pipeline that selects the two features. Okay, so that you can do, and you can use pre-fitted classifiers, which has already been fitted. We previously fitted our classifiers in your models. Okay, fit base estimator equals to false, means you don't want to fit your base estimators. Okay, you can also plot ROC curve using, and you can see the ROC curve like this, and this first of all, these four examples are very important. If you do, you can see the ROC curve in more detail on the internet. Okay, great. So now we have talked a lot about stacking classifier. I showed you the implementation of stacking classifier. Here's a very interesting and a brilliant diagram on stacking, or algorithm given on stacking. This is a good example on stacking that I want to give it to you. Okay, thanks to the author who has given to you. Full credit goes to them. Okay, just I'm annotating. Okay, so now we are done with Ensemble Learning. So let's recapitulate what we have seen so far. We have completed, let me write a good accomplishment, completed Ensemble Learning. So what we have seen we have seen bagging. So in bagging, the basic intuition is we have a data, we take out different data, we train a different model, and then we aggregate the majority of votes from each of the model. Then you have, then in bagging we have learned about one of the algorithm, which is a random forest that just uses base learners with row sampling, with feature sampling, okay, feature bagging. And then we take out the boosting. Then we learned about the boosting. Where in boosting we learned about the technique, okay, and then we kind of converting the weak learners to the strong learners. Then we talk about gradient boosting, decision trees. Then we have talked about adaptive boosting, which is adapt boost, which is just use exponential as a loss. And then we talked about XG boost. Okay. Now we in this section, in this subsection, we have talked about stacking. We have talked about stacking, where we have seen a lot of examples. Using grid search, etc., using that. Okay. So now I hope that you understood everything about machine learning. Sorry, ensemble learning. Okay. So if you're watching till now, I am saying that you know that you do everything about supervised learning that you need to crack any kind of interview. Okay, so just pat your back and be sure to subscribe my YouTube channel. It just gives you a great motivation, as the new deep learning course is coming soon. So you can pre-register there for free. You can pre-register there. Or if you want, you can go to antern.co for detailed CSO. There is CSO 1 course which is on again machine learning, but it's not that different, but it helps you to make a resume based projects. It helps you to make the everything, means a paper in LaTeX. You will get live doubt supports, etc. just as a step to, so that just as you can go to CSO 1, see the benefits, what are the course details, etc. in the launch video, which has already been launched. Okay, so I think that you can also apply for a scholarship if you're a college student, but it's totally fine for but the course price is like this. Okay, but it's totally based upon you. If you want, you can definitely consider it. Just supports to make free content more. Okay, so that is just to me ask a question: Is this course the same as CSO 1? Yeah, it's yeah, but in that we have talked about about neural networks. Then you have talked about GANs, convolution neural networks. You will get a one-to-one session. You will get Jupyter notebooks, which are amazing Jupyter notebooks. You will get early access to my books. You will work with the team. You will be getting an internship. Will work on a real-world project in Antern, etc. Okay, so you can consider antern.co for this. Okay, if you want the lab, but if you complete this course, you all be very comfortable in machine learning. Okay, so that's it for this section, for this whole section on ensemble learning. From the next section, you can consider subscribing, obviously. From the next section, we'll be starting with, and in between we can do some projects. So from the next section, we'll be starting with unsupervised learning, and I really hope that you will enjoy that series also. Okay, so let's meet at the next section. Okay, so now we have covered supervised learning, and you can now consider comfortable in supervised learning yourself. Supervised learning is one of the very vast topic in machine learning that you have covered very smoothly, and I hope that you understood each and everything about supervised learning. If you have any kind of doubt, you can either ask in your Discord community, or you can ask over to you can find the Discord community, or you can comment and then we can answer your questions. Okay, so let's start with unsupervised learning. So what actually in supervised learning we are doing? We have our data set which is xi as well as yi, and we have I equals to 1 all the way down to the n. And actually we have one supervisor which is yi, and we know what our output should look like. Means we know what our output should look like, either be a continuous value, which is either a regression problem or a classification Okay, so that we know that what our output should look like. Okay, so here, so we know what our output should look like. So now, in case of unsupervised learning, there is no supervisor. So in case of unsupervised learning, we have only xi. we have only xi, okay, x1, x2, x3 all the way down to the xi, which covers I equals to 1 all the way down to the m. Okay, so here in unsupervised learning, we don't have any kind of supervisor that will tell us what will either output or will help us to train our model. Okay, and we don't know what our output should look like, either not in continuous and not in classification. So you cannot frame your problem, and you cannot even frame, because if you don't have your labels, then you cannot frame it in a supervised learning problem. So what I have to do? What we have to do? So, but I'm going to do just one or two, just specify that the data, we have a structured data as well as unstructured data. Structured data as well as unstructured data, and structured data is simply that which is in a tabular format, and unstructured data which is just images which cannot be fed on tables or CSV files, okay, or in Excel. Okay, so here, this is our unsupervised learning, because we don't have our output. Okay, so what we have to do? This is the main question to ask. What we have to do if we don't have the labels? So let's consider you have this x and y plane. Let me draw it very nicely. So in this section, in this subsection, I'm just going to give you an overview, understanding, and some of the applications of unsupervised learning. Okay, so consider that you are working on you have your data points. You have your data points like this. You have your data points like this into an x and y plane onto the coordinate planes, and you have another data points which is like this. Okay, which is like this. And you may ask, hey Ayush, why can't we make a simple hyperplane? But you don't know, but you cannot frame it in a classification problem. Just as a motivating example, I'm taking it as an example. Okay, so here just assume that you have this type of data set, okay, which is two-dimensional. Either you can make the three-dimensional also, you can make a three-dimensional also just by converting this. And now let's consider that you have three-dimensional features. So here you have this. Here you have another examples. Okay, so you have this. So now you only have these types of data points, which is this one is x1, x2, x3, these types of. Okay, so in unsupervised learning, what you do, you make cluster of your data, which is closest to one point. You make cluster of your data, Make cluster of your data. So as a motivating example, let's take an example that you want to segment your customers. Okay, let's take an example that you're a data scientist at Amazon, some companies. So you're just wanted to segment your customers. So how you will segment your customers? So what you will just segment your customers. We have this data, but you don't have the Y labels. So what you will do, you will make the similar person into the one group, similar person into the other group, similar person, let me do that, my bad. Okay, similar person in the another group, and similar person into the other group. So what you have done, you have divided your customers into segments. Now data scientists or business stakeholders, what they can do, they can decide that okay, we can give these customers a deal, basis on their activity, what they are doing, or we can make another machine learning model that will detect what they are dealing, what they want. Okay, and we can recommend the products. Basically these types of customers like milk, or like watching the jewelry on Amazon. So here, it will show the products of books or maybe some jewelries which are interested. And here maybe they will show you some kitchen groceries. Maybe these customers are interested in these, and then these customers maybe toys, maybe some TVs. Okay, so they will be recommended some products. And according to them, they earn a huge amount of money from recommending ads, etc. Okay, so that's why you can see that how we frame our problem. And now it's quite clear to understand that as a motivating example of customer segmentation in Amazon. And if you may think, hey Ayush, if you see that let me go to Amazon.com, you will see that I'm being recommending, and they know what I recently viewed, and they are recommending the products. Which you can see over here, that they are recommending the products basis on my views. Okay, so I'm in some segment, and they are simply recommending the basis products. And I hope that you understood, and I hope that you are understanding what I'm saying as a framing the problem as an unsupervised learning. Okay, so that's what the customer segmentation and recommendation engine that is happening in Amazon. Okay, so just watch the too much talk videos on YouTube. Now what YouTube will do, YouTube will take yourself and add it in a segment of the one who watches dogs, and now they will show you dog ads, maybe pedigree or etc., whatever the food of the dog is, or they will recommend you the videos of dogs. Okay, so that's why we have customer segmentation as a motivating example, and a recommendation is as a more motivating example. So now I hope that is start making sense to you to why we call this as unsupervised learning. Okay, now this is in supervised learning. In supervised learning, we have two approaches. We have two approaches, which is the regression, and next one is classification. But in unsupervised learning, we have something called as clustering. Okay, so we cluster our outputs, and if you plot in high dimensional space, then you will imagine that the most similar items are close to each other and most dissimilar items are very much far away. Okay, so you can understand like this. Okay, so let's take a motivating example again. So let's see some of the applications of unsupervised learning. So I will spend a little bit amount of time telling you about the applications of unsupervised learning, and in this next subsection we will start with the making clusters, what is intra, what is inter, how do we make the cluster, how do we evaluate our cluster, etc. Okay, so here I'm not talking about detail about clustering, but I just told you that we divide our customer into segments. Okay, so here let's take an example. We have now we are taking a look at the applications. Now we are taking a look at the applications of unsupervised learning. So the first application of unsupervised learning is in biology, which I have taken from Wikipedia, which is sequence analysis. Okay, sequence analysis. And it's simply it's just put your genes into the particular segment, and this will help you in various cases. For a biology student, then you will understand this concept of sequence analysis, because you don't have what you do. You segment your genes into particular segments, and you can diagnose if this person has any kind of problem. The next application, which is in business, maybe grouping of similar clusters for business needs. So let's take an example that some company takes your data, and then take your data and then simply grouping the similar clusters basis on the business need, and they can see the clusters, what their activity is, and they can provide deals, offers according to their activity. Another thing is we have recommendation engine that recommends the product that we have seen. Okay, so in recommendation you have content filtering, collaborative filtering, collaborative filtering. Okay, so which you can see which is a little advanced, but I'm not going to talk about recommendation engine. But as a motivating example, that whatever you see in Amazon or Google, they just show you what you have seen so far, because they have each and every, because if you search anything, you have they have that data, okay, for making ML models. Next is that in social network analysis. Facebook, if you know about Facebook, they told, hey, this person has just shared a post, means that we do the social network analysis. Social network, means they they group customers into the segments, they group customers into the segments, they group customers into the segments, and they show the accordingly profiles. Okay. Another is we have in computer systems is we have our favorite in computer science, we have image segmentation. So what do I mean by image segmentation? So you have an image, and you segment your image. If you frame this problem as unsupervised learning, so you have your image. So you have your image like this, and someone is here, someone is here, someone is here. So you segment these images. Segment these images. Okay. Segment these images as a pixel wise. You see that they have similar pixels. You segment it. So that's why you're segmenting, and this can be used for classification or object detection. Okay, object detection like that. Okay, so just grouping your images into segments by using maybe pixels, etc. Okay, because we don't have labels for y. Another motivating example in natural language processing is sentiment analysis. Means just seeing whether it be a negative or the positive. Okay, so what? Let's take an example that you have this that you have this sentence. Okay, this sentence and another sentence. Okay, so it will group the positive sentence and the negative sentence. Okay, so now you will see. Now what you will do? You will go and see one of the sentence. You will go and see one of the sentence. Go and see the one of the sentence and see. Okay, if it is positive, then you label whole cluster, which is maybe 10,000 sentences as a positive, and you take it as to whole 10, maybe whatever the number of as a negative. So let me elaborate this NLP task of sentiment analysis. Let's take an example. Sentiment analysis. So for an example, assume that you have a 1 billion text data points in text, which are textual. Okay, so convert it as a word embeddings mean numbers. Now if it is very hard to label, it will compute, it will take time, it will take cost, it will take because if you hire some people, you have to give them money. Okay, so you have to label 1 billion. So how you have to do? So what you will do, you convert them into a high dimensional space, and you segment the closest text, which is called the word embeddings. Closest word embedding means the word embeddings, and sentences are here, and then you see one sentence is from this cluster, another sentence from this cluster. Now assume that this cluster is a positive sentence. You label whole, let's say 50 million as a positive, and whole 50 million as the negative. Okay, so so you just require you don't require a lot of time for working with NLP tasks. Okay, so that's for NLP tasks. Another is anomaly detection. Okay, what is anomaly detection? And anomaly detection, in anomaly, we have anomaly detection, where we determine outliers in your model. So as an example, that you have the exact age like this. Now assume that your data points is here. So this is actually an outlier. So if you cluster it, here, then this will be ignored, and this can help in removing. But using maybe the DB scan, isolation forest, many of them, maybe some k-means, just take that outlier into this cluster. Okay, so let's assume then it is also closest to then take that into that cluster. Okay, so we have a DB scan which helps us into anomaly detection, which is again an unsupervised learning model. Okay, in a dense based reasons. Great. So we have seen a lot of applications of unsupervised learning. We have seen a lot, and I hope that you understood really. And in the next subsection, we will start talking about clustering. Okay, we will deep dive into clustering to help you better understand the topic. We'll talk about clustering. We will talk about intra-cluster, intra-cluster, how we evaluate our cluster. Okay, how we evaluate that we have a good clustering. What are some of the types of clustering, like partial, hierarchical, okay, then we'll talk about center-based, continuity-based, density-based, and then we'll talk about one formal center-based algorithm, which is k-means clustering algorithm, okay, and then we are done with supervised, unsupervised learning, okay. And then I will give you a little bit overview of deep learning, okay, so that you could better understand your deep learning journey. Just evaluation, and then we will do some projects based on machine learning so that you could get more feel about machine learning and you are more comfortable. And be sure to do the problem sets which are uploaded in GitHub to help you understand the topic or master the topic. Okay, so that's it for this section, and I hope that you have enjoyed this section.
Okay, so now we will start talking about clustering. We will get into math and we will see some more algorithms like k-means clustering. Then we will see hierarchical clustering algorithms, which is agglomerative and divisive. And then we are with unsupervised learning. So we are entering the last phases of this course, and I really hope that you enjoyed this course a lot. Okay, as I enjoyed making this course with very curiosity, with very energetic mode. So I think that you are also very energetic till now, and like me. And you may also thinking, hey Ayush, what about the projects? And the projects are in the last section to help you to get feel of everything about machine learning. Means after you learn all of these things, performance matrix, algorithms, now you will be able to build state-of-the-art models. Okay, so I'm very excited to see you all there, and it means in this section, last section, we'll be building back-to-back project, and the course website is also in the description box below. You can see what problem set is there, and you can download and start working on that problem set. Okay, so I hope that you're watching this video did totally worth it. Even I was making video was totally worth it. Okay, so what we are going to start talking about? We are going to start talking about clustering. In our previous subsection we have talked about some of the applications of clustering. We have talked about, let me choose a good pen. We have talked about applications. We have talked about applications of clustering. We have seen what unsupervised learning is, and we have seen the lot of applications like in biology and business and etc. We have seen the applications of unsupervised learning, and then I've showed you the data. Okay, and then I've given you an overview what we do in clustering. Okay, so let's start with clustering. Okay, so what the clustering is. But don't just bear with me with my handwriting, because I don't know what happened to my pen. It's very working bad, but no worries. Let's start. So here let's assume that you have this you have the great why it is not being removed. Let's assume that you have a x and y plane where you have two features like this. If I draw a straight line, okay, so here you have this, and let's assume that you have here as a point here. Okay, you have this as a point, and another point is green ones, which is here. Okay, so in unsupervised learning all data are same. Why I forgot? No worries, I usually forgot everything. Okay, so what you have these features, red features, and you have this here. So what you usually do in case of clustering, you segment your clusters. You segment your data into different clusters. Oh my god, why it is not happening? You segment your cluster. So you have this data, so you segment this cluster, to be going into this, and the second cluster to be going into this. Okay, so this is your first cluster, this is your second cluster. Okay, so this is your basic thing about clustering that we have talked. Okay, so we'll see some of the terminology in this. So let's draw a very good representation of this diagram. So let me delete all these links and let me choose a black pen. It works best in case of white. Okay, so you let me draw a straight line with x plane, okay? So you have x and y plane, x and y plane, and here you have the data point, here you have the data point like this, and here you have the data point like this. Okay, so what do? You segment your data points into clusters. You cluster it out. So some of the terminology is you cluster this, let me draw a good cluster. You cluster this, and then you cluster this. Okay, so let's leave that. I don't want to make it like that. Let's leave that for now. Okay, so you cluster this out, and then what happens? So here is a terminology alert. Means in terminology we have something called as intra-cluster. We have something called as intra-cluster, and inter-cluster. Just listen what I'm saying. Intra-cluster and inter-cluster. So what do I mean with these intra and inter? I mean with this intra and inter is inter-cluster is the distance between the cluster, okay, between the clusters across all the clusters. So inter-cluster is the distance between across the clusters. So here we have one cluster, here we have second cluster. So inter-cluster is the distance between this cluster and this cluster. It's the distance between this cluster and this cluster, so that's why it's known as inter-cluster. Okay, the second type of is intra-cluster, which is the distance between within the cluster, that points within the cluster. So it may be like this. This is called the intra-cluster. This is called the intra-cluster. I hope that you are that it is making sense. You have this x and y plane, and you have this kind of thing, and what we have to do, this is called the intra-cluster, where we have the distance between two clusters, or maybe two or more than clusters across all the clusters, and intra-cluster is the distance between the data points inside that cluster. Okay, great. So we can think something like that is what we want in this case, if we are taking as a terminology that, so we want our intra-cluster to be small, intra-cluster to be small, and inter-cluster to be large. What do I mean with this small and large? I mean with this small and large is you have this intra-cluster. Intra-cluster is the distance between this and this, and the clusters takes whoever is similar, or group is a cluster is just is a grouping of the similar objects that they are similar to one another. So they should be closest. The data point should be closest, and the intra-cluster of these should be closest. Okay, and the intercluster means the dissimilarity between two clusters should be maximum. Okay, so here we have written our optimization objective. We want our intercluster, which I did as IN, should be large, and A should be intracluster should be small. Okay, so that's the basic definition of, that's the basic basic terminology that we have seen, and I hope that is making sense. Okay, so we can frame some problem, we can frame something over here. What we can frame is, we can frame an optimization objective, we can frame a evaluation technique, but before that, why do we even need? So let's assume that you have this cluster like this. You have this cluster 1 2 3 4 5 6 7 1 2 3 4 5 6 7. Okay, so here we have this, and who can tell you that these are the perfect clusters? These are the perfect clusters. Either you will tell, hey Ayush, I'm able to see, I can tell that these are the perfect clusters, but assume that we have 3-dimensional, we have 4-dimensional, we have 50-dimensional, we have 80-dimensional, we have 100-dimensional, we have lakh dimensional. So what you will do in that case? So we have evaluation techniques, okay? We have evaluation technique that will help us to evaluate our clustering or unsupervised learning, clustering model, okay? Clustering model that will help us ideally to understand, to evaluate how good our clustering is. Okay, so let's see how some of the evaluation techniques. Okay, so the first one we have, which is called done index. Okay, so the first one we have is called DUNN index. So this is a very funny name, but it's a very you can still read about it in Wikipedia page. So it's so let me first write the equation. So D equals, which is a done index, equals to the maximum of I and J, means the maximum distance between I and J divided by maximum K, maximum distance D dash between K. Okay, so here what I'm telling, here we have this intra-cluster, here we have maximum inter-cluster distance, okay? So ideally it is framing our problem of intra and inter, that our inter should be small and our inter-as should be large. Okay, so here we are not assuming should be small, we are assuming what is the largest maximum distance. Okay, so if everyone is small, then the largest may be 0.00 like that. Okay, so maybe something like that will be there. So we are just changing this maximum. Okay, we have maximum over here. Just don't be confused, we are telling minimum intra, that just ideally means that you want the distance between intercluster to be small. So that's why you are taking the largest, whoever the have a largest distance. Okay, so that's why so you can evaluate your model. And the denominator simply means that the distance between your intra-cluster, okay, the distance between your clusters, the distance between should be ideally large, not too much small. Okay, so that's the and if you sense it's mathematically, you can see that D should be high to be a good cluster. D should be high. Okay, so this is the evaluation technique for clustering your model, and I think that you understood done index. So let's recapitulate what we have seen so far. Is we have, let me remove this. Let me remove this. So we have seen that we have some of the terminology. So we have this small x and y plane where we have this 1 2 3 4 5 6 1 2 3 4 5 6. Again one more. Okay, so here we have this the distance between two clusters is called as intra-cluster, means across all the clusters, maybe some cluster will be here, another cluster will be here, across all the clusters this is called the intra-cluster. And the distance within the cluster, within the data points, is known as the intercluster, and core idea is, for any evaluation matrix of your clustering model, is your intra-cluster should be large, and intercluster should be small. Okay, so we have talked about a done index. We have talked about done index. And done index is simply evaluation matrix. So the done index is written as D equals to the max of the distance between I and J, which are two data points, which is obviously intercluster, which is obviously the first numerator is intercluster. Okay, and the denominator is simply the intra-cluster, where you want the maximum distance between the values. Okay, so this is the basic definition, and you may think, yeah, you have told about intercluster should be small, but we are checking the maximum so that we can evaluate. We are checking what is the maximum in that cluster that has the distance, so we can evaluate. So everyone should minimum, so our D should be high in that case. Okay, so I think that you understood done index also. So let's see one more evaluation technique, which is for clustering, which is just I'm telling you just some constraints to be added. I just have seen the equations. Just some conditions to be added in I and J, where here in I should be greater than or equals to 1, or it should be and it should be smaller than or equals to J, and J should be smaller than or equals to N, and N here is the number of training examples. And for K, constraints of K is your K should be smaller than or equals to should be at least smaller, smaller than or equals to N. Okay, so that's the basic definition of that's the basic constraints, but I don't find it's a very kind of thing. But here, just understand this: the numerator is just a maximum intercluster, and here maximum intracluster. Okay, and the reason why we want to evaluate, so that's why we are taking the maximum. So if it is maximum, then it is bad. Okay, so our D index should be high if you sense it mathematically. Okay, so another evaluation technique that I've seen so far, let me go back actually. Okay, so here I am on my another thing, and let me remove this. Okay, so another technique is here in front of you, which is the Davis-Baldwin index. Davis-Baldwin index. This is also like a done index. What you want, we denote is that dB equals to, we take it as a dB equals to 1 over n, I equals to 1 all the way down to the n, and then you take out the maximum, where j is not equals to I, sigma I plus sigma j divided by the distance between Ci and Cj. Okay, and this is just the clusters. And for more information about what is this, you can refer to a Wikipedia page. Okay, there is a more derivation, etc. has been already done over there. Okay, so that's the Davis-Baldwin index, but most probably the done index used properly in the country, in the whole for evaluation of your model. So let me highlight it, this one. Okay, so we have seen Davis-Baldwin index. Now it's time for learning a little bit more in depth about what actually the definitions of what's the definition of your favorite clustering. Okay, so one line definition I could tell about clustering is, in clustering you have, and it's a grouping. Can I write it? Yeah, it's better to write it. Okay, just bear with me, or you can write with me also. So the clustering is simply grouping of objects, or elements, objects, such that, in such a way, I could say in such a way our object in a should be similar to each group where it is in, each group, and differ from another cluster, differ from another cluster. Okay, so that's the basic definition of clustering, and a very good definition. And in clustering we have two cases: intra-cluster and intercluster, where we want our intra-cluster is the measure of distance between just a distance within the cluster, and intercluster is difference between across all the clusters. Okay, so this is the basic definition of a clustering, and I hope that you understood everything. Okay, so now we have seen done index, we have seen clustering. Now it's time for learning about getting into depth of clustering, is about types of clustering, how many types of clustering we get in our life, and then we will, just after talking about types of clustering, we will end this subsection, and in the next section we will be talking about one algorithm, which is k-means, and the next subsection we'll be talking about hierarchical clustering, which is agglomerative and divisive clustering. Okay, so but before that, let's see some of the types of clustering. Okay, so the types of clustering, which includes the types of clustering, let me choose it, the color. So some of the types of clustering are, first one is partitional based clustering. Partitional, I'm just writing in short, partitional based approach or clustering. Okay, so what is partitional based clustering? So assume that you have this that you have this x and y plane, and you have this data point like this, and you have this data point like this. Okay, so what you will do, you will partition it into two clusters, and you are done. Okay, so here we have one algorithm which is called k-means algorithm that we'll study in our next subsection. Okay, for in a partitional based approach. Then we have hierarchical clustering, hierarchical clustering. Okay, so in these types of hierarchical clustering, we have like a dendrogram. If you have seen a dendrogram, then you know about hierarchical clustering. Just if you know. So let's assume that you have this data point like this. You have this data point. Let me do it here. That you have this here like this. Okay, so you have this 4 points. You have this 4 points, and again you have P1, P2, P3, P4, and if you plot it, the points looks like this. So these two, this P1 and P2 looks close. This P1 and P2, this P2 and P3, just assume that this is a P2 and P3. This looks close, so you just cluster it out. Okay, so the P2, so what you do, you just make a dendrogram just like this, that P2 and P3 are now a cluster which is the same, which we can consider P2 union P3. Okay, now these are the two clusters. Now if you see, the closest structure is this P4. So what you will do, you will again make a nested cluster. Now this will look like this, and now what you will do, you will attach P4 over here, P4 as a dendrogram. Okay, and then what you do, then here is this is the P1 is the closest, then you cover it, and then this hole and this hole. Now after that, you will be ended up being a dendrogram. You will be able to see a dendrogram, which you can see over here. So here after, which is P1, like this. Okay, now you can see, now we cannot we have a large cluster, which we have a large cluster. Now we are done. This is called the traditional dendrogram. You can see on the internet about this. So what we have seen so far, we have agglomerative structure. We are going up, means we are going up like this, means we have this P1, P2, P3, P4. These are own clusters by themselves in first. These are their own clusters. We have 4 clusters over here. We have 4 clusters. Now we cluster this P2 and P3. Then we cluster P3 and P4 because they are close to each other. Then we construct P1 to P4. Okay, so now we got our full dendrogram. Okay, so that's usually agglomerative cluster. We have something called as divisive. We are in divisive, and I'm talking about in hierarchical clustering which is agglomerative and divisive. In divisive, we have given P1, P2, we have something called as P3. Let's assume that we have A, B, C, D. Okay, so A, it's just it will match if I do that, A, B, C, D. Okay, so E, let's assume E also. So you divide this. Okay, so what you do, you simply divise it. Okay, like this. First you divide A and B, A, B as one cluster. Then you divide C, D, E. Then you have C, D, E. okay? Then you divide A and B into different cluster. So you have this whole dendrogram like structure like this. Now you are this is just opposite of agglomerative. We are just here we are making up, here we are making up, here we are making different cluster, okay? Now we divide our C, then we have a DE. Now we divide our D and E. Now this is our divisive, okay? So we divide our whole cluster into different groups which are most closest to each other, okay? We will study in detail about this in our next subsection, where we will talking about hierarchical clustering, okay? After that we have something known as well separated clusters, where it is well separated clusters, okay? Just I'm writing it's well separated, means you can easily, your model can easily separate, well separated. Then you have the fourth one, which is center based, which is also k-means clustering, is this center based algorithm, okay? Continuity based, we have something called as nearest neighbors, k nearest neighbors, okay? And then we have density based, which is often known as DB scan, okay? Which you will get in problem set to learn about this DB scan, okay? Great. So we have seen a lot about clustering, and I hope that you really enjoyed this session, this subsection of clustering. And from the next section we'll be talking about Lowit's algorithm or k-means clustering. I will definitely try to complete in no time, so that you could get a more prone knowledge of clustering and able to make unsupervised learning models, okay? So let's see just recapitulate what we have seen so far. We have seen what is clustering. Clustering is just a grouping of similar objects in such a way that these objects are similar to each other within the cluster, or our intercluster should be different, should be maximum, and our intra-cluster should be small. And what is the difference between inter and intra? In inter we have the distance between across all the clusters, and that's why we need a maximum. And we have intra, in which our points within the cluster should be minimum, okay? Means more similar, okay, other than the other clusters, okay? So that's the basic intuition about this and the clustering. Then we have seen how we can evaluate. So I have talked about one evaluation index, which is done index, okay? And done index, it is used to it is used to evaluate your clustering model. And what it does, it takes out the maximum. What is the maximum in intercluster? What is the maximum to evaluate the performance between 2 points? And it takes out the maximum of the the denominator is intra-cluster, and numerator, sorry, yeah, the denominator is intra-cluster, the numerator is intra-cluster, and the denominator is intercluster, okay? And then we have something called as Davis bounding block index. This is just it will take a lot of time to teach this, but it's out of the boundary course. But it's just here, n is the number of clusters, where we have a sigma I plus sigma j, and where I is not equals to j, we want the maximum, and then we are taking out the distance between two clusters, and then we are dividing it up, okay? So that's what the full clustering based models is. Now I hope that you understood about clustering. Now it's time for learning about now it's time to learn about something new, which is in subsection, where we will talk about where we have talked about 5 types of clustering, which is partitional based, hierarchical clustering, and well separated, and center based, and DB scan, okay? So we will talk about partitional, hierarchical, and well separated is also and center based, where your problem set will be on DB scan, Okay, so here we are done with this subsection. Now in the next section we'll start talking about k-means. Till then, have a good day. Okay, so now we have talked about various things like clustering. We have given a part 1 in subsection. I've given you unsupervised learning applications, and then we have talked about various applications of unsupervised learning, and then I've just given you an overview of clustering in this first subsection. In the next subsection, I've given you the intuition behind clustering. I've given a formal definition of a clustering. We have talked about intercluster, intra-cluster. We had talked about the evaluation matrix like Dunn index, Davies-Baldwin index, and I've made you understand each and every equations, and I've also helped you to understand what are the types of clustering which are available, like partitional based, hierarchical clustering, then you have a center based, world separated, density based, continuity based. Okay, so we have this kind of clustering which are already available. Now we will talk about a partitional and center based clustering, which is k-means algorithm. As this example was taken from Andrew Ng course of machine learning, but he has but it's too much 37 years old, but I have made it very updated for 2020. Just that this example is from Andrew Ng. Okay, so I've also included k-means plus algorithm, what the k-means plus algorithm does, and some of the variations of k-means. And then also I have talked about in detail what are the limitations of k-means clustering, how we initialize the centroids, what are the time complexity of k-means clustering. Okay, so then we have talked about the full k-means clustering algorithm, how we evaluate our k-means clustering algorithm. Okay, with the Euclidean distance. So that's what we are going to talk about. Just be sure to just sit somewhere and see and take a copy and pen to understand. Okay, but before that, what we are going to study is k-means clustering algorithm. Sometimes the synonym of k-means clustering is Lloyd's algorithm. It's sometimes called Lloyd's. It's sometimes called Lloyd's algorithm. Okay, so it maybe some people pronounce it as a Lloyd's algorithm or a k-means clustering algorithm. Okay, but I like to pronounce with k-means. Okay, so just as an example, we have this data set. We have this data set over here. Now what we do in clustering, we initialize centroid, which is k. Okay, we initialize centroid, which is denoted by k. So here it is a hyperparameter. So what we are going to do, we are going to initialize k as which is two centroids, and centroids is just the initial. You will get to know with the visualization. So what you do, you initialize with 2 points onto this. So here you initialize 2 points like this. The first point is over here, the first point is over here, and the second point is over here, and these are called the centroids. You will get to know why we call it as a centroids, but these are called the centroids. Okay, these are called the centroids, and here in this example k is equals to 2 because we have taken k equals to 2 because as we have 2 centroids and we randomly initialize these centroids. Okay, so we'll see the initialization just after some PPTs, just some slides. Okay, so you initialize your model now, and now this is the first iteration. Now in first you initialize, then what you do the assignment step. What do I mean by assignment step? First you initialize, then what you do assignment step like this. You assign all the particular value, means red to red color and blue to blue color. You can see over here that we have done red to all the red color which are closest to this centroid, and this blue we have covered, that is all the centroids which are closest to that blue. Okay, now what we will do, we will take out the average of these points. We will take out the average of these whole blue points, and then we will take out the average of this red points, and then what we will do, we will average it like this. We will average it. Now after averaging, we will make that centroid to at average, and then what we will do, again we take out the do the assignment step like this. We just assign, we just update our values which are so closest to this centroid. Now you can see that the blue becomes like this. Now then what we will do, we will again move the centroid. Again we will take out the average and move the centroid like this. We will move the centroid, and then we will make this red means those are closest to blue, and these are to red. Okay, then again you do like this, as a taking out the average and making the color as blue and red. Okay, now you can see that what you have done, you have a very good cluster, means you have initialized here, and then you taken out the average, then you move to that centroid, and again you update the cluster, and then again you move that like that. Okay, so we have done like that, and I have just shown you a very good visualizations of this k-means. So let's see again in a little bit more fundamental way. Okay, so here is our data, and then you can see the data looks like this. So here what we had done, we had simply initialized two centroids like this, and then what we have done, we had just make the points which are closer to that blue and red to that red. Okay, you can see over here. Then what we have done, we had taken out the average, and then we moved our centroid to that average. Okay, and how we take out, you all know how do we take out the average. You just take out the number of observations and then divide or the sum over the observation divided by the frequency over the observation. You just do that, and then you update it, and then you again make the whole assignment step. And then what you do, then you again take out the average. Now you again update the points, you can see like this, and then you again take the average, you again make the points as like this. Okay, and after until and unless your centroids are not changing, you keep doing this. Okay, so here is informal algorithm. Here is informal algorithm, and you can see over here after 7th iteration it is not changing, so we converged. Our algorithm is converged. Okay, so this is how whole k-means clustering algorithm works in visualization. So let's see the algorithm in detail. Okay, so what you do, first of all, here's an algorithm I'm writing. Just bear with me, but just bear with my handwriting. So I'm just writing an algorithm. So here is my algorithm with the red's written with the red color. So let me write, here is your algorithm. Okay, so you do for k centroids, okay, so you have to choose k. Okay, you have to choose k, which is k where is a hyperparameter. Okay, then you repeat these two process. The first process is cluster assignment. You assign all the clusters, you assign all the cluster, and then update, take out the average, and then take out the cluster assignment, you assign the clusters, and then you take out the average, and then you make that point. So then you do the updation of a cluster. Okay, then you recompute the centroid. Okay, then you recompute the centroid. Okay, then how you recompute the centroid? The centroid, it simply means you make you take out the average, and then you assign that cluster. Okay, that cluster to the nearest data point. Okay, again you take out the average until and unless your centroid are not changing. Your centroids are not changing. Okay, where it means that your algorithm is converged. Now you don't need. Okay, so you repeat these two process like cluster assignment means assign the cluster with blue or red, and then you update your centroid and by taking out the average, and then again doing this, taking out the average, again doing this like that. Okay, so this is the basic algorithm of k-means clustering algorithm, and I hope that you understood about k-means. So let's understand a little bit more a little bit more further into just a recapitulation of k-means. K-means clustering is an algorithm also called the Lloyd's algorithm. Then what we do, so let's go back to our visualizations. Okay, so here is our data, and what we do is we randomly initialize two centroids. Okay, not every case, just have taken, it is a hyperparameter, we have just taken 2 for this case. Okay, then what you do, then you do the second step, which is which first you do the cluster assignment. You do assign all the cluster with the closest with the same points into the cluster. Then what you do, then you do the recompute the centroid by taking out the average and moving the centroid. Okay, then you do the cluster assignment, then you assign the cluster like this, then you again move the centroid. Okay, recompute the centroid, then you assign the like that, and then you take out the average, and again you do the same. You take out the average and then move your centroid. Okay, now in the next iteration it is not changing. Now your k-means clustering is converged. Now you are done. Okay, so here's a good algorithm. You will be able to see on the internet the same thing. Like first you choose k, how many number of k clusters, then you assign the clusters, recompute, and then until and unless your centroids are not changing. Okay, so this is whole about k-means clustering algorithm, and I really hope that you understood k-means clustering algorithm. So now let's see some evaluation techniques of k-means clustering algorithm. Okay, evaluation technique, how do we evaluate our k-means clustering algorithm? So for an example, here is my example. So for an example, we are given no, not in for an example, is just I'm giving you the optimization objective. So you are given x d-dimensional space as well as k and the clusters which are this and set, I think the dictionary which is in there's C1, C2, all the way down to the CK. Okay, we have k clusters. Okay, then what you do, you want your to optimize C, you want to minimize this cost function. Now what you do, you take out I equals to 1 all the way around to the k, where x be the member of CI, means the cluster. Now you take out the distance of x and C. Okay, you want to minimize this cluster. Okay, so just it will make sense, don't worry. Here we have CI, which is equals to the centroid. So let's see what do I mean with this distance between x and C. So what we are told, that we are told that we are given x d-dimensional space, and we have clusters which is C1, C2, all the way around to the CK, where we have k clusters. Now what we have, this equation I equals to 1 all the way down to the k. We are going to till every clusters where each x is the member of cluster, means where this data point is the member of this cluster. Okay, now you take out the distance between this data point and this cluster, this cluster. Okay, and this should be minimized. Your distance should be minimal. As compared to this. Your distance should be minimal. So that's what it is telling over here. Okay, so I hope that you understood with the help of a visualization. Okay, so CI is the centroid. Okay, cluster centroid. Okay, so how do we take out the distance? For taking out the distance, we have something called as a Euclidean distance. Euclidean. For taking out the distance, we have something called there are a lot more distances which are already available. You can take a look at it online, but it's a very used Euclidean distance. So what is Euclidean distance? In Euclidean distance, we have D, we have 2 points P and Q. Okay, means we are doing for each and every point I equals to 1 all the way down to the n, means number of training example, Qi minus Pi squared. Okay, and it's taking out the square root of that. Okay, so this is the Euclidean distance that just measures the distance between 2 points like this, and you can see more about this onto the internet, how we derive this equation, what is this, whoever found it, etc, etc, etc. Okay, and sometimes this cost function of k-means clustering is called SSE, means sum square error, and you can also see it is just like the done index following the inter and intra cluster. Here we want to minimize our intra cluster over here. We want to minimize our intra cluster. Okay, so that's the basic definition. That's the whole story about k-means clustering algorithm, and I really hope that you understood k-means, and then we have talked about evaluation techniques for k-means, and that's it for k-means. And now we will talk about why it matters, means the basic definition of why it matters, which is the random initialization. As we have seen that we initialize our centroids, these centroids randomly. You can see that we have initialized randomly. So why it matters, how it can cause the problem. It can cause the problem. So here we had just chosen, you can see over here that we have in iteration number 1 we have 3 centroids. Iteration number 2 we take another the average, compute, then we do the we simply what we have done, we assign the cluster with the same centroid, and then we recompute by taking out the average in the second iteration, then in the third iteration, then the fourth iteration, and the fifth iteration, and the sixth iteration. You can see over here that you can easily see that we have a good cluster over here. But you can see in here that you have just it can cause, how it can cause problem is in iteration number you have just randomly initialized. Now you can see whole story changed. You can see over here. Okay, so that's the big problem. So that's why we do, which is very not recommended to choose it randomly. So researchers discussed about it. Researchers had talked about it, how we can use it, how we can make something good. So researchers found that k-means plus something called as k-means plus algorithm works best which I'm going to tell you. Okay, so k-means plus algorithm, what it does, it simply select multiple numbers. As in random, we are just taking any random, but it selects multiple numbers and select the smallest error. Okay, so that's what the k-means plus does. It selects multiple means it's just a multiple, a sample from the numbers, multiple numbers, and checks which number minimizes the SSE, which minimizes the intra-cluster distance. Okay, so that's the k-means plus, and it is usually used in everywhere. Okay, rather than randomly. Okay, so we have talked about why we choose importance, why we choose why we choose k-means plus over randomly, because maybe it can happen sometimes. Okay, if the luck is not with us, it can cause a big problem and further. Okay, so how we have to deal with this kind of situations. For dealing with these kind of situations, we have something called as k-means plus, which will help us to do, which just selects the multiple multipliers and select the numbers which has the smallest error. Okay, so let's see. You may think, hey Ayush, how do we select how many number of a centroid that we need? Okay, so that's also the best, that's also the big problem. So we have something called as elbow method. And what it does, we have elbow method like this. We have written the k clusters 1, 2, 3, 4, 5, 6. Okay, now if you have taken k equals to 1, your error is high. If you've taken k equals to 2, your error is going down like this, like an elbow. Okay, so here you can see the elbow turns around at 3. So you select this elbow, you select k equals to 3. Okay, so this is your loss, this is the number of a k, and this is your loss, which is decreasing, SSE. Okay, so that's how we use elbow method. Either you can use grid search, CV, or randomized search to tune this parameter. I think that will not work because we don't have labels, but elbow method works best when you plot it. When you plot it and see what number of a k you need. Okay, so that's it. That's the following, and let's revise so that we are on the same page. So what we do in k-means clustering algorithm, we choose number of a k using the elbow method. Not now, just I choose we randomly, and then we plot it, and then we choose the k, and then what I've done, then we repeat like cluster assignment, like we assign all the cluster with the same clusters, then we compute the centroid by taking out the average. Okay, then you keep repeating this until and unless your centroids are not changing. And then the evaluation technique for your k-means or loss function for your k-means is you want to minimize your intra-cluster by just taking out the distance between distance between the points inside the cluster. Okay, and then that's called sum square error, and you take out the distance using the Euclidean distance that just take out the difference between 2 points by doing the summation over there. Okay, great. So how we choose the how we choose the centroids? Okay, the initializing of centroids. For initializing, you have seen over here that randomly initialize can cause a very big problem. So that's why we have something called as k-means plus, which will help us to select centroids using what it does. It does for multiple runs and checks the numbers where the SSE is low. Okay, and how we select the number of a k? We select the number of a k by using elbow method, where the elbow is turning around like as a hand. If you draw it like this, if I draw a hand over here, if you draw it like this, okay, so your elbow is there, so your loss is decreasing with k equals to 1 is your loss is this. Okay, so you choose the elbow k equals to 3 and it works best. Okay, so we had talked about these things, and now it's time for ending up k-means clustering, the chapter of k-means clustering, which is just ending the topic with our favorite, what are some of the limitations of k-means clustering algorithm, and what is the first time complexity. So the time complexity of k-means clustering algorithm, the time complexity of k-means clustering algorithm, if you don't know if you don't know DSA, leave it. Okay, ignore this. The time complexity is order of n times k, and n is the input size, k is the number of clusters, I number of iterations, d the dimensions. Okay, this is what the time complexity of that. Okay, so it's because the time complexity depends upon your size. If you don't know about time complexity, I have something called as DSA mastery course. Soon putting videos onto that. So first 4 lectures are based on time complexity. You can watch that. Just go anywhere. I will just show you where you can go. Okay. Some of the limitations of k-means clustering algorithm. Some of the limitations of k-means clustering algorithm is it's very sensitive to outliers. Okay, so let's assume that you have this oops, why PowerPoint Control Z does not work. I don't know why. So here we draw an x and y plane, and here we have x, here we have y, and let's assume that we have made it. And here we have the outlier, here we have it is closer, so it will take that outlier in that cluster. So we don't want that, so it is very prone to outlier, means we have to detect the outlier, and it can be solved using density based even I just don't know what's there. So it can be solved, outliers problems can be solved using a DB scan, which you have a problem set to solve. Okay, means you have to read the Wikipedia page and write Google Docs onto the DB scan what you understood. Okay, and then it's like different sizes, different distances, maybe they're causing the problem. Okay, but the main problem is outlier. Okay, k-means is, so I have given you the thing that DB scan hierarchical clustering works on these types of issues. Okay, so that's it for this k-means clustering algorithm, and where you can find the time complexity videos, and it's very recommend it's very helpful. if you subscribe this YouTube, the New Era YouTube channel, which you can find, which you can easily find onto the YouTube just by writing New Era, where I have 502 subscribers as of now. Okay, so you can subscribe that and see the DSA Mastery course, where we have more than 23 videos already uploaded, long lectures, so you can learn about time complexity from there also. Okay, so that's it for this subsection. You now have a toolkit of various algorithms, various techniques, various things. Okay, so now let's meet at the next section, where we'll be talking about hierarchical clustering. I will give it a short so that it should make sense. Okay, so let's meet at the next subsection. Okay, so now we have talked about clustering, we have talked about unsupervised learning, we have talked about one of the partitional based or center based approach, which is k-means clustering with k-means plus algorithm for random initialization. Okay, so I hope that you understood everything in unsupervised learning, and we have gone so much further into unsupervised learning. Now we are capable of learning hierarchical clustering, which is one of the most favorite and the best clustering techniques that include including partitional based, and then we have a hierarchical clustering. Okay, so this is what we are going to do. We are going to start with an introduction to a hierarchical clustering to help you better understand what a hierarchical clustering is. Then I will go further into different just a quick recap onto partitional based. Okay, then I will show you the visual representation of hierarchical clustering and what is the dendrogram. Okay, and then we will move further into understanding the two types of hierarchical clustering, which is called agglomerative and divisive. Okay, so agglomerative clustering and divisive clustering, we will dive into agglomerative clustering, and we will just take a look at the divisive. Okay, and then we will go further into understanding the agglomerative clustering algorithm, and then we will see then we will compute that algorithm manually, and then we will see the intercluster similarity between 2 points. Okay, but if all the words or technical terms are going above your mind, leave it. Means just ignore the words as of now. Let's start with hierarchical clustering, just introduction to hierarchical clustering. Okay, so what is hierarchical clustering? Hierarchical clustering is that you have a hierarchy of clusters. Okay, so for an example, what I'm going to do is I'm going to take 4 points. I'm going to take 4 points P1. Let's not take it here. Let's take P1 here, P1. Then I'm going to take P2. Then I'm going to take P3. Then I'm going to take P4. Okay, for an example, I've taken these 4 points, and now we want to cluster it out. Okay, now we want to cluster it out. So how do we cluster it? So for clustering, we have our favorite, means we can simply see, okay, this distance is small, these are more similar. We are going to do this. We are going to cluster it out like this. And we have this P3 and P4. How do we cluster? We cluster this P1 and P2 are here. So we cluster, we put another cluster. Okay, because this cluster P1 and P2 is P1 union P2. It is now a one cluster. Now in nearest the data point, nearest point between or the nearest, these are their own clusters. Initially these are their own clusters, so we are going to merge it. Okay, so here we have a P1 and P2. Now the smallest distance is P4. Now we attach, means now we make one more cluster. Okay, now in this big cluster, where we have 3 points, what is the nearest data point now? The nearest data point is P3. Okay, so we'll make again one cluster, again one big cluster like this, until and unless we have one cluster at one cluster at a point. Okay, so here we are ended up with one cluster. Okay, so it is not making sense, I know, but we can just as a diagram I have made this. So let's see how we do it using a dendrogram. That will make more sense. Okay, so here we have a P1. Here we have a P2. Oh, oops, let me make a little bit more good. Oops, what happens? Okay, so here we have a P1. Let's assume that we have, this is the point P1. this is the point P2, this is the point P2, and this is the point P3, and this is the point P4. Okay, now these are the points. Now what we will do with here, you can see, just assume that this is P1, P2, P3 and P4, and you can see this P1 and P2 are smallest, so we can make we can attach this, we can make a we can make like this, we can attach this P2 and P3. Okay, now these are one cluster. P2 and P3 are one cluster, which we usually call P2 union P3. Okay, now initially P1 is one cluster C1, P2 is one cluster C2, P3 C3 and P4 C4. Okay, so these are initial clusters. Now what we'll do, now this is the one cluster, which is C2. Okay, so we found and attached it. Okay, now what we will do, now the nearest state data point is P4 over here. Okay, so what we will do, we'll again attach P4 into this. We'll again attach P4. Now we have P3 and P4 as a one cluster over here. Okay, now we can attach P1. Now we can attach P1. Now we can attach P1 like this. Now we can attach P1, and now we have our dendrogram, which is actually a hierarchy of clusters. Okay, so here we have a traditional dendrogram, which I think that you have all seen in your journey. So this is your dendrogram. What you have done, you have just, who are most similar, you attached it. Okay, who are most similar, you attached it. For an example, these are two similar, you attached it, and then this is now what you attach it like this. Okay, do not merge it, do not merge it. Okay, so you have to do like this. Now here we have, until and unless we have left with one cluster. Okay, so that's the basic hierarchical clustering, and I hope that you understood hierarchical clustering, the basic intuition. But if not, let's try to again understand a little bit more further into more sophisticated way. Okay, not sophisticated, just easy way. Okay, so for the example, I'm gonna take a yellow color. So here you have a C1, here you have a C2, here you have a C3, here you have a C4. Okay, so this is your C4. Now you can, this C2 and C3 are your points, C2 and C3 are your points. Okay, so these are two much similar, so you will attach this like this. Now C4 here is here, so you will make one more. Now C3 and C4 will be attached like this, and C1 will be attached onto the up of C4. Now this is a traditional dendrogram. This is traditional dendrogram, where you convert this cluster of numbers, C1, the clusters to a hierarchy of clusters. Okay, so for an intuition, what I'm trying to say you here, so I have one example. So for an intuition, what I'm trying to say you here, that we have a C1, C2, C3, C4. Now we're just making attaching as a cluster, so C2 union C3, etc. Okay, so this is the basic intuition behind hierarchical clustering. So there are two types of hierarchical clustering. Some of the types are, we have something called as agglomerative clustering, and then we have divisive clustering, and then we have divisive clustering. Okay, so we will deep dive into agglomerative clustering. I'll just give you an intuition behind divisive clustering. Okay, so what is agglomerative clustering? So the agglomerative clustering, agglomerative clustering. Okay, so before that, let's understand, let's understand the divisive clustering to help you better understand that. So it is up to down approach. Sorry, it's a down to up approach. It's a agglomerative is a down to up approach, and divisive is just opposite. It's just opposite, where divisive is just up to down approach. Up to down approach. So what do I mean by this? So for an example, let's assume that we have 4 points. We have 5 points in the form of data A, B, C, and D, and E. Okay, so here what you are going to do, you are going to divide this cluster of numbers, into a different AB, let's assume that you are divided with AB. Now this is your CDE, CDE, CDE as a most similar. Okay, you divided this. Now what you will do, you will divide this A and B, A and B. Now you will divide this C, C and D, DE. Okay, now you will take the D and E. Okay, so this is the basic what you are doing, you are making the cluster of numbers into separate numbers. So you're making the hierarchy of numbers. Okay, hierarchy of numbers, and this is what you are doing. Okay, so you are just making a hierarchy of numbers. It's like ABCD is, you're going to up to down approach, from up to down approach. But in the case of agglomerative, you are doing something different. You are here, you are going up to down. In agglomerative, you will take because in agglomerative you have cluster 1, C2, they are unique clusters, means only one cluster. So you do merge it. Okay, you do merge it. Okay, so it is agglomerative as up to down approach. Sorry, down to approach, down to up. Okay, so that's the basic intuition behind agglomerative and divisive clustering. Okay, so we'll see in detail about agglomerative clustering and divisive clustering to help you better understand all of this agglomerative and divisive. But the basic intuition behind hierarchy of clustering is that you have some points, and what you do, you simply merge two cluster, because these P1, P2, P3 P4 are 4 cluster initially. You merge two cluster, and then you have some kind of similarity matrix. Okay, so you have some kind of similarity matrix that we will see. According to that, you merge it, and then you make a dendrogram or hierarchy of clusters. Okay, so that's what agglomerative, and agglomerative is just down to approach, where you are converting the clusters into by merging different cluster until and unless you have one cluster left at the top, like this C1. Okay, as an example. And in divisive, you are actually going up to down approach, means dividing the cluster into a single group. Okay, like A, B, C, D, E. Okay, so that's the basic intuition behind this agglomerative and divisive clustering. Okay, so let's start with agglomerative clustering, deep dive into agglomerative clustering to help you better understand what an agglomerative clustering does, and we will see a lot more about this. Okay, we will not see the implementation as of now. We will see in another section where now after this, I think we have completed this theory part. All those stuffs means we now have a good knowledge of everything. Now what we will do, we will make lots of projects. Okay, so here's an algorithm. So first let me write an algorithm. First I will write an algorithm, and then I will make you understand with the help of good examples that I've already listed over here. Okay, so here first what we will do, first we compute the proximity matrix. We compute the proximity matrix that just tells you the similarity between 2 points. Second, we will see just now how it looks like, and then you repeat these two process. Then you repeat these two process. Merge two clusters, and update the cluster, update the matrix, update the proximity matrix. Okay, so that's the basic, that you repeat in a for loop, and then you until you have one cluster, you have one large cluster left, means until you have covered all the cluster. Okay, until you have covered all the cluster. Okay, covered all the cluster, or we can say no clusters are left as a single cluster. Okay, but this is a more formal definition, until you have a good cluster, like as an example that I've showed to you. Okay, so this is a basic algorithm to understand in agglomerative clustering. Now let's understand this in more detail. Okay, so initially what I've taught, what I've note here, and what I'm going to note here, like I'm going to write note, which is each cluster, or P1, P2, P3, each are its own cluster. Now we'll build a hierarchy of clusters. Okay, so let's build on proximity matrix how it looks like. So the proximity matrix looks like this. Let's assume that you have P1, P2, P3, P4. Okay, just assume as an example. Now what you do, you do this P1, P2, P3, P4. Okay, now you do this, means this is a proximity matrix. This is your proximity matrix like this. Okay, and these diagonals are 0. These diagonals are 0. The diagonals are 0 because the distance between the P1 and P2 will be obviously 0. The distance between P1 and P2 maybe some 2.4 is P3, P4, like that. So we have written like that. The distance between P1, P2 and P1 is maybe something like that. And the distance between P2 and P2 is obviously 0. Okay, so this is what the basic proximity matrix looks like. So let's see that how we make a dendrogram. Okay, so here we have P1, P2, P3, P4. Now we will just assume that let's take an example that this is 4.6 to 4.2, 6.9, 7.2, 11, 12, 13, 14, 15, 16, 17, 18. Okay, it's a 0. Okay, so the distance between P4 is obviously 0. Okay, so the P2 we will find the smallest one. We will find the smallest similarity. Here you can see that this is the smallest similarity, P2, and I think it's a P2. And also I think that I've not drawn a good I will tell you. So here let's assume that you have this proximity matrix. Just don't take a look at this proximity matrix. Now what you will do, you will find the smallest similarity. So the smallest similarity over here is this 3. Here we have 3 and 6. Okay, so here we have 3 and 6 that we have done first, the smallest similarity. Okay, so that's what I'm going to do. So assume that this is P1 and P2 has the smallest. Now we have the next you can find over here is 4, means 6 and 4, maybe let's see 6 and 4, which is here. Okay, so we can go over here also 3 and 4. We can see this 3 and 4 also. Okay, so we can take this 3 and 4 like this. It's okay. So just assume the next smallest is P3 and the next smallest is P4. Okay, so now we have constructed. Now let's assume C2, P1, P2, P1. Then we have again maybe some P3 and P4. Now first you do this, then you do this, then you make this like this. Okay, so now you have the hierarchy of clusters. Okay, so that's the basic definition, that's the basic algorithm for proximity matrix. Okay, and this is what you do, and you update the proximity matrix. So how you update? Now you merge the cluster. Now what you will do, P1 union P2. Okay, P1 union P2. This one will be, let's assume P1 and P2 are attached, then P1 union P2. This will be the cluster. Okay, now let's assume that the 2.7 and these are similar, means this 2.7 and maybe some like that. So we can combine the cluster like that. I think this is not an actual example, this is a bad example. Okay, but here you will be seeing one more comprehensive example. Okay, so how do we measure the similarity? How do we measure the similarity of the inter-cluster similarity? We can measure the distance between two points or clusters, these P1 and P2, using maybe Euclidean distance, Manhattan distance. We have different distance measures. So how do we measure the similarity between two clusters or inter-cluster? An inter-cluster is nothing much this is your one cluster and this is another cluster. So what's the distance, what the similarity between to merge it? Okay, so that's the inter-cluster that we have already talked about in terminology sessions. So let's see. So we have let's assume that you have this. Let's assume that you have this cluster where we have this. Let's do another cluster So how do we measure the similarity? How do we measure the similarity? So for measuring the similarity, we have, I'm going to talk about three methods. I'm going to talk about three methods: min, the next method max, the next method is group average. The next method is group average. So let's start with min. So what do I do in min? So let's assume that you have this, so you have this data point like this, you have this cluster. You have this cluster. Now the second cluster is like this, second cluster is like this. Okay, so what you do in minimum? What you do in minimum? You take out the minimum first. Just write. Let me write it mathematically to make it more sense. Oops, what I've done. Okay, so what you have to do? What you have to do? So let me write it mathematically for minimum. So minimum is just the similarity between C1 and C2, which is nothing but equals to minimum of pi is member of C1, pi to be the member of C1. Let's assume this is C1, so pi may be this point, and pj, the another cluster, should be the member of C2. Now what you will do, you will take out the similarity, the similarity of pi and pj. Okay, these two. Okay, these two distance. Okay, now you take out the distance, that you take out the distance. I'm writing here distance, and you take out the minimum points who have, means here the distance between these 2 points is minimum as compared to this point, this point, this point. Okay, so we will just what we will do, we will simply merge it. Okay, so this is what the basic minimum approach does. It just takes out the similarity between C1 and C2 by taking out the minimum of all the I and j's, by taking out the distance between all the taking out the minimum distance of all I and j's with the member of C1 and C2. Okay, so that's the minimum. So let's see the basic thing over here to understand it a little bit further away. And this example is taken from CS6 530 by Cluster Analysis class lecture notes. This example. Okay, so here is your proximity matrix. Here is your proximity matrix where you have 1 as a P1, 2 as a P2, like that. Okay, now you have here you have a proximity matrix. Here you have a proximity matrix. Now here the distance between 1 and 1 is 0, the distance between 1 and 2 is 0.24, the distance between 1 and 3 is 0.222, the distance between 1 and 4 is 0.37, the distance between 1 and 5 is like this, and in the same way diagonal are 0. Okay, so you can see here the smallest similarity between, or smallest distance between 2 points I and j. Here we have, let's assume this is I and this is j. So smallest distance is 0.11, and we have 3 and 6. Okay, so we merge 3 and 6 as a first cluster. Okay, now the next smallest similarity, or the smallest distance, is this one. Let me choose, yeah, this one, 0.14. Okay, so 5 and 2. Okay, so this is your next smallest. So now what you will do, you will merge it at the second cluster. Now what you will do, you will find that this cluster you this 5 union 2 and 3 union 6 finds to be has the smallest distance, so you merge the cluster 3. Next is you have 1 and 4. Now what you do, first you take out the you can see, first you take out, first here we have 4, in which this union and this 4 has the smallest distance, so you merge it and then you make a big cluster again, and then you are done. Okay, so it might make sense, it might not make sense further, but I will walk you through, go through this example, make the dendrogram by yourself or nested clusters by yourself. Okay, that will make more sense. The next type of this is max. What do I mean with max? Max is simply, max is taking out the similarity between C1 and C2 which tells us the maximum, which we want the maximum distance between Pi and Pj, and Pi be the member of C1 and Pj be the member of C2. So that's the basic definition. That's the basic of this. Instead of we are taking the max. So what do I mean with max? So here we have an intuitive or comprehensive example. So here you can see that we have again the same proximity matrix. Now you can see that the smallest distance is 3, 6. Okay, you merge it. Now how you will merge this 4? How will merge? Why don't we merge with 5? Okay, so the distance between this 5 and 2 is a maximum, is very large. So obviously this one obviously will be minimum, so you merge it. That makes sense. That makes sense obviously. Okay, so this is why you take minimum distance, but for merging you take the maximum, to merge, and here you have taken the maximum, and that's how all it works. And here we have a maximum, here we have a minimum. So you take out a maximum, and then you compare, and then you take out a minimum, and this is obviously will be minimum, and then you can see this is the maximum here, and this is the minimum from here. So you merge it. Okay, so this is the basic, and you can see the dendrogram over here how we made. Okay, the next type of intercluster similarity measure. The next type of intercluster similarity measure is group average. What do I mean by group average? Group average. So I'm just going to give you the intuitive, as a simple equation, which is Pi be the member of C1 and Pj be the member of C2, Pi be the member of C1 and Pj be the member of C2. You take out the distance between Pi and Pj divided by the norm, because it's the frequency, divided by the norm of C1 with whatever the number of points times the times the norm of C2. Okay, so this is what you have to do. I think it may be plus, yeah, it may be plus, yeah. Okay, so you take out the norm of what is the number of points, frequency. Okay, so that's what you are going to do. So you can see over here that we have this dendrogram, we have this following, and then what you do, you group it. For example, you can see the same thing has been done, but I'm going to take another example to help you understand this much better. So you have this first, and then you have this second cluster. Okay, now you have some points, in here, and some points in here. Okay, you take each pair like this, you take each pair. Okay, now you average it out. Okay, and then you take out the distance, you average it, and then here you go. Okay, so for example, here you take out the minimum distance is 3 and 6, and then you have this 4. Then again you merge it using the in max what we were doing, but here we are merging 1 also. The reason being the average between will be making sense if you sense it mathematically. Okay, and 5 and 2 are closest. Okay, so this is what you are doing in group min, and let's see some of the just this minimum disadvantage. The minimum disadvantage is it is sensitive to outliers. It is sensitive to outliers, and rather than max is will be less prone to outliers. Okay, so that's the basic disadvantage that I've told to you, and you can see more onto the CS6 for 530 cluster analysis lecture notes to understand it much better. Okay, so this is what we are doing, and if you have not understood, it is a little bit advanced, but it should make sense little bit what we do in this. We make hierarchy of clusters like this. Okay, so now we have talked a lot about hierarchical clustering, and I hope that you really understood everything you need to know about hierarchical clustering. Now what I will do, I will just name some now what I will do, I will name a time complexity, and a space complexity. Now I'll name one time complexity and a space complexity for agglomerative clustering, just to make sure everyone is on the same pace. So the space complexity is order of n square. Okay, because we have a proximity matrix too, and time complexity will be order, or maybe sometimes it's order of nq. Okay, but sometimes it goes to order of n square log of Okay, so this is your space and time complexity to understand it much better, and you can see the limitations, pros, cons of these onto the Wikipedia pages. They are really well explained there. Okay, so we are done with the hierarchical clustering, and I really hope that you understood everything. Now we are done with unsupervised learning. Now we will do a lot of projects, and then we will end up this course. And I highly recommend you to do lots of projects also. Okay, and then after learning this machine learning, you can go to new era. Again, I'm going to just navigate here the URL https you can /youtube.com/new era. Okay, so you can find and just take a look at a newly launched deep learning series. Okay, from there you can learn advanced machine learning or deep learning. Okay, so that's it for this session. So that's it for whole this subsection. I'll be catching up your next section.
Okay, so now we will build or start our last section of this course, which is project section, and in this section we will build 2 projects, maybe some more projects, but initially I planned for 2 projects. Maybe I can add more, but you can surely go to my YouTube channel for more projects, but these projects will tell you an overview of how a machine learning project would look like, and the motivation for starting a new project, because it's better to make your project by yourself, just taking the inspiration from other people. Okay, so in this project we will build a heart failure prediction model that will predict whether the person will die based on some of the features or not. Okay, so this is the problem statement, and we have certain features like age, gender, blood pressure, smoke, whether the person smoked or not, whether the person have diabetes or not, what is the injection fraction, what is the etc. This is a long name which I can't pronounce, but this is a problem statement, and you can take a look at the data. You can take a look at the data which is available at this link, and I hope that you will understand this project. I will run step by step to help you understand everything. And as I have not worked on this project, so I just want to pick up this heart failure detection system just to make sure that I will be making my own project also, and I will be narrating over through this project. Okay, so here what I'm going to do is I'm going to make a heart failure detection based on these features and the target variable of our, which is the death event, whether the particular person died or not. So that will be the target variable. We will see more about the data. But what is the business objective over here? Every machine learning problem has some kind of business objective. It simply means that it's some healthcare problem, means we'll be able to build a healthcare, we'll be able to build healthcare, something AI in healthcare, which is simply able to make a machine learning model that will help you in early detection of the person based on particular features, and help the person can be saved. So that's why we are going to build that model to help you better understand the AI in healthcare. We'll be building one more project, which is spam detection system, that is whether the email or messages are spam or not. Okay, so let's start with this notebook, and first of all, I'm going to load the data and import the libraries. So I'm going to import pandas, numpy, seaborn, matplotlib, and this. Okay, so I will run it out, and then I will load my data. So I don't know why it's taking time, so now I will load the data, and my data is located in the folder of heart failure dataset. If you click on dataset, click on archive, and here is my dataset. Okay, so there I'm going to just print out head. And one more thing that I want to clarify over here. The reason why I'm not writing or coding by here, because I thought like it will be better if I narrate the code. If I'm writing the code, maybe I forget something, or maybe the code is not annotated too much. So that's for a few further references, I just took to just write it down over here, and then I'm only gonna to just narrate over there. Okay, most of them, because maybe while writing the code I may forget to narrate some of the code. But yeah, let me know what you like, whether I should write a code or not. Okay, so I'm going to print it down the shape of the data. I'm going to do the shape of the data is 29913, which is 13 columns, and here we have age, anemia, creatinine, phosphokinase, diabetes, injection fraction, HP, then battle age, serum, then what is the gender, smoking, time, and death event. Okay, and death event is our target variable that we need to detect. Okay, so that's our basic intuition, that's our basic data exploration. Now what I'm going to do is we will see how much the data we have. Means we will see what's the shape of the data we have. So here we are given the shape of the data, which is 299 rows and 13 columns. Okay, now using data.shape you can do. Now I'm going to take a look at the information about the data. You can calculate or you can take out the information about the data from the data.info method, and you can, if you see over here, that it will tell you whether the particular column has null values, what is the data type, and what is the memory usage, and it will also tell you what's the shape of the data by just taking. You can also take a look at this, and you can see that it starts with 0 indexing, so we have 13 columns. You can also take a look at the description. It will simply tell you whoever is the numerical column. It will tell you the describing means what is the count, what is the mean of the particular column, what is the standard deviation, what is the minimum, what is the 25% of that column, and 50% of that column, and 75% of that column, and max in that column. It will surely help in photo, means when if you're a data scientist, it will surely help. Maybe something kind of you are exploring what's the maximum. You can take a look at this, you can take a look at what is the standard deviation, what is the mean. Maybe you're formulating some problem based on machine learning, so it will be very helpful. This data frame, you can have a day, spend 5 minutes understanding what's this, and it's very easy. It will tell you the count, minimum, standard deviation, etc. Okay, so what we have seen so far, we have imported the libraries, we have loaded the data from a local directory. I'm going to take a look at the shape of the data. Now I'm going to take a look at information about the data. Okay, so here I'm going to data.info, and that will give me the information about the data. Okay, then I'm going to take a look at the description. Means what is the it will describe our numerical data, and then I'm going to take a look at what is the number of null values. So here this will tell you in all the columns how many number of null values are, and here we have 0, 0, 0 null values in each and every column. Okay, but if you let's take an example that you want, no, I don't want this, I just only want that how many numbers. So you can add some and then you can run it out to see how it works. So you can see that we have a total of 0 null values. Okay, so this is the basic exploration as I can do about the data. Little bit exploration about the data. Okay, now the main part will come in exploratory data analysis when we do so much of EDA and a lot more. So we will see over here how we do the exploratory data analysis. And here, what do I mean by exploratory data analysis? In EDA, it does not mean that it's a very hard, but it does not also mean that it's very easy. It's a very crucial step in machine learning. You should know your data, how it is working, what's the distribution of the data, is your data is balanced. You have certain questions to ask, which we'll see over here. Okay, so you have certain questions to ask to your data that using maybe some plots, maybe some numbers. We'll see that, and you have to find answers of your company, because if you're a data scientist or data analyst at some company, you should work mostly on to understanding and finding your business solutions. As I'm a data scientist at Artifact, I used to work a lot more with the data. I used to work a lot more with the data because I think that I should be able to what actually my data is and what the business objectives are and what's the answer they want from my data. Okay, so that's what I do, a lot of data exploratory data analysis there. So that's why I picked up this problem. I found it very interesting. I've not picked so much apart because it should be conserved, like advanced house price predictor, diabetes prediction system, which I already made, which is available in my GitHub, but I want you to try out, make your unique project and showcase on your resume. Okay, so then what we will do, then we will simply see the distribution of our classes. What do I mean by classes over here? For this example, we have a binary classification problem, and in this binary classification problem we are given 1 and 0. Okay, so whether if it is 1, then the person died. If it is 0, then the person not died. I think I have to see. Okay, so it's sometimes, yeah, so the person is living is 0 and the person is dead is 1. So we have two classes, which is the binary classification problem. Okay, so I'm going to take a look first. What I will do, I will take a look at the distribution of my data, and you can see I'm highlighting the code from where I'm taking a look at the distribution of my data. And here it simply means that I'm just going to take just going to data, then bracket, I'm going to take a look at the event. I'm going to count the number of event where the event is equals to 0, and I'm going to count the same where the event is equals to 1 by taking out the length of each arrays or CDs. Okay, then and also the pi takes an array, so I'm going to put it in an array like this. I'm going to put it in an array, so let me choose that red color and this medium. That works good. So I'm going to put in an array, and then I'm going to just label it just to make sure everything is right. So I'm going to label it with living and died. I'm going to print it out. What is the total number of living cases and what is the total number of died cases? Okay, and then I'm going to plot it out by just plt.py. I'm going to plot it a pie chart by giving our ARR. ARR will contain the length of life and length of death, like this. Okay, and then labels will be the same, living and died. Exploit, this is how much to explode our, and shadow, what do you want your shadow? Yeah, sure, I want the shadow. So I'm going to run it now. So I just hope that I've run the previously, so I'm going to run it now, and you can see over here that your data is imbalanced. We are actually working out, our data is imbalanced data. So I will tell you why this data is imbalanced. But first of all, you can see over here that we have total of 203 living cases and 96 which is died cases, and it makes sense also because in real world living cases is more than the dead cases. I don't know, actually I'm not, but I think so. Okay, so now let me show it to you in particular to help you get a feel that what is imbalanced data. Okay, oops, why it is not working? What is imbalanced data? So imbalanced data means, let's take an example that you have two classes. For an example, here we have two classes, living and death. Okay, so you have more examples of living, which is here 203 examples, but you have a far lesser, 2 times lesser than examples of 96. Okay, so here you are actually working on imbalanced data. What can be the issue of this? Issue of this can be that your model, in most of the model is most trained onto this living, so you can assume that the output of the most of the output of your model will be 0 rather than 1. In some cases that will print 1, but it will, in most of the cases it will be 0. Okay, so here we have some examples, so maybe it can, but your model is more prone trained under 203, and your model maybe get biased towards some problem. Means your model can be like this, print 0. Your model is this model, and it's only printing 0 at every time. So this happens when you have, for one cases you have 200. Let's take an example that you have a 400 examples. So for one cases you have 399 examples, and only one example for death. Okay, so that will cause the problem. Okay, a big problem. This is a big problem which comes as something called as, which was studying in deep learning, which is working with imbalanced data. Okay, so this is what I'm going to highlight. That I just want to take my answer. Is my data is imbalanced? How much examples for each case do I have? So I answered my question that we are actually working on imbalanced data, which is actually working here on imbalanced data where we have a living cases equals to 203 and died cases equals to 96. So imbalance simply means that your classes are not equally distributed. So can I write it out? Yeah. So let's write the definition. So I was just going to comment it out. Just to imbalance means that your data is not equally distributed between classes. Okay, so it may happen that if in balanced data, our data is equally distributed. So for a particular example, let's say you have a training length maybe 400. So if you have a training length to be the 400, so assume 200 is for death examples, 200 is for live examples. So we have equal number of examples in both living and death cases. Okay, so this is an example of balanced data, and our model works best here. Okay, it is more robust. It is not biased towards anything. Okay, so this is the basic. This is our first exploratory data analysis. Taken out the reference. So what we have done so far, we have simply drawn some EDA from here by taking out the length of each event for 0 and 1, and then I put in an array, and then I have labels, which is living and dots, and printed something, and then I'm gonna plot the pie chart with that. This explode comes with explode and shadow. We want the shadow, so you might be seeing the shadow over here. Okay, and you can see what the inference. So I answered my question. Am I working on imbalanced data? Yes. How much? Here. Okay, 2 times. Just an approximate. So our died case is 2 times lesser than the living cases. Or we can put in a percentage by just dividing it out to the total length of our data. Okay, so you can try it out more mathematically, but this is what I'm going to show you about this inference. Okay, let's move on to the next inference. In the next inference, I'm going to take a look at the distribution of our age. This will tell you whether your data is in what range. Most of the central tendency, I think that is here, the mean, most of the ages, like from 40 to 95. Okay, most of the cases 40 to 95 examples are starting from 40 to 95, and then you can see most of the cases are in around 60. Okay, and around 60 with some standard deviation. Okay, so this is the distribution of your data. You can try out for different numbers, which I've already shown to you. There are a lot more numbers. You can definitely try it out. Okay, make a pie chart for binary columns like high blood pressure, it was or not, or maybe gender. Make that column and see if it works. So I will show you how to filter out the columns from there. Okay, so now we have seen the distribution of our data. So now what I just want to check. So maybe my business objective is, maybe my lead told to me, hey, it's your data dashboard like this should be answering lots of questions. Lots of your questions about the data. Okay, so here we answered that you're working on this data means the total number of type cases is less than the living cases. Okay, which is 2 times less than the living cases. Okay, so that's how you do. And here you can see, you can say to your stakeholder or whatever the lead that most of the age rise from 40 to 95. Okay, so you can see from this and see, and you can tell most of the cases lie around from 50 to 70 like that. Okay, so this is the distribution of our data. So now say that you want to select the columns that are above age 50 and seeing they're died or not. Again, a very great secret. It can be solved. It can be put as a SQL query forum. But mate, you just think about what you want to do in pandas, or you want to do it like that. Okay, so it is possible in SQL, but it's not. I just as an example, yeah, I've made it in a Python. Okay, so what I'm going to do, my business objective is select the columns sorry, number of examples. I think that I've written wrong. Select rows that are above age 50 and seeing that they are died or not. So here, what I'm going to do, I want the death event. I want the death event because I don't want any column. I want the death event whose age is above or equals to 50 and they are living. Okay, and then again the same thing. And then again I'm going to take out the length of the same as above, and then I'm going to put in an array labels, and then I'm going to plot it. Okay, so if you can, if I run this, you can again see, you can see here that here we have living cases. Here we have the living cases a lot, and you have a small, but you can see the died cases. So if I write it out, I'm just going to write it out like this. So oops, I'm going to write a total number of let's say died cases. I'm going to take out the length of died. I'm going to do for total number of not died cases. Just I'm not able to write because I have two tabs in front of me. It's very difficult for me to tab right over here. Okay, so here length not died. Okay, so here if you can see that you are able to see that we have total number of died cases 85 and total number of not died 167. So just see over here that in total we have 203, which is 2 times lesser than, and here this is fairly 1 times lesser than. Okay, so here you can see that most of the cases again died, but most of the cases above 50 died. Okay, as comparatively to our plot. Maybe not making sense, but again I'm going to say that assume that just listen to me what I'm saying. I'm saying like you can see that in our plot we have total number of our died cases in 2 times our died cases is 2 times lesser than our living cases, and here our died cases is 1 times lesser than not died cases. So here we can see obviously this is low, but here you can see most of the people that are above age 50 died. Okay, from this inference comparatively from the upper plot. Okay, so here that's how we answer the questions from the data, and I hope that you understood everything, and I think that you will be taking out more inference. Okay, great. So let's see one more column, which is fairly good column, which I think, oops, get out. I'm just going to, yeah, here it is. Oops. Yeah, here it is. Okay, so now just assume that you want the columns that are above age 50 and you just see whether they are died or not. I think that I have already done. Okay, so you want that are above age 50. Oops, I think this is for diabetes. So yeah, so what you have to see, you have to answer the question that the person is having diabetes. How many numbers of patient who are died are having diabetes, and how many numbers of patient did not die having diabetes. Okay, so diabetes is where the person is not having diabetes and having diabetes. Okay, so maybe I've done a little bit wrong over here. The diabetes should be there, and we have to see whether the person had died or not. Okay, so you can see died with diabetes is this, and not died with diabetes is this. So there are a lot more, but you can again compare with the other plot over here, then it will start making more sense. Okay, so we have done extensive data exploratory data analysis. A lot more can be done to answer a particular business problem. Like this, you can see over here, you can answer some more questions from the data. But as to give you a taste of this, how I like to do the answer the problem using my favorite visualizations. Okay, so you can answer this. It's very good to answer this all by just visualizing it out and saying to the lead. Okay, so now we have seen a lot more things. We have seen more of the visualization. Just don't worry about this. These are again in the course website, mlo1.netlify.app. It's a very easy to get all these notebooks. Okay, so now you will check the correlation of our variable. So what do I mean by checking the correlation of our variables? It simply means that you know that how your features are correlated. So here you have a very good reference I've taken from Sago. They have explained it very much extensively, maybe some online. So here what it's telling, it shows the correlation between variables on each axis, and it just shows the. I will give you the plot over here. But what it does, it simply shows you the correlation ranges from -1 to +1. Okay, -1 to +1. It simply means that if your variable is closer to -1, then it's a very similar. Okay, if it's very similar, so you can see value closer to 0 means there is no linear trend, means linear thing is not there, so you can't use linear regression over there between two variables. Means we can this correlation tell us whether your data is a linear or not, and the close to 1, the correlation is more positively correlated. Okay, more positive means correlation between these things, and you can read about Pearson correlation coefficient over here because this uses something kind of that. Okay, that is one increase so that the other, and close to 1 to the strongest this relationship is, means the one is closer to 1, the stronger the relationship is. The diagonals are all 1. That simply indicates that the squares are correlating with each variable to itself. So it's a perfect correlation. So if you have all the data, all the diagonals are 1, so it's a perfect sign of perfect correlation. And the plot is also symmetrical, and I know that you know about symmetrical. So you can see over here, but I'm going to just put it in a form of this. I just hope that I'm going to put it like this. Okay, so I'm going to run it out, and here you can see that our data is perfect correlation. More the dark is -5.3, like that is the more correlated. Okay, so you can read that. It's very I have explained, and also you can do the same as your, like if you want to do with the PANAS. So here you are going to do, and your diagonals are again 1, etc. Okay. So we have talked about various things. You have understood data and etc. everything. Okay. So now I hope that you got an idea about how we process. So now what I will do, I will start with data set development. As I've talked about, that you should divide your data into training or testing set, because for testing you have to check some, you don't have real world examples. So for validating your model works best. So what you will do, you will divide your data into validation set, means training and validation set, where you are dividing 70-30. Okay, so 70% for training and 30% for testing. Okay, so you can run this out. We are using the sklearn API while importing the train test split. Okay, so now we have done this, and I hope that you understood this also. So now I will not do feature engineering over here, but I will just showcase to you what we do. Just one example of feature engineering. Okay, so in feature engineering we add more features, we encode our variable, we encode our categorical variables, we apply some transformations on our data just to insert our feature. Okay, so here is an example of adding the feature. Okay, so here what we are doing, we are adding the interaction term. Okay, so what is interaction term? Interaction terms means let's, for sake of example, assume that you have this data set which is gender and age. Okay, for an example, so it will add again one new column by taking out the product of G, Z, and not, let's take it a BP. Okay, anything means in numerical, so it will take the product and add. Okay, so it is just doing the product of two features and making that column. Okay, so maybe that will not make sense, but this is what the interaction term means we are just adding the product of two features. Okay, so here is a function for that. So first of all, we are taking the columns names, then we are taking the length, because we have to iterate through and then I'm going to copy it out so that we can't change anything to x, and I'm going to just iterate through all the columns, and ith column represent the first column, and this feature I name that this where it is, this column I'm going to access using the x, and then I'm going to range through j because I want to multiply these two. So here again the same thing, and again I'm going to take out the data, and I'm going to do just to make it this to just show the name of the column like this, that we multiplied, and actually we are multiplying this out, and then we are returning the x int. Okay, so this is what, and then we are calling on xtrain and xtest, and we are done. Okay, so here if you run it out, now you can see if I show you the code, if I show you the xtrain mod, do I run it? Yep. So let me run it again. You can see that we have 78 columns. We have 78 columns from we have 13 columns to 78 columns. You can try the result, how it is working, and let me know in the comment box below on in our Discord community. Okay, so this is what we are doing, and by adding the interaction term, you are feel free to explore more. Okay, now what we'll do, we'll start building our model. So how do we build? We will start building our model. So first I'm going to make a model for evaluating our model. So first I will take a look at the accuracy, precision, recall, and confusion matrix. So again, if I run it over here now it will give, and we are giving the ground truth as well as a predictor. Okay, first of all I will start with logistic regression with max iteration to be 1000. The reason why I've given over here, because if it is not converging, with any solver. So for converging, if you run it down, you can see that LBGS failed to converge. What you can do, you can increase the number of iterations, or what you can do, you can simply scale your data. Maybe my data is not scaled, so increased the iterations to 1000, and it worked. Okay, but it is also telling a process to standardize your data or to scale your data. So here for standardizing as well as the building the model, so we have something called this make pipeline. So what it will do for any coming example, it will standardize, and then it will it will apply logistic regression over there. Okay, so we are just doing in a small number of, and you can compare the result of the standardization and that max iteration. So the accuracy is actually better. Precision is also better. Recall is also better, and this is also better. Okay, confusion matrix. Okay, so I hope that you watched my session on precision, recall. But let me show you what those precision, recall, confusion matrix means. So maybe I have the this stochastic gradient descent. Yeah, so we just want to make sure that you are on the same base. Okay, so here I'm going to highlight one algorithm, which is optimization algorithm, which is same as our favorite gradient descent. But here in gradient descent, what we were doing, it is taking a lot of time. Why it is taking a lot of time? So here, assume this example. I'm going to narrow it over here. That let's assume that you have 10,000 data points, 10,000 data points, 10,000 data points, and you have 10 features. Okay, so here you have 10 features, and the residuals consist of as many terms as their data points. So you have 10,000 residuals because you are taking the difference between your predicted and the predicted model output value. So you have around 10,000 term in our case, residuals. So we need to compute the derivative of the 10,000 term. You need to compute the derivative of the 10,000 term with respect to our features, which is 10,000 times 10, which is 1 lakh computation per iteration. That is so much high. Okay, so that's why we have something called as stochastic gradient descent. So what we do in stochastic gradient descent, we choose simply as the same thing happens. We repeat until and unless our approximation is minimized, and then we randomly shuffle, and then we do at each step. it means we at only a step. So we don't update, we do updation as well as derivation at each step, and we are doing for each training examples, Okay, so it is a little bit out of the course. It's usual thoughts and maybe in deep learning, but I would highly recommend to learn this. Is just equals to the batch gradient descent. Okay, so you will be able to see what's the difference. Okay, so now as I've talked to you that we have something called as precision, recall, accuracy. So we have not talked about that. So let's talk about just to spend a little bit of amount of time onto that. So here TP means true positive. True positive means that your outcome that your model outcome correctly predicts the positive class. Okay, so you have in any model you have two positive and negative classes. Positive, negative classes. Positive, like 0 is a positive and 1 is a negative. Positive, so your model predicts the same output as your ground truth. Okay, for a positive class. True negative is where your model predicted 1 and your output is also 1, and true positive means 0 and 0. These are positive class and these are negative class. Okay, here you have false positive, which is your model incorrectly, your model predicted your 0 and actually the output is 1. So it is false positive, means positive and false because they are not matching. False negative is just your model predicted wrongly. Okay, so your model predicted 1 and your output is actually 0, means negative and positive class. Okay, so that's the true positive and negative. And confusion matrix is simply like this. First we have a true positive, false negative, false positive, and true negative that we have just seen. It will tell you how many number of are correctly classified as in a positive class, in a negative class, but in the model failed, in a positive class where the model failed, and this is a true negative where the model actually worked. Okay, so you can see we have seen. Okay, so precision recall. As we have talked about precision and recall, the number of a true positive divided by the number of a true positive divided by the number of a true positive plus the number of a false positive. So true positives TP plus by TP divided by the number of a true positive plus the number of a false positive. Okay, so this is your output. This is your output of the precision. It simply answers the question, what proportion of positive indications was actually correct? Okay, so it answered what proportion. So here we have 0.73, which is actually a good proportion, but it can be improved. Recall answers the question, what proportion of actual positive was identified correctly? Okay, so it will tell you that what is the proportion of actual positives was identified correctly. Okay, so this is the recall of our model. Okay, so now we will see. Now we will see the precision, recall, confusion matrix, etc. Okay, so now we will see. Now we have built our logistic regression with some standardization. Now we'll build a support vector classifier with a grid search CV with extensive fine tuning. We have C, which is lambda, which controls the width of that margin. So we'll try different differences: 0.1, 1, 10, 100, 1000. Gamma 1, 0.1, 0.1, 0.1, and kernel to be RBF kernel. And then I will call the grid source instantiate with the SVC classifier, param grid, ref equals to verbose equals to 3. I'm going to fit it. It will try for each and every and checks the score. And this is what the thing is. They have done. They have checked. And you can find out the best parameter that the model found, where C equals to 10 and gamma equals to 0.001. You can see it performs a little bit less with compared to logistic regression, but it worked. Okay, so we have done with the support vector classifier as well as logistic regression classifier. Now what we will do? We will make a decision tree classifier. Okay, so what do I mean by decision tree classifier is I'm going to import the tree, as we have already talked in detail. I'm going to import a randomized search. We have talked about grid search. Randomized search is same. So I'm going to define a function that takes the parameters takes how many runs to CLF what the classifier to use. Okay. Then we will call a randomized on CLF. First we will give the CLF, which is classification, number of iterations, etc. Then we'll fit it, then we'll find the best parameter, then we'll find the best score, and then we'll say this, and this is just a custom made model, but you can surely remove that and just use that randomized search and then put all these. So I have already done in some of my projects. So I've just taken out from there, and it's working great. Okay, so it will tell which is the best, which criterion is the best, whether entropy or Gini or splitter or mean weight is. I have done a lot of fine tuning. Okay, I will run it. It will take a little bit amount of time trying all the values and checking the score, and you can see the training score is 0.84 and the test score is at 0.75. Okay, now we will run this classifier with the same with these features. Okay, so it will give me the output like this. Now I will run it out. Maybe you can see. Okay, so you can see how well it is performing. Maybe I have not. Let's see the best score, randomized search best score. Okay, yeah. So that's the basic, and you can also try it out. Maybe I'm a little bit. You can see. Let's see if it is not good or not. Oops. I have to also show. Okay, so it is showing the best classifier, so I have to put it over here. I don't know why I put it over here, but what I have put it now in what mine, but let me put it. Okay, let's run it. It's actually 0.75, so I have obviously done some fine tuning, and here what I got with a good parameter. Okay, so it not always this works best. In some of the cases it worked. Okay, so now with little bit of fine tuning, I'm going to call a random forest classifier. Then I'm going to run it with a parameter set that we got with a random forest. Okay, it will evaluate my model, and then 0.86, 0.1 actually good. Okay, now what we'll do, we will use XG boost. Okay, XG boost is another we have talked about. We're learning by 0.1 max step. What is the number of parameters? Then I'm going to put evaluation set into one array. Okay, so just see the log loss at the same time, and then I'm going to run it. So it will tell at the log loss of the 0 iteration, and 0.32 is the log loss, validation loss. Okay, now we will evaluate, and here you can 0.85 is more robust model. Okay, it is a robust model. If you can see the importance, it will show what features are more important. So time is very important, injection is very important. So in this way you can select, you can discriminate, so maybe smoking, anemia, sex, creatine, and then means these three you can remove as a feature selection. Okay, the last thing that we are going to use is a gradient boosting classifier. Gradient boosting is mostly used in a cases of images, but let's see how it works with these hyperparameters. You can also fine tune it to get better results than me, and it actually worked. Okay, now what I will do, I will save my XG boost model, because XG boost is more robust. So I will save my model by just calling for joblib.dump. I'm going to load my joblib. If you can see, if I run it, now you can see that 001, and you can see if I go over here, if I go over my hot failure and model.pkl file, and you can load this model.pkl file to make a good model. Okay, so that's a basic thing that we need to understand about this hot failure detection system, and I hope that you have understood a lot from this. Okay, so thank you for seeing this section, and I really hope that you enjoyed this, and we have covered this project in 42 minutes. In the next project, we will be talking about a small project, spam detection system, which is again a very cool project, which is understanding problem statement and building a good model. Okay, so let's meet at the next project. Till then, have a good day. So now we'll talk about, or we will make one project, which is spam and ham detector system. So if you have seen your Gmail or Google Gmail or Microsoft Outlook, there you are seeing that you have a tab which is spam tab, where all your spam emails are there. So in the same way, we are going to build a spam and ham detector system. So a spam means that a particular message may be corrupt, and ham means not a spam, just opposite to spam. Okay, so just ham means not a spam. I don't know why it does not work for the first time. Not spam. Okay, and here you can see that that we have a label means we are given a message. We are given a message, and we are given the target label, which is our y. Okay, so this is our message. Maybe go until journey point crazy, and then there is a label which is given over there. Okay, and this data set is downloaded. This data set is downloaded from a UCI repository, and here is our data set. So it is in table. So I'm not going to use CSV. I'm going to use table to read that. I'm going to separate by a tab. Header should be none, and the names of the columns should be label and messages. Okay, so let's take a look at. We will take a look at the first few data points. So let me run this out. First of all, this, and then this, and then I'm going to show you one of the messages there. So it should start making sense to you. So here, data. Oops, what happened? Data. I mean, this is the messages. It will take a little bit of time. Then 0th position. So you can see that go until journey point crazy, available one, etc., etc. And here it says that it is a ham. It means not a spam. So for example, let's assume this second number, because in second number we have it labeled as a spam. So free entry, it's looking like a spam, like it's free entry or winner, like that. Okay. So that's the basic exploration of our data, and this is downloaded from UCI repository. Okay, so I think that you understood. We are given a corpus of a test. So here we are not given any numbers. Here we are given. Here we are not given any number. We are given. Oops, what is happening? We are given a messages, which is X as a messages, which is in text format. So your neural network, or machine learning model does not work with text. So you have to convert the text into numbers. So we will see some of our favorite text a vectorizer to convert this corpus of a test into a matrix or a vector or a number of a vector. We will see that. Okay. So here you can see that here we are given a data which is text and this one, and then we have a label. Okay, so now we'll start exploring our data set. So now we have got our problem statement that we are given a corpus text. We are given a text, and we need to pass it through a pipeline and give it to your output, whether it is a ham or a spam, or ham means 0 and spam means 1. Okay, so that's our favorite given. Now we will move forward. Now we'll move forward into exploring our data. So I've already explored it, so let me rerun it again. So here I hope that you all are able to see this. So maybe you, and if you're not, don't worry. We're going to take a look at the shape of the data, which is 5,572 with 2 columns, and then we have a null values to be 0 because we don't have any null values. We have 2 infos, and here which is a count, unique values, what is the frequency, etc. And obviously in the text you don't have numerical things, so that's why it's empty. Okay. Great. So we explored the data very much. Now it's time to again start with exploratory data analysis. Okay. So in exploratory data analysis, in our previous project, we have seen that we have to see the distribution. We have to see the distribution. We have to see the distribution of the classes. Okay, so here we are seeing the distribution of the classes by just taking out the length and converting that into a length. Now here you can see the labels, which is ham and spam, and it will tell what is the number of total labels with the plotting the pie chart. And you can see over here that the number of ham examples is 4,825, and spam examples as 747. So we are actually working on imbalanced. We are actually working on imbalanced data. So your model will learn more about ham rather than spam. Okay, so be sure to keep that in mind. Next, we will now it's very important. Like for an example, so let's understand the processing of our text, how we clean our text, and why it is there a lot more need. So what do I mean by cleaning? Is, for an example, let's assume that you have a Go. Okay, so you have Go. Go. Okay. Small g. I don't know why it is not working again. Okay, so here you have Go, here you have Go. Okay, it says small O. Okay, so these two will be considered different. These two will be considered different, but this is the same. These two will be considered different, but this is the same. Or maybe this hashtag does not need any sense over here. So why do we need hashtag over here? Maybe we don't need like this. We don't need emojis, but in some cases, like in sentiment analysis, emojis plays an important role. But here Go and Go are the similar thing. Maybe here we have these if we give to the model, these two will be considered differently. So that's not a good thing. So what we will do, we will convert all our text into lower text. Okay, now here we are doing some text preprocessing that you need to know. Okay, just using regex. Okay, so I'm going to replace here. I'll be given one simple message. First of all. Okay, I'm going to first lower it down by converting that into a string. Then I'm going to replace this zero. If there is any zeros in the text, will be replaced by m. Okay, and this 3 will be replaced by k, and k is 1000k or 100k or whatever. This comma will be replaced by this. Sorry, the above I'm not recalling what's the name, and this I'm not recalling, but yeah, you can see. Okay, so then you have won't will be here. It will be considered different. So will not. Okay, cannot should be cannot, can't should be cannot. Okay, we are just doing n not equals not. What is it is. Then we have his, he is, she is, s own, percentage, then etc. and then here L will. Okay, so this is the basic text preprocessing that I've done over here. But one thing that I can also do over here. Like stemming. Okay, stemming, lemmatization. So I would like you to explore this. I would like you to explore both of them and implement over here. Okay, and first of all, let me tell you what is stemming. Okay, so stemming, it simply means, it simply means that, for an example, so if I go to some website, let's take an example that I write play, I write PLAYED, then I write player. Okay, so the stemming will give play, means these 3 words will be converted to this single word because they make a similar sense. Okay, so that's the stemming, and lemmatization is just a bigger version of that. It makes a meaningful. Sometimes stemming does not make a meaningful word. So for making a meaningful word, we have lemmatization. But again, lemmatization, what is just? So for example, plays, plates, played, and players. So it will convert in play, and the stemming will convert in pla. Okay, so it is not making sense, but this lemmatization is making sense after we lemmatize our word, or we convert our corpus of a word into a single word. Okay, so that's the stemming and lemmatization. But I want you to explore stemming, the word stemming, lemmatization using NLTK library. You can refer to some of my GitHub. I have already done that, but I want you to do this. Okay, so otherwise no task will be left for you in this task. Okay, so here what we'll do, then you apply to each messages by making a new column. You apply to each messages these text preprocessing by doing this all, by calling the lambda and calling the lambda. It will go through each step. It will go to each step and apply the function onto each messages and put that into a processed text. So let's take an example of that. So it will start making more sense if you take a little bit of example. Okay, so what I'm going to do is I'm going to print out not first, which will be our favorite not processed text. So I'm going to print out first, which is not processed text. So this is data, and then I'm going to post over here. Now I want the 0th element, and now I'm going to make a simple line. Oops, what happened? I'm going to make a simple line, so it just makes this. And then I'm going to just paste it over like this. Okay, so it will show you what is the preprocessed text. So this preprocessed text is converted like this. Okay, so apply stemming. Okay, by using the Porter stemmer, you can go to NLTK stemming. Okay, there is something called as lemmatization. So you can see some of the tutorials which are available in Geeks for Geeks and etc. So read it out means you can go to any of them, whatever you like. It just converts the words into yeah, here is a good example. So playing, played, played, so it will come common root from play. Okay, so this will be converted like this. Like stemming is the process of reducing your inflection into words. Okay, so you can read this out. This is a very good documentation provided by DataCamp, and you will get to know much better about this. But I will be bringing up one full course onto natural language processing. Just this is a sample how to work with the text, but on new era, one full course on deep learning, where we will be talking on deep learning. We'll cover text working with the textual data. Okay. Now I'll go further into feature engineering. What is feature engineering? Here we are not going to add any features. We're just going to encode our ham to 0 and span to 1 by calling our map method. It's done. Now we'll divide our data into 20 split. Now if I run it, here we have total number of this, and then what we will do. Now just assume, now just see over here that in training set we have our text, but machine learning will not accept the string or whatever the textual data. So what we have to do there is modern means word embeddings. Then we convert our word, and then we convert our word into maybe this word into some numbers. There are a lot more techniques: count vectorizer, TF-IDF vectorizer, bag of words, which I'm not going to again talk about. Again, it's time for you to explore. As of now, you can just think of it as, you can see what's the mathematical equation for that. Just a single mathematical equation. But what it does is simply you can go to sklearn feature extraction. Just extract the features from the text, means it converts your text into the numbers. Okay, by just we instantiate over here. Now what it will do, it will fit the training data, means, and it return the matrix. And then we don't want to fit the text testing, so that's why we are just transforming our text test to the numerical into the matrix. Okay, that's it. Okay, so this is what we use to convert our text into vector of numbers. Okay, so if I show you the training data, how is the training data is a sparse matrix. Okay, it's a sparse matrix which is with 55,209 stored elements into that. Okay, now we will use naive Bayes. I hope that you understood, and I hope that you had a look on naive Bayes on this, as you have told to do the assignment. So I hope that you had a look at naive Bayes. You can read more about naive Bayes. It's just a very simple, as we talked about some other learning algorithm. It's very, very simple. Okay, so you may run this and then you just call a predict, and here you have accuracy. So now let's give a corpus of a text. So let's take an example. Here you have a text. Here you have a text, and I'm going to write AYUSH is a good boy. I think let's see if it is a spam or not spam. Okay, so I'm just going to convert that in production. What we do, we write a function process. We write a function. It will take a text as an input. Then what it will do, we call our count vectorizer, which we call over here. So I'm going to call my count vectorizer like this: count vector dot transform. I'm going to transform my text, giving this. I'm going to do this num. Okay, so it will contain the basis of vectors. Now I'm going to just call my model, which is maybe it will take a model. So I'm going to call my model, which is here, naive Bayes, and then it will simply dot predict. Now it will simply predict my txt. Okay, and then I'm going to, oops, it's numna. I've just converted that into a num. So it's the prediction. It's the prediction. And then what I'm going to do, I'm going to return the prediction. Okay, so here if you call preprocess and then preprocess and predict, so it will take text as an input and it will return. Maybe it's some problem. Maybe I have to do count vector dot fit transform. What happened? Preprocess iteratable over raw documents string object received. Okay, no worries. So maybe what's the problem was causing is I given this messages and instead of this pre-processed, but we need to give the process text instead of messages. So here we are given the messages. Now we are just going to provide in the CDs, and then I'm going to do count vector dot transform, giving the stock, and then providing naive Bayes dot predict, and this will predict whether that it is a spam or a non-spam. Okay, so that's the basic spam and ham detector system. Obviously you can try more stacking, various things over here, just to give you a taste how the natural language processing project, how we work with the data, just to give you the taste of our data. Okay, so I think we are completed with this project. I'll be catching up you in the in the next. I think that we are done with this this course. Maybe maybe we will talk about simple perceptron, and then we will wrap up this course. Okay, so thank you for seeing this course. I would highly congratulate you for completing this course.